participants are asked to detect violation of helmet rule for motorcyclists. The dataset is obtained from one of the developing Indian city. The training and testing dataset consists of 100 videos each recorded at 10 fps, 1080 pixel resolution for 20-second duration. The dataset consists of three different light conditions and weather conditions like daytime, nighttime, and fog conditions. The training dataset consists of approximately 65,000 annotated objects, which have minimum width and height of 40 pixels. The dataset is annotated on 7 different classes like motorbikes, driver with and without helmet, passenger 1 with and without helmet, and passenger 2 with and without helmet.
Thank you, Sanjita. Yeah, and we have also confirmed that there is the evaluation metric will be updated, and so today during the award announcements, we will be using all the successful submissions for track 5 to reconduct the evaluation, and so the leaderboard will be updated. So just a heads up, and we will announce the final ranking in the afternoon. Okay, now let's have Professor Anastasiou to present for the evaluation.
Hello, everybody. So for the evaluation for track 1, we had the same evaluation as last year. So track 1 is city scale multi-camera vehicle tracking, and the object is tracking people across multiple cameras in 10 plus hours of real and synthetic videos. So I guess not the same as last year, but same as what we used for multi-camera vehicle tracking. So this is actually people tracking, sorry for the typo there, which is we use the IDF1 score adapted to multi-camera setting. For track 2, tracked vehicle retrieval by natural language descriptions, this is where we use the same scoring as last year. So mean reciprocal rank, or MRP. For track 3, naturalistic driving action recognition, we actually changed the scoring from last year. Again, the challenge here is identifying driver distracted behavior from multimodal driver video data. Last year, we had an F1 score type scoring that was very firm on when the action started and ended. And we found that a lot of people detected the correct activity, but not necessarily the start and end time of the activity. So this time we changed the scoring to allow for those events to be captured better. So the score is based on average activity overlap score, where activities must start and end within 10 seconds of the ground truth activity start and end times respectively. For track 4, multi-class product counting and recognition for automated retail checkout. Here, what we're trying to do is identify items passing in front of camera in an automatic checkout retail scenario. And we use the same scoring as last year, which is F1 score, where true positive is when the correct object is identified once while the object passed through the ROI. And track 5 is a new track this year, detecting violation of helmet rule for motorcyclists. We detect motorcycle riders with and without helmets based on traffic camera footage from India. And we used mean average precision across all frames and test video, ignoring small and redacted bounding boxes. Unfortunately, this year we had some challenges on the evaluation in a couple of different tracks. We found some bugs in the evaluation script. For one of the tracks, we were able to correct it before the challenge was over and allowed the teams some extra submissions in the last week to account for the error. For track 5, unfortunately, we didn't find the bug until after the evaluation time was over, so we reevaluated using the correct metric all the submissions that were submitted up to that time. So this, as Thomas said earlier, the prizes that will be given will be based on the reevaluated scores. Also, the evaluation server has not been updated yet for track 5, but will be updated hopefully today or tomorrow. All right, next slide. All right, so as in previous years, the way that the evaluation system works is each team is allowed up to 5 submissions per day, per track, per team, with a total maximum number of submissions, which is different for different tracks. Initially, we had 10 submissions for tracks 1 and 4 and 20 for all the other tracks. And a couple of the tracks got extra submissions due to evaluation system errors. Then validated submission, the system evaluates the submission online and validates the submission format and sends errors back so that the teams can fix those and resubmit, and those errors don't count against their submission total number of submissions. Leaderboard shows during the evaluation period, the leaderboard shows the team's own rank and anonymized top 3 scores for 50% of the test set. That makes sure that teams can't tune their algorithms specifically to that test set, the overall test set. And as we expect methods to be generalizable and work on larger test sets from the same distribution. The full leaderboard was available after the submission closed, which was March 26th at 6 p.m. And as in years before, the last couple of years, the leaderboard, the teams had a choice of submitting to the public or the general leaderboard. And to the right, you see a picture of the leaderboard for track 4 general submissions. All right, moving on. Okay, so these are some statistics about submissions. We had 2,482 successful submissions to the evaluation system. That's an increase by over 780 submissions from last year. We had 129 teams submitting, which again is an increase of 10 teams from last year. We had 9 loaner submissions, and that means one team submitted to one track only, one time, basically. And that's an increase of 3 from last year. We want to have fewer of those, which is why it's red. Then the average number of tracks a team submitted to is 1.36. That's an increase of 0.11 from last year. What that means is a large number of teams submitted to more than one track. And then in the tables, you see statistics for the public and the general leaderboards as far as number of teams, number of submissions, and mean number of submissions per track. So we can see for the general leaderboard, track 1 had about a little over 6 submissions per track. Track 2 had 10, track 3 had 20, track 4 had 6, and track 5 again had almost 20 submissions per track, and slightly less on the public leaderboard. The graph to the right shows the distribution of the number of submissions for the period of the challenge, which was 32 submission days. Obviously, it took a little while for teams to get started, but once they did, there was a consistent submission on both the public and the general leaderboard, and a lot of teams submitted heavily in the last week. All right, moving on to the next slide. Some more distributions of the submissions on the left-hand side for all the individual tracks and cumulative for all the tracks. So this shows that some teams had a lot of submissions, a few teams had a lot of submissions, and then some, half the teams submitted less than half of their allotted submissions. And then the graph to the right shows the overall number of submissions for different teams. So teams that signed up for the evaluation server early on probably were repeat teams from previous years, and they had lots of submissions. And teams that signed up for the evaluation system late had higher team IDs, and they had much fewer submissions. Moving on. Finally, after the evaluation server closed, we went ahead and reopened the evaluation server after saving the database so that we could use that data for evaluating for prizes. And these are some statistics of improvements. Oh no, never mind. I'm thinking of the next slide. So these are some statistics of improvements for the different teams from their first submission to their last submission, or their best submission. So we had 70 teams that had more than a 10% score improvement, relative score improvement in at least one track. And that's 18 teams higher than last year. 10 teams that had a 10% score improvement in at least 2 tracks, and 5 teams that had 10% relative score improvement in at least 3 tracks. And all of those are improvements over last year's submissions. And the table to the right shows shows the mean and the maximum improvement between the first submission and the best submission of a given team. So quite a lot of improvement. A lot of teams just submit something as soon as they get their code working, and then eventually they get much better algorithms working and get much better scores. And that's the whole point of this evaluation system, and allowing teams to submit against a leaderboard for up to 5 times a day is, once teams see the score and how they stack up against the rest of the teams in the competition, then that allows them to improve their methods and try again and get much better scores. Right, moving on to the next and I believe last slide of evaluation. Right, so after the evaluation was closed for the competition, we reopened the evaluation server and had teams submitting more evaluations. And so overall, we had 2,669 successful submissions. So an increase of 187 since the last day of the competition. We had more teams that signed up to submit to the evaluation server, an extra 7 teams, and 2 extra loaner submissions so far. So overall, up to last Friday, I believe, when I compiled these data, we had 59 submission days. And the graph to the right shows the number of submissions per day across those 59 days. Right.
Thank you, David, for all the very detailed statistics. And I think this will give us a whole picture of our evaluation and how complex it is. Okay, now I will present some observations for track 1. In track 1, which is on multi-camera people tracking, what most teams did is that they used the pipeline of object detection and extract ReID features from all the bounding boxes, and then use the ReID features for single camera tracking and also the clustering across multiple cameras. And most of the teams, they use YOLO-based models for detection. Actually, for all the submitted papers, they all use YOLO detectors. And also all the teams use the SORT, sort-based methods for single camera tracking. And what did the leading team did, which improved their accuracy, and we will see more presentations afterwards. I see that many of them use Hungarian algorithm to enhance the robustness of the clustering besides the hierarchical clustering. And also many teams, they use the post estimation to find the foot point using the average of the anchor points, and then use that to refine the homography projected locations on the ground plane, which is very effective. What we learn year over year is that people-based MPMC tracking is very challenging because of the unconstrained movement. So this is more challenging compared to vehicle-based tracking. And also, we found that foundation models and domain adaptation methods have a lot of potential. A lot of leading teams, they use the foundation model-based ReID models to extract features. And also, we have synthetic and real data for multi-camera tracking because it's extremely hard to annotate for multi-camera tracking. So using synthetic data is the trend for the future. So domain adaptation is very important. And as for the future directions, we want to improve the synthetic data with auto calibration. So teams don't have to conduct calibration for 129 cameras. And we will also offer more complex scenes using the synthetic data generation. We also encourage teams to explore 3D tracking using graph-based methods. Okay, Fred, you can present for track 2's finding.
Yeah. So the track 2 is, we have the track 2 for 3 years, and this is the 3rd year. This track is about the track vehicle retrieval by natural language descriptions. And from last year, I think this time most teams take the best model that people developed last year and use CLIP to combine the text and image information for the feature extractor. What the leading team did is to use a semi-supervised domain adaptive training strategy to fine-tune their cross-modality retrieval model. And finally, which is also one thing that we observed last year, that's also getting improved this year, is the multi-contextual pruning, which is a post-processing to fine-tune their outputs of the retrieval result. CLIP is like, so what we've learned year over year, first thing is the CLIP, which was what the prior year's leading teams, including the first year, like 2 years ago, people using CLIP to get a very good results on this challenge track. And this is now what most teams adopted as the baseline model. And also we've observed a big improvement on the retrieval performance, which is going up from 66% up to 82.63% mean reciprocal rank. This means over half of the ranks were correctly retrieved at rank 1. So for future directions, we were thinking pseudo labeling of the existing data sets. Introducing more data definitely helps a scenario like this. Semi-supervised domain adaptive training strategy, which is what the leading team is doing, that can also introduce much more data into this challenge track, and we hopefully can see an improved performance. And finally, post-processing is one essential part for this challenge track from what we've observed in the last 2 years. Yeah.
Thank you. Thank you, Fred.
Thanks.
Okay. I can present for track 3's finding. So what most teams did is that they use this classification of different distracted activities such as phone call and texting and yawning. Many teams use temporal action localization to determine the start time and end time for each activity, which is what we use for evaluation. What the leading team did is that they utilize a clip level video recognition action probability calibration or multi-attention transformer module for the classification, and non-trivial clustering and category customized filtering was used for determining the start and end points. As for future directions, the notations for each activity can be more refined for better localization, and also we want to create cleaner ground truth labels to improve the development and evaluation of the research process, and also increasing the data size with adequate representation can improve the classification results as well. We want to go from 30 drivers to 60 to 70 drivers in the future. So the team from the Iowa State University, they will continue to improve the data set for the future. Now let's have Yue to present for track 4.
Yeah, in track 4, we have the domain adaptation settings where we have source as the synthetic data and targeted real-world data. So what most of the team did to perform the domain adaptation to make the synthetic training really similar to the real targets. And also in terms of the task network, they follow the detection, tracking, and counting framework. This is what most teams did, and for the leading teams did, they may further optimize the training data by using the content mismatch between the synthetic and the real. So they use the task accuracy to optimize the content mismatch. And also they have the one more leading teams did. They also improved the association algorithms in the tracking part. In the future directions, we may see in this track we have seen the improvements in the both data-centric OS and also model-centric OSs, and they may some kind of separated in current situations, and how to make them cover each other to get higher accuracy. And also, one of the future directions is we have to need to build a real-time system. In our evaluations, we have seen that current system may still have need a large computational resource, but need far from the real-time system. So this is one of our future directions.
Thank you, Yue. Finally, and last but not least, let's have Sanjita to present for track 5.
In track 5, most of the team had tackled the problem in 3 different steps. First one is object detection, where the team had used different pre-trained models like Dita algorithm, YOLO V8, Efficient Dead, and it is used to detect the motorbikes, driver, and passengers. Second step is object association or identification. It is used to extract the correct position of driver and passenger and whether the person is wearing helmet or not. The last step is category refinement model, which is used to generate the correct result, correct the misclassified classes. So the leading team had used YOLO V8 for object detection. They had also built identifier model over YOLO V8 and differentiated between motorbikes, driver, and passengers. They had also used assemble approach to combine multiple models of output. So in future, we can add more congested video in order to increase the complexity of data set, and we can ask participant to build a real-time system for that.
Thank you, Sanjita. So that's all our observations. We will release the final results in the afternoon. So I hope that you guys can all come back in the afternoon for this exciting results. And now we will have a special speaker for us, our keynote speaker. Let me introduce Professor Laura Liu-Taxi. So she is a pioneer in the field of multiple object tracking. As you know, my advisor, Professor Huang, knows that since my PhD study, I have been using the MOT challenge dataset to pursue for the MOT to pursue the state-of-the-art of multiple object tracking. And Professor Liu-Taxi has recently joined NVIDIA as a research manager, and we are very honored to have her present for the keynote today. Professor, you can take over for the presentation.
Thank you, Thomas, for the kind introduction. So let me share my screen.
Oh, just a second. Let me try to change you to the correct screen.
Yep.
Okay, I think everyone can see you now. Thank you.
Okay, perfect. So as I said, thank you for the introduction. It's really a pleasure to be here today. And I want to talk about some of the work that we did while I was still at the Technical University in Munich, and that we are now working also to transfer to NVIDIA. And this is about something that is often kind of not really, people don't really pay attention to this problem in tracking, which is the problem of long-term tracking. How can we actually keep tracking objects that are occluded for longer and longer times? So let me start with the task, right? So I think we're all familiar with the task at hand, multi-object tracking. Given a video, we want to find all the parts in the image that depict the same object in different frames. And it's oftentimes the case that we use tracking by detection as a way to break down the problem into two simpler parts. So the part of applying an object detector first in all the frames of a video, and then the part of data association, in which we want to find the correspondences between these detections across frames and so form trajectories. Now, in this talk, I will differentiate two types of association steps, what I call short-term association and long-term association. So short-term association is what happens from frame to frame. And this is often what regression-based or attention-based trackers are doing, which is to regress a bounding box from the first frame where it was detected to the next frame. These are often online trackers, meaning that you track from frame to frame, you kind of propagate the boxes from frame to frame. And of course, these are very powerful because they are online trackers, but at the same time, they lack robustness under occlusion. So as soon as the object becomes occluded, they are not able to track it. And so we have to use other techniques to track this object or to re-identify it once the occlusion is over. So in order to solve this problem of mostly of occlusions, people have also been working on long-term association, which means actually connecting detections across different time frames, and especially connecting detections like, for example, this blue detection here that has been occluded for a long time, for example, 10, 20 frames. This is kind of the time horizon that people were working with until now. And so one of the most used long-term association paradigms is actually graph-based association. And in this formulation, what we do is we pose the multiple object tracking problem as a graphical model. And this means that every detection is going to be represented in our graph as a node. And the edges are going to represent possible trajectories. And by possible trajectories, I mean that if I want to represent a trajectory throughout this graph that I, for example, represented here in red color, all that this means is a connection between detections from frame to frame. So every edge is going to connect two detections, and it's going to say that these two detections actually belong to the same trajectory. So in this case, we're going to have three pedestrians in the scene, which are identified by three paths through this graph that are connecting all the nodes, depending on how many detections these trajectories have. And so back in, pre-deep learning era, 2008, how one would normally find these trajectories is by working with network flows. And this is why I'm putting here a little bit of a vocabulary, because so I'm going to use these words interchangeably. And so one node is going to represent one detection, one edge is going to represent one trajectory, and this is also called one flow in this vocabulary of network flows. And also in this vocabulary, one unit of flow is going to represent one pedestrian. And so you're probably understanding more with this slide when I say that finding the trajectories in this graph is equivalent to solving the minimum cost flow problem, which is defined by determining the minimum cost of shipment of a commodity through a network. Now, in our case, the commodities are the pedestrians. And all we want to do is we want to ship these pedestrians from the beginning of the video towards the end of the video. And we want to find the optimal paths for these pedestrians to go through this graph, or to go from the beginning towards the end of the video. Now, of course, this is represented as an optimization problem. And for this, we have, of course, an objective function that is a minimization problem. And this is going to be mostly driven by this term Cij, which is nothing else than a cost associated to an edge. And this is essentially where you're going to put all your information, all your appearance information, all your geometry information is going to go into this definition of the cost of the edges. So since we're talking about a minimization problem, and we know that the costs are what is going to be driving the tracking, we're going to need a function that defines cost in this way. If we find two bounding boxes, two detections that represent the same person, we want to assign the edge connecting these two bounding boxes with a very low cost, because we're solving a minimization problem. So edges that have a low cost are good for us. They are edges that are probably going to be present in our final solution. If we have two bounding boxes that represent different people, we don't want them to be connected. So we're going to assign a really high cost to the edge that connects these two detections. So just for completion, of course, we have our indicator function that indicates whether the edge is active, and it takes the value 1, or whether the edge is not active. When the edge is active, this means that the two detections are connected and they form a trajectory. If the edge is 0, then it means that these two detections are not connected. And this is how we're going to find our optimal set of trajectories. Now, everything that I've said up until now is something that it doesn't involve any machine learning, right? So you extract features in whatever handcrafted way you want, and you put these features into your costs for your edges. And then you solve a discrete optimization problem to obtain your trajectories. There is absolutely no machine learning involved. Now, of course, we want to keep optimizing this. We want to learn some, like part of this optimization, part of this feature extraction, but from data, right? We want to infuse some machine learning in this problem. So how can we do this? Well, the easiest way is to actually learn the cost, right? So let's say that we have these two detections, and instead of learning some handcrafted way of defining the cost, we put any information that we want in there. In this case, I've defined it as spatial temporal cues. We pass it through a neural network, and the neural network will map it directly to a cost value. In this case, these two detections do not belong to the same trajectory, so the cost should be very high. In this other case, the neural network should detect that these two bounding boxes belong to the same trajectory and should assign a very low cost to the edge. Now, this is great, right? We don't have to handcraft our features anymore, but there's still the feature extraction part, which is learning-based, and the optimization part, which is not learning-based. And the really bad thing about this is that we're actually not learning features in the right domain, right? So the domain in which I'm optimizing is a graph domain, but I'm not really learning the features in this domain. I'm learning the features in a completely separate step. And this means that I essentially cannot backpropagate from my task, which is tracking, all the way back to the image, right? So these two parts, feature extraction and discrete optimization, are completely separate. So this is when we thought, okay, how about we use a learning framework that allows us to learn features in the multiple object tracking domain, which is the graph domain. And of course, we have graph neural networks for this, right? So we thought, okay, how can we leverage graph neural networks for the task of tracking? So essentially, what I'm going to do is, or let's say, all that I need to do in order to work with graph neural networks is define embeddings, right? Define embeddings for my nodes and define embeddings for my edges. And these need to be extracted by a learning method. So for example, node embeddings can be obtained from a tiny CNN that analyzes the detection, that image patch, and puts it, encodes it into a feature embedding that is going to represent the node embedding. And the other thing that we're going to have to define are the edge embeddings, right? So these are typically obtained from having some appearance features, some position features, like for example, relative box position, box size, something like that. Encoding all of this with an MLP and just putting it as an edge embedding. So essentially what we did now is we encoded some appearance features, we encoded some appearance plus geometric features into the edges, and now we can let the graph neural network do the work. So in particular, we use a message passing network to propagate node and edge embeddings over the graph. So you can imagine this as a huge optimization problem in which the node communicates with all the connecting edges, and at the same time, the edges connect with the other connecting nodes. So it's kind of a huge pass of information. Nodes are talking to edges, edges are talking to nodes. And so you can imagine that at some point, me as a node, right, that initially I only saw information from my own detection. Now what I'm seeing is information about all nearby detections, right? Which is amazing for tracking, right? This is exactly what we want to have. We want each node to be aware of what is my appearance, what is my position, and what is the appearance and position of all my neighbors. And this is exactly what a message passing network is going to do for us. So once, so just as a note, the message passing network, the only thing that it does is it updates the node embeddings and the edge embeddings, right? So it teaches the embeddings to be stronger for the task, which is in the end just going to be classification, edge classification, right? So our goal, our loss is going to be edge classification. Is this edge active or is it not active? That's it. That's the only thing. So the whole process is I initialize my embeddings. I update my embeddings through a series of message passing steps so that they become stronger, they become more informed, so that in the end, for the task, which is edge classification, their job is made easier, right? Because they have information about all the neighbors. So essentially what I did after a series of message passing steps and classifying those edges is I obtained the trajectories in my graph. Now this is great, right? Now what I had is a step of feature extraction, learnable data association. So my data association is no longer fixed, which means that theoretically I can do backpropagation from the data association to the feature extraction. So this is awesome, right? Because now I'm going to extract features that are really useful for my task and not features that are extracted in one step and then a completely different optimization in another step. So just some insights that we obtained. So I really like this visualization here. And what we did here is we studied, so in the x-axis, I'm going to plot the number of message passing steps. And in the y-axis, I'm going to plot the MOTA, so the multiple object tracking accuracy, and the IDF1, right? Two metrics for accuracy of tracking. And you can see how this accuracy evolves as we increase the number of message passing steps. And you see here the huge jump that we get from 0 message passing steps to 2 message passing steps. This just means that the nodes have communicated with the edges and the edges have communicated with the nodes. So essentially what you have done is collect higher order information from neighboring nodes. And only by doing this once, you get this huge boost in performance. So this is really what tells you that this collection of higher order information, this passing of information between nodes, it's really, really beneficial for tracking. Okay, good. So I've started the talk about, short-term tracking, long-term tracking, solving really long occlusions. And the question is, can I actually solve long occlusions with the formulation that I've presented right now? And the solution is kind of, right? So when we're talking about long-term association, we can mean something like 20 frames. For example, this could already mean long-term association. And this would mean creating a graph that has a reasonable size. When we're talking about full sequence, 500 frames, 700 frames, 1000 frames, this methodology is completely unfeasible. First of all, because you're going to create a huge graph, right? So memory-wise, this is going to be impossible to keep in memory. But the most important problem is that you're going to have a huge imbalance between active and inactive edges, especially if you start connecting all nodes with all nodes, or even if you use some kind of edge pruning. Even then, you're going to have most of the edges which should be labeled inactive, and just a handful of edges that should be labeled active. And you know what happens with these imbalance problems, right? Learning with these imbalance data sets is actually really, really hard because the active edges almost don't count for the loss. And even if you work with losses that are actually exacerbating the effect of the active edges, this is really, really hard still to learn with this huge imbalance. So what we thought was we went back to the literature and we said, okay, how are people usually solving this? Well, they are creating hybrid multi-level trackers, right? They're sort of putting together a mix of short-term trackers and then obtaining tracklets from this and then putting on top some sort of long-term tracker. And the funny thing is that if you look at the literature, you see that most trackers, for example, most trackers that are submitted to Mod Challenge, they follow this kind of structure, right? They don't specifically write it, but somewhere hidden in implementation details, you see, oh yeah, by the way, we have some re-ID head on top to solve long occlusions, which means that they do have some sort of short-term processing and some sort of long-term processing. And usually these are completely independent and these are engineered for each level from short to long-term, or even short, mid-term, and long-term. So that's a lot of engineering that, of course, doesn't translate when you go to other data sets. So what we thought is, could we actually extend our graph tracker to work across different levels? So to deal with short-term tracking, collect some tracklets, and then from those tracklets, keep building longer and longer and longer trajectories in different hierarchical levels. Now, of course, we have several challenges, right? The first challenge is that the features used for short-term tracking and the features used for long-term tracking are not the same, right? So intuitively, you can think short-term tracking is more about the position, right? The position of the object doesn't change much. So the position is a huge information. For long-term tracking, it's a different story, right? If the object has been occluded for 10 seconds, it could be pretty much anywhere. So we tend to rely a lot on appearance. We tend to rely on re-identification. So the question is, could we have a unified tracker across different levels that learns to choose which features are going to be used, which features are going to be best for each level of the tracking pipeline? And so this is basically what we present at this CVPR. I'm just going to talk about it briefly, but if you want to know more details, we do have a poster at the main conference. So please feel free to go there and ask any tough questions to Orchun and Ghislaine, who are both going to be there. And so SUSHI is our tracker, and it stands for the name Strong, Unified, Scalable, and Hierarchical Multi-Object Tracker. And the key features of the tracker is that for the first time, we can process long clids of 512 frames. And for the first time, we can actually solve occlusions of up to 512 frames. And you might think, well, are there many long occlusions in Mod Challenge that are this long? So as you will see in the results, this has a huge impact on IDF1, on identity preservation. So there are long occlusions even in Mod Challenge. Now, the other key feature is that we're going to have the same graph neural network architecture and weights for all the levels of the hierarchy. So whether it's short-term tracking or long-term tracking, we're going to use exactly the same tracker. And for each level, the tracker will know which features to use, more appearance, more position, depending on which level is it at. And also the cool thing is that while I love Mod Challenge, of course, there are also other data sets, other multiple object tracking data sets out there, right? And there are many papers that are showing that trackers don't really generalize across data sets. And we show for the first time that our tracker can actually generalize to 4 diverse data sets and obtain state-of-the-art by quite a large margin. So essentially, our tracker consists of different sushi blocks, and each sushi block is essentially a graph neural network, so the tracker that I've explained before, that works at different hierarchies, right? So you can imagine the first hierarchy, which takes only 5 frames, and obtains tracklets up to 5 frames long, right? The second sushi block, though, it takes those tracklets, and now one node is going to represent a tracklet and not a detection. And it tries to build longer tracklets, let's say 25 frames. And you keep going 5 frames, 25 frames, 75, all the way to 500 frames. And the idea is always the same, right? You have your message passing network, your graph neural network that propagates nodes and edge embeddings. And the goal is to classify edges as active or not active. Now, another cool thing is that we can do weight sharing, right? So this is extremely efficient because each sushi block shares weights. And so you don't really need to have a huge model that has 4 times the number of weights, right? You can have the same number of weights and still be much more efficient by just using this tracker in a hierarchical way. And so this is another view of the pipeline, right? Where you get your detections at the top. You apply a sushi block for a small scale at first, let's say 5 frames. You find trajectories within those 5 frames. And then you have the sushi block that takes all the outputs from these tiny sushi blocks at the top and tries to obtain longer trajectories, right? So it's the old idea of saying, going from detection to tracklets, to longer tracklets, to trajectories, but in a scalable way, in a way where we don't need to have a huge model and we don't need to have engineering per level. Now, these are some ablation studies that I really like, right? Because this shows really the potential of this hierarchy. So what we've plotted here is different hierarchy levels that we tried from 1 all the way to 9. And then working with different clip sizes. And by clip size here, I mean that if I have a clip size of 8, basically I can only fill up to, so I can only correct for occlusions up to 8 frames. While if I have clip sizes of 512, theoretically, if there's a detection in the first frame and a detection in the frame 512, I could actually connect these 2 detections, and I could resolve an occlusion that is 511 frames long. Now, what happens when I have only one hierarchy level? Well, basically, first of all, memory-wise, I cannot really deal with clip sizes of 512. But even when I increase the clip size, the accuracy is not really increasing, right? So it's, as I said before, the imbalance problem makes it really, really hard to learn with these large clip sizes. And you can see here how things change by just using 3 hierarchy levels, right? So first of all, the accuracy goes up almost by 10 points in IDF1 when I go from clip size 8 to clip size 512. And same thing happens when I increase the hierarchy levels, right? So I see a consistent update, a consistent increase in performance as I use more and more hierarchy levels. Now, here are some qualitative results per level. So we start from the top left, where we have level 1. These are just tracklets of 5 frames. And indeed, you see this flickering of the identities because every time, so we obtain tracklets from frame 1 to 5, from frame 6 to 7, 6 to 10, sorry. And so every 5 frames, the color of the track is going to change. We start seeing more consistent results with level 3, even more with level 6 and our final results, which is with 9 hierarchy levels in which we have really nice and long consistent tracks. And as I've said, we do generalize to 4 datasets. We work with Mod Challenge, with Dense Track, with BDD, which is actually for vehicle tracking, and with Mod 20. And for all of these, we obtain a really huge performance boost, especially when we're looking at identity preservation, right? We have not really worked with detection, which is why we're not too interested in MOTA, though we are also state-of-the-art there. But I think here, the real increase is in identity preservation, right? So it's almost 10 points for some of the datasets, which is a really huge increase. Okay, so to conclude my talk, I hope that I've convinced you that graph neural networks are really, really robust trackers. They're actually capable of adapting to short and long-term association challenges. And one thing which you might not like is that the tracker that I've presented and the results that I presented is actually for an offline tracker, which means that you do have access to the whole sequence and you do obtain trajectories for the whole sequence. So if you're interested in having an online tracker, this is not directly applicable. Luckily, though, we do have a way to convert this graph tracker into an online tracker, which we presented in this work, Polar Mod. And this work is also about 3D tracking. So it's also about how can you use graph neural networks to perform tracking in 3D using only LiDAR sensors. So if you're interested in making your tracker online or in working in 3D, also please go ahead and check this work. And with this, I would like to thank you for your attention, and I hope I can answer as many questions as possible. Thank you.
Thank you, Professor. We are very excited. You know, we have. I hope you can see this room. We have a whole room of guests, and they are very excited by your work. And now we can open the space for some questions that you might have. If you have questions, you can come up on the stage, or if there's anyone have questions, you can on Zoom. You can also ask question on Zoom. I can start with the question. You know that in NVIDIA, we collaborate a lot between the products and research. And you might be surprised to find out that at NVIDIA, we care a lot about performance in terms of runtime performance, in terms of the time needed to run, and also the memory utilized in the algorithm. So could you share a little bit about your findings and you know, to deploy in real world, like what kind of resources is needed for this sushi method and other tracker that you mentioned?
So if we were to make sushi online, I think at every step you can actually run your method in real time, right? So I don't want to tell a lie, but I remember something like 20 frames per second, maybe. Don't take it too literally because this is just out of memory now. But of course, here solving the tracking problem is just making a forward pass in the graph, right? So it's actually really, really efficient. I mean, in the end, you just have like tiny MLPs and you have to do several message passing steps, but these are very fast, which means that you do obtain a solution very quickly, right? It's not like the old methods that I presented at the beginning where you have an actual optimization step where it's actually really expensive. So you could deploy your method to be real time. Of course, it does take a little bit of memory. In terms of the big model, it's completely unfeasible if you want to deal with long occlusions. The hierarchical one, of course, it's much more efficient, right? You still need a proper GPU to run it, but nothing super fancy. I think we did a lot of experiments with 24 gigabyte GPUs and things were working smoothly. It's still not at the level maybe of running, of course, on a mobile phone, but I think one could work up to that.
Thank you for the answer. And yeah, we hope that, you know, when the performance and accuracy is at the state-of-the-art level, we can apply it to more products, and we can apply it in the real world and to apply it in the industries. Any other questions you might have? Oh, there's a question in the chat. I'm not sure if you can see it. It says,
oh, yeah.
Yep. So I can read the questions first. This guest said he or she has a question for a data set that misses a strong object representation. For example, thermal imagery. How can we adapt the sushi method?
That's an excellent question, right? So the only thing that you're going to have missing here is sort of the CNN that takes in the appearance information. But all the rest of information you can use, right? You can use position information, relative size information. And for this, I would recommend actually to go to the Polar Mod paper, because there we don't use any appearance, because we want to generalize across sensors, we want to generalize across locations. And so it's really important to work only with the LiDAR sensor. And so I can imagine that it is more similar to thermal imagery, where basically you cannot really rely on appearance. And so you have to rely on all the other cues, which are mostly geometric cues. Now, the cool thing is that the graph method is so robust, right? Because it makes all the decisions, all the data association decisions at once for all the detections. And this is so robust that I think it's going to be enough if you use only geometric information. I really think that not having an appearance is actually not a huge problem. And this is essentially what we showed in the Polar Mod paper.
Thank you. Any other questions from the guests? I can have asked another question. So at NVIDIA, you know, and also at the AICP challenge, we have this track of multi-camera people tracking. So I see that the sushi method is mainly utilized for a single camera tracking. So could you like explain like how we can extend this kind of methods to multi-camera tracking?
Yeah. So we did some work back in 2012, I think, which was about multi-camera tracking with graphs. And so essentially you can do something very simple, right? You can take the exact same formulation and translate it into a graph neural network, right? So the only thing that changes is the graph connectivity. Now you need to express connections across detections, connections between detections across cameras. And so that you also have this flow of information during your message passes between cameras, right? And then you need to have some constraints also about how the decisions are going to be made so that you don't have double decisions, for example. But this is something that you can borrow from that classic formulation, the 2012 paper. And then what you can do is essentially you can create a much faster solver, because the problem with that paper was that the solver took days, and I'm not joking, days to obtain a solution for one sequence. But now you can obtain a solution almost instantly by just having a forward pass in your graph neural network, right? So it's actually really easy to extend its method to multi-cameras.
Thank you. We can have room for one more question. The guest. Oh, please come ahead to the microphone. Thank you.
Hello, thanks for your very nice presentation. Sorry, I might have missed it, and you might have mentioned it. I was wondering whether the time frame of the tracklets are predefined, or can those be variable based on the events of, like, for example, an occlusion?
So we predefine the hierarchy levels, right? So we have something like 525, 75, 150, et cetera, but this is actually not a problem. If the events happen slower or faster, the only thing that's going to happen is that the lower levels of the hierarchy are going to work more, are going to have a harder time making the association, or the higher levels are going to have a harder time, right? So this is not really a problem, but we did do some experiments on different types of hierarchy levels, having a really big hierarchy level at the beginning, like, for example, starting with 50 instead of 5. And this is actually much heavier and much worse for performance. So we decided to do something that is slower, that increases the number of frames that we process at each level in a slower way. And this turns out to be the best for performance. And I'm pretty sure that it generalizes to a lot of events, as we showed, since we generalized to data sets that actually have, for example, fast moving objects like cars, or people that actually move a lot, like, for example, in dense track, people move suddenly from one place to the other. And these were handled really well with the exact same graph hierarchy across the 4 data sets.
The question get answered? Okay, thank you. So let's thank Professor Laura Liu-Taxi again for the great presentation.
Thank you for the invitation.
Thank you all. Now let's take a break of 10 minutes. Now it is 9:22 a.m. and we can come back at 9:32 a.m. Can have some coffee outside. We know that it's the audio system might be a little challenging for you guys, so we will try to fix it when you are back. And we will have the presentations of track 1, track 2, and track 3 before lunch. And in the afternoon, we'll hear all the presentations of track 4 and track 5 and all the independent researchers. Thank you again, and let's come back in 10 minutes. Thank you all. So we are trying to resolve some audio output issue in the meeting room. So we will get started in a while. Thank you for the wait. Okay, thank you for the wait. Yep. So we will continue. So now let's have time for the presentation of track 1. So we have 7 participants in this track. We will have 2 teams that will present for 10 minutes, and the rest of the teams will present for 5 minutes each. And we will have a 10-minute Q&A session after this track 1 presentation. So now let me share my screen for the track 1 presentations. So you can see the screen. Sorry, let me make sure that we have the sound going to Zoom. Can you hear on Zoom? Is there anyone in the room? Maybe you can type. No sound. Can you still hear? No sound still. Can hear mic but not recording. Okay. Yeah. So currently, let me see. Is there a way to share the sound? Oh, you can hear me. Okay. I will try to keep the mic very close to the speaker so you can hear from there. And we will try to resolve improve the sound. If just let us know if there's an issue hearing the audio. Thanks. We will replay the video.
Hi everyone, today I am representing the Information Processing Lab from the University of Washington. And I will present our paper, Enhancing Multi-Camera People Tracking with Anchor-Guided Clustering and Special Temporal Consistency ID Reassignment. Our members include Shanwei Huang, Chenyan Yang, Zhongyu Jiang, Pyeongkuen Kim, Kyunggo Lee, Kwangju Kim, Samarth Ramkumar, Chaitanya Mulapudi, Insu Zhang, Changyi Huang, and our advisor Zhenming Huang. Multi-camera people tracking plays a crucial role in several applications including surveillance or business analytics. For example, retail industry can improve the shopping experience by analyzing customer behavior with the multi-camera tracking technique to track each customer's location and to further analyze their behavior and shopping preferences. In the 2023 AI City Challenge Track 1 multi-camera people tracking, participants are required to detect, track and assign a unique global ID to all the people in multiple cameras in several diverse scenarios, including one real environment and 6 synthetic environments with a total of 43 cameras. The team that could achieve the highest tracking accuracy across multiple cameras will be declared the winner. The testing dataset includes synthetic and real-world environment. The synthetic environment includes several different scenarios like supermarket, office, hospital, warehouse, or store. Each of the video is 10 minutes long. The real-world environment is a scenario with real people moving in a warehouse. The total video length of the real-world environment is 30 minutes. Now, I will introduce our overall pipeline. Our pipeline contains 3 main parts, including the single camera tracking module, the anchor-guided clustering module, and the spatiotemporal consistency ID reassignment module. For the single camera tracking module, we deploy BOTsort as our tracking algorithm, YOLO 7 as our detector and OSNet as our re-ID feature extractor. We follow the original association method of BOTsort, except we remove the camera motion compensation part since the camera is stable in the provided dataset. BOTsort follows the classic tracking by detection paradigm and utilizes Kalman filter and appearance features for multi-object online tracking. After applying BOTsort, we can obtain some preliminary tracking result. As you can see in the tracking result, BOTsort, which is originally used to tackle the MOT dataset, does not have the re-ID processing method that can handle more complicated situation when a person reappear after a certain amount of time. Therefore, false ID assignment can happen and the same person can have different tracking ID when re-enter the camera field of view. Here, three main challenges in the multi-camera people tracking task needs to be solved. The first one is the need for re-identification method. A person can disappear in the camera for a certain amount of time, but when the person comes back, the system needs to re-identify the person. The second challenge is the ID switch during single camera tracking. The single camera tracking cannot always be perfect and ID switch might happen when there is occlusion in the tracking process. For example, in the video, the person with ID 6 and ID 19 switch their tracking ID. And the last challenge is the unaligned tracking ID between different camera, which means after the single camera tracking is performed on each camera, the resulted tracking ID will not be aligned since we do not conduct information exchange between different cameras, therefore the tracking ID is only aligned within each single camera. So is there a way to tackle these three challenges all at once? Now, I will introduce our second module, named Anchor-Guided Clustering, which is a simple and effective module that can deal with the three challenges all at once. This is the overall pipeline of our Anchor-Guided Clustering module. After we obtained all the detections and the appearance features from all the cameras in the same scenario, we conduct sampling across all the appearance features from each camera. And then we perform hierarchical clustering to obtain anchors for each person in the scenarios. Each anchor include a feature bank with several features representing the person. The feature includes the person's feature from different size, rotation angle, and lighting condition. And then we back-check the single camera tracking trajectories, and for each detections in the single camera trajectories, we conduct Hungarian assignment for all the detections in the same frame to the anchors according to the similarity in appearance. So now each detection in the single camera trajectories is assigned with a global ID, given by their distance to each anchor. And then, to further refine the results and remove the outlier, a sliding window majority vote is conducted on each trajectory to produce a more robust global tracking ID for each trajectory. This method successfully remove the ID switch, conduct re-identification, and also assign global ID to all the trajectories in the same scenario. So far, with the anchor-guided clustering, we achieve around 92 IDF1 on the testing set. However, due to several challenges in the real-world environment like extreme similar appearance and more severe occlusion, anchor-guided clustering fails to perform well on the real-world scenario. Now, I will introduce our third module, named Spatiotemporal Consistency ID Reassignment, which effectively fixed the false ID assignment in the real-world multi-camera people tracking process. The approach has several steps, including a pose estimator that can generate the foot coordinates, camera self-calibration that can transform 2D coordinate in each camera into 3D global coordinate on the top-down view map. And finally, a iterative ID reassignment method is conducted to further refine and fix the incorrect tracking result based on spatial and temporal information. Camera self-calibration is labeled to help us obtain the global coordinate from the 2D image. As you can see in the image, on the top is the visualization of the estimated ground plane for different camera views. In the bottom is the field of view for different cameras projected on the top-down map. After obtain the global coordinate on the top-down map, we can then fix and reassign the tracking ID based on spatial and temporal information. In each frame, every tracking ID should produce several top-down coordinates. We further calculate the average position of these points. Remove the outlier, reassign it with the correct tracking ID, and then conduct another round of reassignment iteratively, and finally we can fix the wrong ID assignment in certain camera, and utilize global information to produce better tracking results. Finally, with our baseline method, we achieve 89.5 IDF1 on the track 1 test set. After that, we further fine-tune the detector for each scenario. This improves our performance by more than 3%, to around 92.9 IDF1. And then a single round spatial temporal consistency reassignment push our performance to 93.6. And finally, the iterative version of spatial temporal consistency reassignment leads to a final performance of 95.3 in IDF1, ranking first place among all the participants on the leaderboard. And here is some demo for our multi-camera people tracking system. Our method successfully tackled down the challenges in multi-camera people tracking, and achieve decent performance in both synthetic environment and real-world environment. And finally, we want to acknowledge Taiwan's Nation Center for High-Performance Computing for providing the computational resource. And we also want to acknowledge the help from the researchers from Korea's Electronics and Telecommunications Research Institute. And that is all for our presentation. Thank you.
Hello everyone, and thank you for joining us today. My name is Lei Hui, and on behalf of my team from International University, Vietnam National University, Ho Chi Minh City, it is my pleasure to present to you our work on the multi-camera people tracking challenge, that name multi-camera people tracking with a mixture of realistic and synthetic knowledge, which has achieved second place in the highly competitive Track 1 AI City Challenge. In Track 1, our primary objective is to track individuals in indoor environment across multiple cameras and ultimately assign a unique and consistent ID for each person. For example, in this figure, we need to track a man wearing a white shirt as he stands through the field of view of 4 different cameras and consistently match his ID across all cameras. The challenge in this track is complex movement. People exhibit nonlinear motion, such as walking straight, stopping suddenly, or making abrupt turns. Next, ID switching. This issue contain occur when a single tracker contains more than one ID. Next is reassigning person ID in single camera. Sometimes individual may leave the camera field of view and then return. Our goal is to correctly reassign the original ID when they reappear. Another problem is matching person ID in multi-camera. We must ensure that each person is assigned a unique and consistent ID as they move between different camera views. Now, let's move on to our method. In this figure, we introduced a proposed multi-camera people tracking framework. The process consists of the following steps. Boson detection. We detect individual and obtain the bounding box in each camera view. Next is feature extraction. We extract a feature vector for each bounding box to represent the person. Tracking. We combine the bounding box and feature vector as input for our tracker. Next is single camera matching. The tracklets are passed to the single camera matching module, which assign ID to each tracklet within one camera view. The output of this module is cluster, with each cluster representing a unique ID. Multi-camera matching. We use the multi-camera matching module to assign a consistent ID for each cluster across multiple cameras. And finally, ID switching refinement. We apply an ID switching step to refine the result and further improve the accuracy. For person detection, our experiments have shown that YOLO V5 is the best model in terms of both efficiency and effectiveness when detecting individuals in both synthetic and real data. So during the training phase, we fine-tune our model for just one epoch for the training set to achieve optimal performance. In inference phase, we apply the fine-tune to the synthetic scenes and obtain satisfactory result. However, when we attempt to use the fine-tuned model on a real-life scenario, the performance was not satisfactory. Consequently, we decided to use the pre-trained YOLO V5 X6 model to achieve better result in detecting individuals in a real-life scenario. For feature extraction and re-ID, we employ two model architecture, JANS-ready and HRNet. For training, we train both model on our training data, using pre-trained model on the ImageNet. For inference, we use the feature we adopt from different strategy during the feature extraction step for synthetic and real-life scenario. In the synthetic scenes, we use the JANS-ready model to extract person feature for those scenario. in real-life scenes. In this case, we employ an ensemble approach, combining features from free model, Trace Reality, HRNet, and Trace Reality with additional modules. For the tracking model, we adopt the tracking method from the Top 1 AICD Challenge first play in the 6th AICD Challenge, named Box Crane Re-ranking Matching for multi-camera multi-target tracking. To detect ID switch in tracklet, we have utilized a Gaussian mixture model with two components to model the feature of each frame within a tracklet. Since different IDs typically have different means value, a significant difference in the mean of two consecutive Gaussian likely indicate an ID switch. We calculate of the cosine distance between the means of these two Gaussian. If this distance exceeds a threshold value of 0.4, we consider that an ID switch has been detected. Once an ID switch is detected, we need to determine the exact split point to separate the tracklet into two parts. We do this by finding the longest subarray of data that belongs to either of the two Gaussian. The start index of the longest subarray is then taken as the split position. If the first Gaussian start index is larger, we split at the point. Otherwise, we split at the second Gaussian start index. This method utilizes Gaussian mixed model and a mean distance check to detect potential ID switch, and then find the optimal split position based on the longest consistent subarray for either ID. And next, our approach to single camera matching consists of the following steps. First, filter unreliable tracklets. Identify separate unreliable tracklets which have incomplete or inaccurate feature information from the reliable ones. Next is apply cluster on the reliable tracklet. Perform a clustering algorithm on the reliable tracklet to create anchor cluster which represent accurate and consistent individual ID. And finally, assign unreliable tracklet to closest anchors. Determine the closest anchor cluster for each unreliable tracklet based on the cosine distance between features, and assign the tracklet to that cluster. In synthetic scenario, we identify unreliable tracklet as those with shorter duration, measure in frames. To generate feature for each tracklet, we utilize the Trace Reality model. Next, we apply agglomerative cluster to create anchor cluster from the more reliable tracklets in order to achieve the best result. In real-life scenario, cluster is not only affected by the presence of shortest tracklet but also by interclass similarity. This interclass similarity issue is because our model was trained solely on synthetic data, which limits its ability to generalize well to real-world scenario. To address the problem, we propose a heuristic algorithm called realistic matching, which replaces traditional clustering method. The realistic matching method, or matching algorithm, takes a different approach to finding anchor cluster. Instead of removing unreliable tracklet and applying a clustering algorithm on the remaining tracklet, we directly identify anchor cluster. First, we find a valid cluster. We determine the valid cluster that the current tracklet can join. A valid cluster is one where the current tracklet does not intersect with any tracklet within the cluster. The current tracklet will then join on the closest valid cluster. Second, we will check the distance threshold by verifying that the distance between the current tracklet and its two closest valid cluster is greater than a predefined threshold. If this condition is met, the current tracklet will join the closest cluster. This condition helps us overcome the interclass similarity that affects cluster formation. If a tracklet does not satisfy both conditions, it is deemed to unreliable. Finally, all the unreliable tracklets are assigned to their closest and anchor cluster, resulting in a more accurate and robust matching process in real-life scene. In the multi-camera matching step, our objective is to accurately access the cluster from different cameras to identify the same person. To achieve this, we compute the cluster feature of each camera by taking mean of the feature from all tracklets within the cluster. Depending on the type of scene, we can adopt one of the two approaches for multi-camera matching, synthetic scene or real-life scene. For synthetic scene, we can apply agglomerative clustering to create a cluster, where each cluster represents a single person ID across multiple cameras. We observe that each cluster generated from the single camera matching step have minimal noise. The cluster in the multi-camera matching step will ensure that no cluster contains two persons from the same camera. Finally, our framework obtained an IDF1 score of 94.17%, which has achieved the second place on both test sets. Thank you for your attention. This simply brings the end of our presentation. If you have any question, please leave at the end of the answer.
Hello everyone, today I'm very glad to introduce our work, integrating appearance and spatial temporal information for multi-camera people tracking. Multi-camera people tracking is a crucial task in intelligent surveillance, which aims to accurately locate and track individuals across multiple cameras. However, we observe the following problems that need to be addressed in this challenging task. First, most MOT-based methods can hardly handle heavily occluded human bodies, which often leads to frequent ID switches. Second, it is difficult to distinguish people with similar appearance via real ID features, since they are likely to be assigned with the same identity, which we refer as ID antinomy. Finally, existing tracking by detection methods rely heavily on detection quality, while false positive detection results may appear in complex scenes. Faced with these problems, we designed a MCPT system leveraging spatial temporal and appearance information. Specifically, we specially designed a MOT method which could minimize the ID switch errors and obtain more accurate appearance features. Besides, we developed an intra-camera association approach, which leverages both appearance information and multiple sources of spatial temporal information in one single step. In addition, we proposed a post-process module, which contains multi-step post-processing to eliminate ID antinomy and false positive detections, as well as compensate missing trajectories. And we will present our method in detail. In our MOT module, we will adopt a two-step matching strategy. The first step is to match the tracked trajectories with current detections based on IOU. Second, we match the untracked trajectories with the unmatched detections after the first step. And we apply an adaptive MIOU threshold according to the lost time of trajectory. Finally, we will initiate new trajectories for high-confidence unmatched detections. Besides, we also design an algorithm to calculate a confidence-aware trajectory appearance, where only the real ID feature of high-confidence detections will be considered. Based on the trajectories and their appearance, we dynamically maintain a temporal overlap matrix during tracking, where a strict positive value means existence of temporal overlap. When such trajectory is matched more than once in a single frame, the real ID similarities between its matched detections and its overlapping trajectories are compared. The detections with real ID similarity inferior to the maximum value will be considered as wrongly matched and will be assigned to a new trajectory. After MOT, single camera trajectories are acquired and need to be associated across multiple views. We leverage appearance information and multiple sources of spatial temporal information, and we formulate them in the form of distance matrices. The appearance distance matrix measures appearance dissimilarity among all tracklets, and the proposed homograph distance is a normalized distance between detected bounding box and the box transformed by homograph from other cameras. The ID antinomy term is proportional to the length of temporal overlap. And finally, the speed constraint term penalizes trajectories with abnormal speed. The distance matrices are integrated using an adaptive weight matrix that form a final association matrix. We perform a hierarchical clustering to associate all trajectories in one single step. As for post-process, we first remove all ID antinomies and compensate missing trajectories from existing trajectory in other camera views via homograph transform. We also conduct ablation studies on AIC23 MCMT tracking testset. We can observe that significant improvements are achieved With our proposed MOT, spatial temporal distance matrix, and post-process module, compared to the baseline with ByteTrack. Finally, we achieved an IDF1 score of 93.31% and ranked third among more than 40 teams. Thanks for your attention.
Hi everyone, in this video I will present our paper titled ReID Track, ReID Only Multi-Target Multi-Camera Tracking. This paper showcases our approach for this year's AICTE Challenge Track 1. Multi-target multi-camera tracking involves tracking objects, specifically persons in our case, across multiple camera views, even when the views do not overlap. This tracking technology has diverse applications, including optimizing product placement and customer navigation in retail stores by tracking customers' routes in the stores. Additionally, it's valuable in manufacturing and warehouses to improve work processes and minimize workers' travel distances. Our motivation for developing a ReID-only approach stems from the significance of visual appearance features in empty MCT systems. Visual person re-identification is crucial for connecting tracklets before and after occlusions and linking person tracks across non-overlapping camera views. Besides, if person re-identification is executed perfectly, it directly solves the tracking task without the need for motion prediction or scene models. Therefore, our research question was focused on comparing the performance of a ReID-only system to more complex MT-MCT systems. The figures at the bottom illustrate some of the toughest challenges faced when developing ReID-only multi-camera tracking, including overlapping bounding boxes, occlusions, and partly visible persons. Overlapping bounding boxes of persons may include misleading information and lead to identity switches. Occlusions by objects and partly visible persons are challenging since the ReID model needs to be able to learn robust features that allow the matching of heads and full body images. Our single camera tracking approach utilizes the YOLO V8 single stage detector with a 640 pixels input resolution due to its favorable trade-off between speed and accuracy. We employ COCO pre-trained and fine-tuned models for real-world and simulated data. ReID features are extracted using the AGW approach, and we enhance the robustness against the aforementioned challenges by applying data augmentation techniques. The figure provides an overview of the single camera tracking procedure we follow. Initially, all persons visible in the video frames are detected. To prevent identity switches caused by misleading information from multiple persons, bounding boxes containing multiple persons are excluded. Non-overlapping detections are forwarded to an IOU tracking stage. It is not necessary since it does not influence the tracking performance, but it reduces the memory footprint of the subsequent clustering stage. Next, ReID features of detections are clustered in multiple rounds with varying conditions to obtain single camera tracks. Finally, overlapping detections are matched to cluster tracks by closing gaps in tracks and assigning them to the visually most similar track. The results presented here are based on a validation split of the challenge dataset. We found that fine-tuning the detector on the challenge dataset had the most significant impact on performance. Multiple rounds of clustering proved beneficial, improving both identity precision and identity recall. Our mechanism for handling overlapping detections greatly improved recall by closing gaps in tracks. However, precision was better without this handling. Cross-camera association of single-camera tracks also relies on clustering ReID features, followed by interpolation to close still existing gaps in tracks and track filtering to exclude short tracks. However, interpolation and track filtering had minimal impact on the final performance. Moving on, we measured the processing times of our ReID framework to demonstrate its efficiency. We conducted experiments using one scenario from the challenge dataset consisting of 5 videos, each with a duration of 10 minutes. Sequential processing, where cameras are processed one after the other, took 36 minutes to process 50 minutes of video data. When multiple GPUs are leveraged and detection, ReID feature extraction, and IOU tracking are performed in parallel, only 7.5 minutes were required to process all the data. The majority of the processing time was attributed to detection and feature extraction, which collectively account for 98% of the total time. These results demonstrate the real-time capability of ReID Track. Since the clustering cannot be done online, there is a delay until the multi-camera tracking results are available. However, this latency is just 11 seconds. In our work, we present the fast and efficient ReID track framework. A crucial component that enables robust ReID-only tracking is our handling of overlapping detections. To address our research question, we can conclude that our ReID-only tracking system achieves competitive results with more complex MTMCT approaches. As evidence, we achieved rank 4 in track 1 of the AI City Challenge.
Hello everyone, I am Lizoni, and today I am excited to present our paper titled Hierarchical Clustering and Refinement for Generalized Multi-Camera Person Tracking, which is submitted for the CVPR 2023 AI City Track 1 competition. In this competition, our goal was to track people across multiple cameras using a combination of real and synthetic data. However, the indoor setting, along with the variations in viewpoints, illumination, and image resolution, posed several challenges to the existing tracking methods. Traditional tracklets were not robust enough in such scenarios, especially when dealing with appearances and disappearances of the same identity within the same camera. To address these challenges, we proposed a hierarchical clustering and refinement approach for both inter-camera clustering and intra-camera tracking. Additionally, we leveraged face representations as an effective biometric clue to refine the clustering results. Our proposed method is illustrated in this figure. The hierarchical clustering method performs intra-camera clustering and inter-camera clustering separately to associate identities across different cameras. This allows us to handle the variations caused by different environmental conditions. Furthermore, we introduced hierarchical refinement, which consists of tracklet-level refinement and cluster-level refinement. The tracklet-level refinement filters out low-quality frames to improve the accuracy of tracklet features, while the cluster-level refinement enhances the clustering results by incorporating face representations as an additional biometric clue. For the person re-identification (ReID) model, we use trans-ReID SSL with the C-loss and triplet loss to ensure robustness and discriminative power. To tackle the issue of ID switching caused by crowded situations, we employed the k-means algorithm to split tracklets into two separate tracklets if the intravariance exceeded a certain threshold. Additionally, we utilized Discan to associate tracklets within a single camera. The fusion distance matrix was constructed using appearance distance, JACA distance, and spatial temporal distance. After the inter-camera clustering, we performed appearance refinement by recalculating the distance between each tracklet and the center of the cluster. This allowed us to reassign the identity of each tracklet to its nearest cluster. In the spatio-temporal refinement step, we reassigned tracklets with camera time overlap to different clusters. For conflicting pairs within the same cluster, only the tracklet closest to the cluster center was retained, while other conflicting tracklets were assigned to different clusters based on their similarity. Furthermore, we employed face refinement techniques. If the face feature of a tracklet significantly differed from the assigned cluster's ReID features, we considered it as a misclustered tracklet. When the face similarity between the tracklet and its nearest face cluster exceeded 0.8, we reassigned the ID of the tracklet to the nearest face cluster. We conducted an ablation study to evaluate the effectiveness of our proposed methods. It is impressive that the hierarchical clustering, intra-camera cluster, together with inter-camera cluster in tab 1, promotes the performance by a large margin. Moreover, different refinement strategies are able to boost performance. Specifically, appearance, spatial temporal, and tracklet level refinement promote the performance by 2%, 1%, and 2%, respectively. The results demonstrated the superiority of our approach in multi-camera tracklet association. In fact, our method achieved an impressive score of 0.92 in this track, securing the 5th place ranking. In conclusion, our hierarchical clustering and refinement approach, along with the incorporation of face representations, proved to be highly effective for generalized multi-camera person tracking. Our method successfully addressed the challenges posed by varying viewpoints, illumination, and image resolution, resulting in accurate and robust tracking results. Thank you for your attention.
Hello, we are from NODA, and we will be presenting our solutions to 2023 AI City Challenge Track 1. The task involves detecting and tracking people captured by multiple cameras simultaneously. In this task, we specifically address the challenge of body part occlusion, which leads to significant changes in a person's appearance and makes it difficult to accurately locate them on the 2D map of a given area. The figure above presents the overall pipeline of our implemented multi-camera people tracking system, referred to as MCPT. The system consists of 3 main modules, and the input image sequentially passes through these modules. The 3 modules are People Detection, which detects people, SCPT, which tracks people on each camera, and ICA, which matches the same people across multiple cameras. All of these processes are conducted in online manner. The models used in each module can be found within the figure. Now, we will give details for ICA in the next few slides. The figure above provides illustration of the pipeline within the ICA module, which is our main part to improve the performance of MCPT. Firstly, we perform a projective transformation on all the people detected by each camera to project them onto a 2D map, as seen in the top left corner. Next, we utilize clustering algorithm among the detected people from each camera, based on appearance features obtained via the re-identification model and individuals' coordinates on the 2D map. Subsequently, we match the clusters tracked up to the previous frame with the aforementioned clusters. Ultimately, each person within a cluster is assigned the cluster's ID as a global ID. In 3 of the aforementioned processes, namely projective transformation, clustering, and cluster tracking, we encountered the issue of occlusion in the human body. In the following slides, I will explain how we addressed and solved this problem using human pose estimation. The first method we employed to address occlusion is key points-aware projective transformation. We projected the coordinates of the person's bounding box detected in the camera, specifically the bottom center, namely feet, onto a 2D map. However, as shown person 67 in the left image, if a portion of the human body is occluded, the projected coordinates on the 2D map significantly deviate from the actual position. To tackle this issue, we utilize a pose estimation model to identify the missing key points, interpolate them, and estimate the actual coordinates of the feet, as shown in the right image. We then project the interpolated coordinates onto the 2D map. We then conduct key points-aware clustering to match the individual person. Thus, we define similarity between 2 individuals. The similarity between 2 individuals is determined by the weighted sum of the Euclidean distance between their locations on the 2D map and the cosine similarity of their appearance features. This similarity score is used for clustering people detected by each camera. However, when a part of the body is occluded, it can lead to significant differences in appearance features between identical individuals from different cameras. In such cases, the weight value of cosine similarity, lambda, is reduced to less than 0.5. When no key points of the 2 individuals are occluded, lambda is set to 0.5. As shown in the example above, the weight of cosine similarity is relatively reduced when only a few key points overlap between the 2 individuals. The third method is key points-aware cluster tracking. Each cluster maintains a predefined number of appearance features and utilizes them for matching between clusters. However, storing appearance features of a person with occluded body parts can negatively impact the matching performance. Therefore, we discard the appearance features of individuals when associated key points are insufficient. We evaluated the performance improvement of applying the above 3 methods on the validation set. We observed a slight improvement when applying the method to projective transformation, while the significant improvement was achieved when applying it to clustering. Additionally, some performance improvements were also observed when applying it to cluster tracking. Other ways to improve the performance of the MCPT, we employed gamma correction to enhance image brightness, allowing better detection of people in dark areas. And when extracting appearance features, we employed an ensemble technique that averaged the normalized output appearance features from 3 re-identification models. Through the aforementioned methods, we achieved an IDF-1 score of 86.76 on the test set, securing a position in the top 10 of the iCity Challenge Track 1. If you have any questions, we would be glad to address them.
Hello, my name is Yoon Tae-jeon, MS course at Global Smart City in Sungkyunkwan University, South Korea. Today, I'll present our paper leveraging future trajectory prediction for multi-camera people tracking in CVPR 2023 AICT Challenge. This is the order of presentation. We participated in Track 1 in AICT Challenge. Track 1's primary objective is to improve multi-camera multi-target tracking systems which aim to simultaneously identify and track multiple objects across various camera views. One issue arises when we use camera filter-based methods like ID switching programs. We also face difficulties when employing re-identification or re-ID based methods. In single camera or intra-camera, re-ID works well, but in multi-camera or inter-camera, we face two appearance-related challenges. One is the confusing similarity of different objects across cameras, and another one is the variation of same object's appearance within the multiple camera views. Furthermore, because of the computation cost of re-ID-based methods are not proper for real-time application. To solve these challenges, we suggest trajectory prediction-based multi-camera people tracking system. By using deep learning-based trajectory prediction model, we can leverage the motion information of objects. Moreover, by replacing the re-ID model, our method can learn on real-time in real-world application. Let me introduce our proposed pipeline. First, execute single camera tracking for each camera view. For each view, detect the bounding box and key point for figure out the location of objects. And then do trajectory prediction using spatiotemporal and social information. After that, based on the IOU distance, we can track the objects using Hungarian methods. Then, in multi-camera perspective, we can project the track rest from multiple views, and finally associate the projected track rest based on the only motion features. These slides are detail of trajectory prediction. The architecture of model is composed to CNN layers for a single object and multiple objects. This is the detail of our tracking systems. First, we detect the location of objects. Second, we can calculate the IOU distance between bounding boxes to figure out whether there happens object occlusions or not. Based on the result, we can figure out whether we need to use trajectory prediction or not, and if necessary, how many frames ahead we need to predict. Then we run a Hungarian matching based on the IOU distance. Continuously, we project the track rest from local onto a global map. Then finally, we can associate the track rest using motion information only. When any different two objects in multiple views are not close, then just do threshold-based association, but some close objects exist, then do spectral clustering for the close objects on motion feature. This is our quantitative result. So left table is challenge result on AI challenge based on IDF1 metric, and right table is the comparison of different single camera tracking modules. Considering the trade-off between the accuracy and computation cost, we suggested efficient method. These slides show that we solved the ID switching problem of ByTrack without re-ID model used in BOSOT. So we can maintain the inference rate solving the ID switching problem. This is our conclusion. First, by using trajectory prediction, we praised the re-ID and developed efficient multi-camera, multi-target tracking system. Second, our method can operate in real time and real world. Now we search about the real application in construction sites. Below two images are two different CCTV views on same site, and above two are synthetic videos for each views. Our proposed method could be utilized in many different industries like constructions and factories because of the wideness of scene. Thank you for listening.
Thank you all. So that's all the presentations for track one. I would like to invite maybe the authors of the track one papers, if possible, can come in the front. We will have some Q&A. session. Also, if you are on Zoom, maybe you could maybe turn on the camera to let us know that you're there. Great. Or you can, yeah, if when there's a question, please come ahead to answer it in front of the cameras. Maybe you can take a look at the chat if there are some questions on chat. Okay, is there any questions from the audience? If not, I can ask a question. So the first question is that, because we are trying to generate the synthetic data for multi-camera tracking, and we find it very useful in our own use case. But to you, do you think there is some way that you wish us to improve the synthetic data so it will be better, more helpful for your own use case for the multi-camera tracking? Yeah, anyone can.
So I'm Arthur from the first team. We're from UW. And from my personal experience, if we want to sort of like take synthetic into account of helping the real world tracking, I believe that since we are actually doing like a multi-camera tracking, so I believe the 3D coordinate, as Thomas, you had mentioned in the previous summarizing presentation, the 3D location, I think for the synthetic data should be pretty easy to achieve from the original generation step. So if with those 3D, let's say footpoint location within the synthetic coordinate, I think we can probably better incorporate into our sort of like a global multi-object tracking in the sense of how to use synthetic to help the real data. And one other thing we'll like probably is about the probably the camera parameters for the synthetic data, because we know that the synthetic is very valuable, but without those synthetic, we can only sort of like manually labeling some pseudo camera intrinsic parameter to do the sort of like homographic projection. So if we can have both the 3D location of the object and also the 3D the camera parameters of those sequence, I think it will probably help us to get a better sense or better idea of how to incorporate those synthetic into the real world tracking scenario. Yep. Okay.
Anyone? Okay, if there is any author on Zoom, you can answer the question. Is there some way that we can improve the synthetic data to better help you? If not, I have a second questions for all the teams. So I know some of you have participated in the previous challenge in terms of the multi-camera tracking. In the previous challenges, we used vehicle-based videos for multi-camera tracking. And this year, we switched to people-based multi-camera tracking. So what do you think is the challenge between these two scenarios? Can the same method be applied to both scenarios? Maybe, so the team from UW have already answered this. Maybe for other teams that you can answer, like what's the difference of people tracking and vehicle tracking?
Hello. Actually, I did not participate in last year challenge, but I think I already seen some last year data set. So last year data set is too far and it's not clear the video, and the LID is, the picture looks different in each vehicle. So maybe in this synthetic video data set, their objects are so clear, like LED shots or blue pants like this. So I think the synthetic data set is more clear to understand the scene and is to understand is to understand train the deep learning model. So I think it's the most different things to advance now synthetic data set. Yeah, thank you.
Thank you. Yeah.
Yeah. Hello everyone. So my name is Zhong Zhang. I'm also from the UW, and so we have participated in the previous vehicle tracking challenge and also this year's human tracking challenges. I think the difference between the camera and between the vehicle and human-based tracking will be the appearance feature for the vehicle tracking actually is much less than human tracking, because cars are similar to each other, and there's multiple cars actually in the way they're exactly the same, just a little bit different in the maybe some people do some customize on the vehicles. So normally the vehicle tracking is more or less more based on the position in 2D or 3D. And also there's another difference is that in this year's challenge, we're collecting the human data in indoor. So which means there is a lot of overlapping for the cameras. So we can get some rich 3D information actually of the location of the human and try to do some tracking based on both appearance feature and the localization feature. But for the previous challenge in the vehicle tracking, actually although we have multiple cameras, but their overlapping are not that much. So we have to build some camera link model, try to estimate the car is from camera 1 and it's going to move into camera 3. So this kind of trajectory prediction or the estimation will help us better understand how the car is moving through all the different cameras. So the vehicle is just how going through all the different cameras. So I think that's the major difference between the vehicle and the human tracking. Yeah, that's it.
Thank you, Zhengyu. Maybe, do you have any question?
Just the follow-up question. Just mentioned that because the parent features might be similar to each other, for person then be larger different features. So what do you mean by this? Do you mean that maybe for example method, maybe we need some kind of similar parent features to achieve the. That would mean so for vehicles maybe the best method might have the higher accuracy, but for person
yeah, let me repeat it through the mic so people can hear. So the question is that it seems, or the answer is for vehicle features, they look very more similar than between people. So is there, so the audience is asking like whether there's any comments in terms of like what kind of method in terms of like re-ID or appearance features that we can use to address this kind of appearance domain gap.
Yeah, thanks for the question. It's a very good question actually. So for the in the human tracking, normally we just directly using a re-ID model. So we're using the neural network like method or some other method to try to extract the features from the human. But for the vehicle, we tried a similar way, but actually it does not work that well, because in terms of if we just directly extract the appearance feature from the vehicle images, actually they are too similar to each other. So actually we switch to characteristic method. So we categorize the vehicles, like is that white car, the gray car, dark or black car, and we also try to make sure it's a sedan or it's a truck. So we use this kind of categorized method, try to do the appearance feature similarity check between the vehicles instead of the re-ID features like the human. So that's a different strategy if we really want to use the appearance feature to like get a similarity between the vehicles and humans. Yeah.
Thank you. One more question I would like to ask. I see that representative from KIT and NOTA are here. Actually, these two methods impress me a lot because KIT method, they only use re-ID features. And for the NOTA method, they only use spatial temporal features. So this is a very contrastive method that they use. So my question is for KIT, like what do you think that spatial temporal information can help you in your method? And for NOTA, what do you think appearance features can be helpful in your method?
Yeah, I mean, we have the problem that we still have gaps in the tracklets. So yeah, we don't use motion prediction, and so we have gaps. And I think motion prediction and such things can help to bridge the gaps and improve the recall of our method. Okay, I think that's the main point. Thank you.
Actually, we use spatial information and reality inference both.
Okay. Both.
Yeah.
Okay. So
So maybe like how you combine them in the method, and how do you find them useful when they combine together?
How we combine together?
Yep.
We first mainly focus on reality-based appearance features to clustering, and if human body occluded, so its information downgraded, then we plus mainly more focus on the spatial information. Yeah.
Thank you. Okay, thank you for the clarification. Okay, so let's thank all the authors again. And now you can go back to your seat, and we can continue with the presentation for track 2.
Hello everyone, and thank you for joining us today. My name is Lehui. Hello everyone, and thank you for joining us today. My name is Lehui, and on the behalf of my team from International University, Vietnam National University, Ho Chi Minh City, it is my pleasure to present to you our work on the challenge that named Tracked Vehicle Retrieval by Natural Language Description with multi-contextual adaptive knowledge, which has achieved first place in the highly competitive Track 2 AICT Challenge. The scope of our problem is concerned with how to retrieve the video that contains the right tracked vehicle from the text description. The given vehicle is a very informative tracked vehicle that provides a lot of fine-grained features about the appearance of a target, while the natural language description is very intuitive, and its structure is diverse with many different synonyms that describe the same target. While there have been promising results, it is still very challenging to address the limitation of high-quality label data and the diversity of text data alongside with many multi-dimensional features from the visual data. In this figure, we introduce a multi-contextual retrieval framework, with the process consists of the following steps: pre-process, which we will deal with how to normalize the text data; baseline retrieval model, where we deal with how to create a robust retrieval model; domain adaptive training method, to tackle the unseen scenario that appear in the test set, which leads to domain bias between the training and the test set and resolve the domain gap between those two. And finally, post-processing multi-contextual pruning. We propose a multi-contextual post-processing technique that prunes out the wrong result based on the multi-contextual attribute information that effectively boosts the final retrieval result. There are numerous ways to describe anything in natural language, although it is very intuitive to human, but for machine it is very difficult to distinguish different descriptions of the same vehicle. Therefore, NLP preprocessing is essential and provides a consistency in the information order to boost the generalization of the model during the learning stage. Our pre-process method consists of two main steps, that is text cleaning and text standardization. For text cleaning, which is text description, the cleaning process comprises of removing the article, replacing misspelling words, and converting all verb into the base form. For text standardization, we use English prop bank semantic role labeling to convert all original description into the above format. Finally, we cluster these words into zero cluster based on the semantic similarity and replace them with their cluster name. To tackle the unseen scenario that appear in the test set, which lead to domain bias between the training and test set, we propose a semi-supervised domain adaptive method and training strategy to address the problem. The method consists of two main parts: generate pseudo-label and fine-tuning the baseline model. For the pseudo-label part, due to the difference between the two data domain features, we cannot use regular feature clustering method like typical domain adaptation on RealID tests. And due to the diversity of the text content in the data, we cannot recreate any pseudo-label near that content level. Therefore, we decide to reformat the description text of each vehicle track into the new format, letter 1 in the pre-process section, with three attributes: vehicle color, type, movement. For vehicle color and type classification, we will leverage the trained knowledge of the baseline model on the training set and turn it into a classification model, while the movement classification is leveraged by a motion analysis module. So based on our observation, we have determined that imposing strict constraints on the contextual attribute of the vehicle can significantly improve the accuracy of the final result. Accordingly, we propose a novel multi-contextual pruning approach and eliminate track with attributes that differ from those specified descriptions as color, type, and direction from the top of the rank. In contrast to our prior approach, we rely solely on unidirectional information. Our proposed approach leverages a new motion analysis module to prune track based on bidirectional information, which takes into account several directions of the vehicle. By integrating this module, we can more accurately identify and eliminate tracks that do not conform to the specified contextual attribute, thereby improving the overall accuracy of the model. We have verified our approach with the dataset provided by AICT Challenge 2023, with the dataset is CityFlow NL that have 666 target vehicles in 3,000 single-view track from 40 calibrated cameras with more than 500 unique NL descriptions. And scoring metric is mean reciprocal rank, or MMR. For the experiment result, we can observe that our overall framework achieved a state-of-the-art performance, while the new multi-contextual pruning technique further boosts the retrieval performance by several fold and achieved the first place of the competition. From this work, we have shown that we achieved a competitive performance of 82.63% MMR accuracy as the first place solution in the fifth and the sixth and the seventh AICT challenge. We propose a solution address linguistic ambiguity in the query, utilize CLIP for the feature extraction, use semi-supervised, and propose a post-processing technique to prune out wrong result based on multi-attribute information. Thank you very much for your time. If you have any questions, feel free to ask us.
Hello, everyone. My name is Dong Xie from the Novel Research AI Lab. Thank you for being here to listen to our talk in AICT Challenge Workshop Track 2. The topic of my presentation today is a unified multimodal structure for retrieving tracked vehicles through natural language description. My presentation will be divided into 4 parts: introduction, methodology, experiment, and conclusion. Here is the first part, the introduction. The AICT Challenge Track 2 incorporates the language modality called natural language-based vehicle track retrieval. This task aims to retrieve single camera tracks of vehicles that are consistent with the natural language query. Figure 1 shows an example from CityFlow NL. In the methodology section, our innovative deep learning system, the multimodal language vehicle retrieval MLVR, is introduced. This system is designed for text vehicle retrieval tasks. The MLVR system is a unique blend of various techniques and strategies that enhance retrieval process of vehicles by leveraging multimodal information, including text, images, and videos. The MLVR system primarily comprises 3 core components: an end-to-end text vehicle contrastive learning module, a clip-based train-free domain adaptation technique, and a semi-centralized control optimization mechanism. The structure of our MLVR system is depicted in Figure 2. The text extractor and the image extractor extract the text and the image information. The video frames and NL description are fed into the video recognition module to generate the video vector sequence. The bundle information of images and the keywords is delivered to the vehicle color modules, vehicle type modules, vehicle motion modules, and vehicle surrounding modules to create the corresponding vectors. The fused and weighted vectors are finalized in the mesh control system to produce the final score matrix. An integral part of our methodology is the analysis of natural language NL descriptions and corresponding descriptions from alternative perspectives. Our analysis reveals a connection between these 2 types of descriptions, suggesting that NL other views descriptions are supposed to be transferred from descriptions in other scenarios. As illustrated in Figure 3, the relationship between NL description and NL other views description can be observed. The video recognition module serves as the foundation of our MLVR model. This module is adapted from the XClip algorithm. Figure 4 shows the primary architecture of the video recognition module. Frames are input into the frame and temporal encoders to generate visual representations, while text information is processed by the text encoder to yield textual representations. The attention similarity process combines visual and textual representations to predict a video score. Both the vehicle color module and the vehicle type module are based on the tip adapter model. This model effectively integrates the strengths of visual and textual few-shot information to enhance classification accuracy. In this module, vehicle images are cropped using bounding boxes from the trajectory, and corresponding labels are extracted using the keyword parsers. Figure 5 presents the architecture of the vehicle color module. The blue part collects general purpose clip knowledge from the pre-trained model. After combining these knowledge sources in the orange section, the final losses are calculated for class predictions. Through an in-depth analysis of vehicle maneuver trajectories, we have developed the vehicle motion modules as a cultured direction control system, utilizing the provided trajectories. The vehicle starting vectors is obtained by fitting the first partition of the trajectory center points using linear regression, while the vehicle ending vector is generated by fitting the last partition center points with another linear regression function. Subsequently, the angle between the two vectors is computed to establish a baseline. Additionally, a set of threshold parameters is designed to generate the final direction. The process of calculation, the motion rate of a pickup vehicle is visually depicted in Figure 6. The vehicle surrounding module aims to extract information about neighboring vehicles in the surrounding of the tracked vehicle. Initially, textual representations of neighboring vehicle data are derived from natural language descriptions using the keyword parser. Simultaneously, other tracked vehicles within the same frame are identified and marked with bounding boxes. The vehicle surrounding module branches into two distinct pathways, which are visually represented in Figure 7. The frame and text are fed into the glib model to predict the tracked vehicle and adjacent vehicle positions and attributes. Concurrently, other vehicles mentioned in the frame with different track IDs are marked as proposals, which are subsequently filtered by the vehicle color model and vehicle type model. The final S-vector output is a product of the combined results from the glib model, vehicle color model, and vehicle type model. The match control system is employed to identify the optimal text-video match. A matching elimination system is devised to rewrite the score matrix, thereby enhancing the final MRR score. Algorithm 1 shows the processing of the matching system. Figure 8 illustrates a 6x6 text-video matrix example. The highest score is found at the intersection of row 3 and column 2, indicating a match between ID 3 text and video ID 2. Consequently, a predetermined threshold bias is subtracted from all other elements in column 2. This procedure is applied to all rows, resulting in a more robust and effective sum matching process. Here is the part 3, the experiment. In the experiment, the CityFlow NL dataset is used, consisting of 2155 distinct vehicle trajectories and associated tracked IDs, as well as corresponding natural language descriptions. In addition to the primary dataset, a separate text set comprising 184 distinct vehicle trajectories is utilized to assess the MLVR module's final performance. The mean reciprocal rank MRR serves as the primary evaluation matrix for evaluating the performance of the MLVR model. In the experiment, we conducted a comprehensive analysis of our MLVR model's performance, comparing it with other participating teams and running an ablation study to assess the contributions of each individual model towards the overall performance. Table 1 presents an ablation study of our MLVR approach, clarifying the influence of each module on the MR score. Employing the baseline video recognition module alone resulted in an MR score of 0.2761. By adding other modules, our model can arrive the highest MR score of 0.8179. Table 2 shows the public leaderboard for the task of tracked vehicle retrieval using natural language descriptions. Our MLVR model arrived at second place ranking, following the top performance team. This result undergo the competitive performance of our MLVR model. In conclusion, we designed an innovative multimodal technique called the multimodal language vehicle retrieval system for retrieving the trajectory of tracked vehicles based on natural language descriptions. Our proposed approach demonstrated its effectiveness by achieving an impressive score on track 2 at the 7 AICT challenge, which highlighted the promising potential of MLVR in the traffic field of multimodal retrieval. Here are the references of our slides. Thank you once again for your time and attention. If you have any further questions, please feel free to email me. You can also access our code on GitHub. Thank you.
Hello everyone, in this video I will be talking about our CVPR 2023 workshop paper, Comprehensive Visual Features and Pseudo-Labeling for Robust Natural Language-Based Vehicle Retrieval for the AICD Challenge Track 2 2023. About the problem introduction, nowadays the capability to search for vehicles is crucial for efficient traffic management. But current methods for vehicle search mainly involve image matching, which includes vehicle detection, re-identification, and tracking. However, in real-world scenarios, the query image may not be accessible, and obtaining and using natural language text descriptions is simpler and more flexible than using image queries. Therefore, there is a pressing need for natural language-based vehicle retrieval solutions. And the primary objective of Track 2 in the AICT challenge is to locate particular vehicles based on their textual descriptions. So this is an overview of our architecture. So as you can see here, we implement a two-stream network to extract the local and global information of the vehicle category, and then we fuse them together to get the final representations. So we propose an improved input mechanism for the model called multi-view associations and a post-processing model to enhance the retrieval results. We also adopt pseudo-labeling as a way to enrich training data, making a more robust model. About the multi-view association mechanism, in some previous methods, only one frame in the category is used as the input for the local branch of the model, making it vulnerable to misrepresentation of local vehicle attributes. So we propose a multi-view associations, a method that concatenates n frames in the category into one single image, then feeds it to the model, which helps the model consider different angles of the vehicles, resulting in a more robust representations. So the result of that process is shown in the picture here. And based on our experiment, we choose n equal to 4 as it achieves the highest accuracy in our local validation set, and as you can see in this figure here. So in our solution, we also use pseudo-labeling as a post-processing model to refine the retrieval results. Regarding the pseudo-labeling part, using our best models, we generate pseudo-labels on the test set, and then we combine it with the available training set to make a larger and more information-enriched training datasets. And about the post-processing phase, we have three main modules, including vehicle feature refinement, long and short distance relationship modeling, and clip feature reweighting. So an overview of our post-processing module module is shown here. So for the vehicle feature refinement, we use three CNN-based neural networks to classify the vehicle attributes, including color, type, and motion, and then we match it with a text query to enhance the retrieval results. And to further model the long and short distance relationship, we calculate the vehicle location and movement using bounding box and coordinates. Then for the textual queries, we extract all noun phrases in the text and keep all phrases describing vehicles. Then we match them together to generate a relationship and therefore further improve the retrieval results. For the clip reweighting part, given all the textual queries in the crop image of the vehicle, we generate clip embeddings and then calculate their dot product to generate a clip matrix, which is a similarity matrix between the textual queries and the crop image. Then we add it together with our original retrieve matrix to generate the final result matrix. So this is the result of our approach. And we apply our approach on the CVPR AICT Challenge 2023 and achieve the third place position in the private test set with an MRR score of 47.95%. So that's all for our team presentations, and thank you for your attention. More details about the code and implementations you can find in the GitHub link here. And thank you.
Thanks. So that concludes the presentations for track 2. Fred, are you there? Then maybe you can host a Q&A for track 2. If there is any author of track 2 here, maybe you can come up. Or if they are on Zoom, maybe you can turn on your mic. Thanks. Not sure if Fred is there. If not, I have a question. So there's a question from the audience. So for the last presentation, so on which hardware is the FPS benchmark done for the inference time? Oh, that's for MTMC. Okay, never mind. So if there's any authors on Zoom, there's a quick question. For this track 2 challenge, we are trying to do this retrieval of vehicles using the natural language. So as you can see that currently in the benchmark, I think a lot of teams, they are achieving very high accuracy, and we are saturating the performance on the benchmark. So I'm asking that, so what do you think is the gap or the room for improvements to achieve like higher accuracy for maybe like over 90%? And also, how can we improve the data to help you improve your algorithm?
Hi, I'm Dong Xie from Lenovo Research, from Team 28. I'm the second presentation. So I think we can use the surrounding information from the NAR description, such as the neighboring car, the stop sign, the other information from NAR description. If we combine this description with the video, we can continue to improve our result. Probably we can achieve 90% MRR. I'm sorry.
Cool, thank you. Is there any other author online?
Hi, we are from International University team.
So we believe that the current data set is still small compared to other video retrieval data set. It's now it's only have about 200 samples during test set. So it may not reflect a very good performance during the algorithm inference. So we believe that if you can increase the number of the data set, it will be a much more challenging and more room for improvement. Yes, thank you.
You. So that's all my challenge. That's all my questions. Is there any other question from the guests? Okay, if not, let's plus for all the authors for track 2 here. And now let's continue with the presentation for track 3. We have 8 papers for track 3. And then after that, we will have a lunch break.
First step, we completed the of approach and experiments in the AICT challenge. My name is Wei Zhou, representing the IoT CV team from Meituan Company. We participated in track 3, naturalistic driving action recognition. Given a video, the task is to detect driver distracted action in the video and output beginning and end timestamps and behavior class. The dataset consists of a total 13 full-hour driving videos recorded by 13 bio drivers. In each video, drivers randomly perform each of the 16 distracting activity once in random order. 3 cameras are mounted in the car to record cycling from different angles. First and foremost, we conducted an analysis of the dataset to gather information. From the graph, it's evident that the number of dangerous actions is relatively low compared to normal action. Therefore, during the training process, we employed oversampling techniques specifically for driver distraction actions. Furthermore, we identified certain noise in the dataset annotation. Firstly, there were instances of incorrect labeling of certain categories, such as taxing being labeled as for calling. Additionally, there were inaccuracy in the annotated tempo range of some actions. For example, the annotated range for the drinking water action was longer than the actual duration of the action. Lastly, there were cases of mislabeling, where the driver had resident chewing behavior after the annotated interview of the eating action, which went unnoticed. These noise factors significantly impact the final results and subsequently influence our approach selection and post-processing consideration. For the action localization approach, we have 2 options. The first option is to adopt a solution similar to action former, a network-based approach that combines video classification and action boundary regression. This approach utilizes a public available dataset and has achieved SOTA results on multiple benchmarks. However, during our training process, we observed issues with localization accuracy and potential classification errors. Therefore, we adopt for the second approach, which consists of 3 steps. First step, we deployed an action classification network to perform clip-level video classification. The second step, we partition the data using K-field validation to fuse the results from different fields and multiple perspectives to obtain action categories. The last step, we apply post-processing techniques to refine the fusion results and merge the clip-level classification outputs temporarily to obtain the final action intervals. By leveraging this multi-step approach, we aim to address the localization and classification challenges encountered in the first option. ultimately improving the accuracy and reliability of our action localization solution. Certainly, regarding the classification models, we have experimented with X3D and video MAE. Video MAE, which has been pre-trained on large-scale video dataset and fine-tuned on connected 1710, has exhibited excellent performance in video classification. Our results have also confirmed its superiority over X3D on the same dataset, demonstrating its strong performance in our context as well. Due to the relatively small size of the provided dataset for the computation, overfitting is become more concern. To mitigate this issue, we employed k-fold cross-validation on the dataset. Specifically for each perspective of the video data, we trained k-separated video classification models. The results of these k-models present fused during an average approach. Additionally, for the same video captured from multiple perspectives, with averaging the results improving the overall performance. However, it was observed from the graph that its different perspectives had varying capacities for different action categories. Hence, we adopted different ways for each perspective when performing the fusion. We explored two approaches for weighting selection, one based on convex optimization learning and the other based on manual design considering the correctivity of the data. Although the weights obtained from convex optimization tend to be overfitting, the manually designed weights prove to be more effective. As shown in the table, the approach outperforms the simple averaging fusion method. Once we obtain the temporal classification result of the video, post-processing was performed to fill the result and determine the temporal boundaries of action. We propose three methods: smoothing, linking, and removing, to refine the results. The smoothing method primarily utilizes temporal information to correct misclassifications and improving the overall consistency of the sequence. The linking method aims to merge labeling discrete classification results to form continuous action segments. On the other hand, the removing method focuses on eliminating isolated and insignificant results. This method involves the pruning of certain hyperparameters, which can be found in detail in our article and our release code. Due to the complexity of the process, a comprehensive explanation is beyond the scope of this discussion. Through the aforementioned strategy, we achieved the first place on the initial A2 leaderboard. Through the competition, we have accumulated valuable insights and regarding the techniques that proved to be beneficial as well as those did not yield significant improvements. We believe sharing these experiments can provide valuable lessons and guidance to the community. In conclusion, we would like to summarize our key takeaways from the computation experiments. The first one, comprehensive data analysis is very important. 2, pre-trained visual model helps. The 3, multi-view ensembling boosts performance. And the last, the dataset needs to be cleaned for further evaluation. During the computation, we observed that our model prediction were actually more accurate than the annotation provided by the computation. However, to ensure fairness and consistency with the final evaluation, we had to incorporate certain rules and adjustments during the post-processing step to align our result closer to the provided annotation. Nonetheless, in order to address real-world problems more effectively and validated further iteration. We acknowledge the importance of having a clean and refined dataset. This would enable us to better analyze and understand the underlying patterns, improving the performance of our models and explore novel approaches in action recognition. We believe that a well-structured dataset will contribute significantly to the advance of the research and development in this field. Thank you.
Hello everyone, I'm Rongchang Li, and I'm glad to share our approach for the third track, naturalistic driving action recognition. Our team members come from Jiangnan University and Suzhou University of Science and Technology, and additionally, we have received assistance from professors at the University of Surrey, Zhejiang University, and Tsinghua University. In the third track, we are asked to utilize video stream information from 3 views to identify the distracted driving actions. Specifically, we are supposed to recognize the start time, end time, and category of distracted actions for given videos. The challenges lie in several aspects. The first is how to establish an efficient framework to process long-duration videos. The videos is about 8 minutes, so we have to design the efficient way to save the computational resource. The second is how to well utilize information to determine the finest temporal boundaries of distracted actions. Additionally, we must address the issue of training satisfactory deep models with limited training samples. To solve the mentioned challenges, we designed the following pipeline. We divide the test video into multiple snippets and input them to the corresponding action recognition models to obtain the snippet-level action category probabilities. Then, based on the probability scores, we apply a series of post-processing operations to determine the distracted driving actions and the start and end time points. This mechanism allows us to gradually obtain global results from local scores in an efficient way. As only the AR model requires training, the total training cost is also very low. In fact, we only use 2 3090 GPUs throughout the entire competition. In the action recognition part, our goal is to generate snippet-level action probabilities. Considering the limited scale of the training dataset, we utilize X3D as our backbone network. We set the duration of the snippet to 32, 64, and 96 frames. The corresponding time duration in seconds is the result of frame count divided by 30, and because the frame rate of the test video is 30 FPS. During training, we crop the training videos to clips including complete distracted actions. Snippets are then sampled from these clips, and 8 or 16 frames are further sampled from each snippet for training the network. During testing, we first divide the video into different snippets with different size and overlap rates. Then, we sample 8 or 16 frames from each snippet and input them to the trained AR model to obtain the action probability. After obtaining the snippet-level action probabilities, We aim to generate frame-level probabilities to achieve more precise action boundaries. One simple approach is to average the action probabilities of all snippets containing the frame. However, the snippet-level results cannot fully reflect the true situation at the boundaries, so it may lead to mistake as shown in this slide. We can see that if we average all the action probability scores, the frame in the red box will be allocated an unreasonable probability score. That happens due to the frame trusts the results from snippet 1 too much. Actually, it should trust snippet 2 more, as it is closer to the center of snippet 2. Therefore, we propose the reliability-based action probability calibration operation. We generate reliability values using a Gaussian probability model, where the reliability is highest at the center of the snippet and lowest at the edges. We then use the reliability as weights to calculate a weighted average of the probabilities of all snippets containing the frame. In this way, we refine the temporal resolution to the frame level. Moreover, we can fully utilize the results of snippets of any size and any overlap ratio in a flexible manner. After calibrating the action probability, we choose the class with the highest score as the classification result, and its corresponding probability score is assigned as the confidence score. Then, we determine a threshold to filter out frames with low confidence scores. The threshold for Class C is defined as the average confidence of all frames classified as C. If the average value is higher than 0.5, we lower the threshold to 0.5. After the filtering process, we next merge regions belonging to the same action category to obtain candidate regions of longer duration. The confidence score of regions are the average scores of frames it contains. Finally, for each category, we again perform a region-level filtering to obtain the final localization results. As the candidate regions can be redundant, we set a high threshold. The threshold is set as 0.95 times the maximum confidence value of the regions predicted as Class C. We conducted ablation experiments using our self-defined training and validation sets. Specifically, we adopt 25% of samples of the given training set as the validation set, and the remaining 75% samples are used for training action recognition model. We can see that using multiple snippet sizes and ensemble models of 8 and 17 frames are helpful. And using the overlapping snippets can also improve performance. We compare the mean and propose the Gaussian averaging method to generate frame-level probabilities. It shows that our proposed calibrating methods are effective. Finally, using category customized method also helps a lot. Finally, we ranked the second place on the public leaderboard. The final result is 70-41. If you are interested in our work, you can visit our open source code or paper. You can gain the implementation details, such as training recipe of AR models. You can also contact me by this email. if you have any questions. This is all of my presentation. Thank you very much for your attention.
Hello, everyone. I am very glad to present our work named Multi-Attention Transformer for Naturalistic Driving Action Recognition, which is Track 3 of CVPR Workshop AI City Challenge 2023. I briefly divide the presentation into 4 sections. First of all, I will briefly go through the background and dataset, and then I will introduce our method, including data preprocess, feature extraction, multi-attention and time correction. Moreover, we will show some experiments results. Finally, we will make a conclusion for our method. Distracted driving is highly dangerous and is reported to kill about 8 people every day in the United States. Today, naturalistic driving studies and computer vision techniques provide a much-needed solution to identify and eliminate distracted driving behavior on the road. In this challenge track, users will be presented with synthetic naturalistic data of the driver collected from 3 camera locations inside the vehicle while the driver is pretending to be driving. The objective is to identify the start time, end time, and type of distracted behavior activities executed by the driver in each video. Our approach builds a transformer-based model, using the action classification to estimate action boundaries for each moment. In feature extraction stage, we extract a sequence of video clip features by video MAE, then embed each of these features. The embedded features will be encoded via window attention and global attention module. A candidate action is generated at each time step through using the classification head to predict the action category and the regression head to predict the boundaries of the action time boundaries. Multi-attention, as shown in the right of Fig. In the multi-scale channel transformer encoder, the feature F1 extracted from the video segment is input to layer norm, multi-head attention and window attention, and then downsampled to obtain feature F1. The feature F1 is re-entered into the encoder, and the feature F2 is obtained after layer norm, multi-head attention, window attention, and downsampled. This operation is repeated n-1 times to obtain F2, F3, Fn. After that, F2, F3, Fn are input into the multi-scale channel transformer decoder for decoding, and the category information and the corresponding time information of the actions are regressed through different fully connected layers. We observed some videos and found that there is a lot of background information in the videos that is not needed. So, we detect the human body in the video and crop each frame. To ensure the stability of the video, we perform human body detection for each frame of the video and save the one with the largest detection area as the crop standard for the whole video, avoiding background shaking caused by different detection sizes in different frames. Video MAE is adopted for feature extraction on rear and dashboard views in this paper because of its better performance in the ITH We fine-tune different models on the videos from rear and dashboard views respectively. A standard transformer block structure includes 2 multi-head self-attention (MSA) and multi-layer perception (MLP). The output of temporal action localization model contains a large number of predictions with low scores, and these results have a large range of overlapping temporal regions. The time correction operation consists of 3 main steps, which are: first, for all prediction results of each video keep only the one with the highest score among the results of the same label, and discard the other items. Second, perform step 1 separately for several different models and stitch the obtained results. Third, for the results obtained in step 2, fuse the results of the same labels and same video according to the time intersection over union TIOU. Considering the different areas contain different information on the target of the screen, we conduct as many experiments as possible for a fair comparison to the features with different crop parts and different resize mode of the videos. The results are shown in tab. Fifth, compared with the results map 67.33% in tab 4. There is not much difference. So we remove the crop pattern in the follow-up experiments. We test the performance of the model in rear and dashboard view features extracted with different backbone model from Vidimi, as shown in tab 6. Different features have variable performance on TAL. The proposed system is submitted to the Track 3 of AI City Challenge 2023 for evaluation, as shown in table. Our method surpasses these methods by a large margin with score 0.6723 and ranks third place. In this paper, we present a multi-attention transformer-based method for temporal action localization. We conduct extensive experiments to compare with different video views, different feature extraction networks. We also propose a time correction module to improve temporal accuracy. Thanks for your watching. If you have any questions, please contact us.
Hello everyone, my name is Liangqi Yuan, a first-year PhD student at Purdue University. I'm very honored to present our project here, peer-to-peer federated continuous learning for naturalistic driving action recognition. Let's have a quick introduction for federated learning. Federated learning aims to promote collaboration while protecting privacy. In traditional approaches, local learning often results in low generalization due to the lack of collaboration, while centralized learning raises concerns about privacy. Classic federated learning is client-to-server architecture. That is, clients send deep learning models to a server, the server aggregates these models, and then sends the aggregated model to all clients. In some peer-to-peer federated learning frameworks, a single client takes on the role of the server. But sometimes we have trust issues with the server, such as single point of failure, security, and fairness concerns. For example, it remains an open question how can we ensure that the server fully considers those underrepresented clients. Therefore, we have an idea to forego the use of the server, as well as aggregation computation. Subsequent clients would simply train on the model from the previous clients. This is referred to as gossip or continuous learning. So this is our method. We propose a peer-to-peer federated learning framework that combines a continuous learning approach, which allows subsequent clients to train directly on the previous client's model. This can effectively reduce the communication, computation, and storage overheads, and facilitate knowledge dissemination. We implemented the proposed FastPC on 2 datasets, including State Farm dataset and AI City Challenge dataset, as shown in the figure. You can see that there is heterogeneity in the data distribution between these 2 datasets. The main reason for this is that they have different systems, such as vehicles, cameras, and so on. In addition to the proposed FastPC, we also re-implemented baselines, including independent learning, FastAverage, and FastProx. The base model is ResNet 34. The input of the base model is the driver images, as shown in the figure. We use 3 metrics to evaluate the performance of the federated learning frameworks. The most important one is the client objective, which is the accuracy of the model on the local dataset. The second one is the generalization performance, which is the accuracy of the model on other client datasets. The third one is the performance of the trained model on new clients. From the experimental results, FastPC has an outstanding performance in the client objective. It can propagate knowledge very quickly without waiting for server aggregation. Why is the proposed FastPC effective? Because in traditional FastAverage framework, which uses server aggregation as a knowledge dissemination paradigm, there is no knowledge dissemination between the clients before server aggregation. Therefore, all clients are trained on the initial model with random weights. However, in the FastPC framework, only the first client is trained on the initial model. Therefore, FastPC can achieve faster convergence and quicker knowledge dissemination. So this is a comparison of proposed FastPC and client-to-server federated learning. We use FastAverage as an example. We compare these two systems, such as the knowledge dissemination method, dissemination rate, limitation, and so on. I cannot tell which framework is better. Each framework has its own advantages and is suitable for different scenarios. But specifically, in V2V communication networks, the proposed FastPC will be more effective. Thank you so much. If you have any questions, please feel free to let me know.
Hello everyone. Today I'm going to present our work M2DAR multi-view multi-skill driver action recognition with vision transformer. My name is Yunsheng Ma. I'm a first-year PhD student at Purdue University College of Engineering. So first I will introduce the background of this work. Distracted driving is a major cause of traffic accidents, and AICT Challenge has released a comprehensive dataset and organized the competition on naturalistic driving action recognition to recognize those distracted behaviors. And our goal is to accurately determine the start and end times and identify the specific type of actions performed by a driver in each video using input from multi-view camera views. And our system comprises of two stages, the driver action recognition stage and the election stage. In the driver action recognition stage, we utilize a multi-skill vision transformer model to classify fixed-length video clips into different action categories. The model is designed to utilize both spatial and temporal information, allowing us to effectively capture the spatial temporal characteristics of the actions. In the election stage, we refine the preliminary findings obtained from the action recognition module to arrive at a final prediction. This stage is crucial for improving the performance of the DAR stage, as it enables us to consolidate the information from different camera views and select the most reliable action candidates. So specifically for the election algorithm, the input is a probability matrix in T times C times M, where T is the length of the video, C is the number of predefined categories, and M is the number of views available. And our algorithm consists of 4 steps: aggregation, filtering, merging, and selection. I will dive into details of each of these steps in the next few slides. So in the aggregation step, we apply a convolution operation to the input probability matrix to capture information from various camera views. The convolution operation is defined using convolution kernels that weight the information from each camera view differently for each action category, integrating the complementary information from different camera views while focusing on the one containing the most discriminative information. In the filtering step, we identify the initial action candidates by extracting continuous frames with probability scores that exceed a predefined threshold for each action category. The resulting clips are considered as potential action segments that may contain the target actions. Frames with probability below this threshold are discarded as they are unlikely to represent a valid action. In the merging step, we merge clips that have a small temporal gap between them by iteratively comparing the temporal distance between each pair of adjacent action candidate clips, and we merge them if the distance is less than a predefined gap threshold. And the final step is the selection step, in which we compute the average score of all merged candidates for each action category and choose the one with the highest average score as the final action candidate. To summarize, in this work, we present a multi-view, multi-skill framework for detecting distracted driving behaviors in untrimmed videos. And this framework achieved an overlap score of 0.5921 on the A2 test set of the AICT Challenge 2023 Track 3. And the proposed framework has the potential to aid in the development of more effective driver monitoring systems and ultimately improve road safety.
Good day, ladies and gentlemen. I'm honored to be here today to present our study, Chiplet Tempo-based VR recognition with multi-view for tempo action localization for Track 3 in AICT Challenge. This is done by Huizhen Lei, Mingguan Wu, Menchen Tung, and Nguyễn Phúc from the Tel Cyber Space Center, the Tel Group. First of all, about introduction. Nowadays, traffic accidents have taken away numerous lives every year around the world. Distracted driving is highly dangerous and is reported to be one of the most common reasons causing those deaths. So, studying and analyzing the driver's behavior is crucial to reduce traffic accidents and save many people's lives. With the advancement in deep learning and computer vision, naturalistic driving studies can provide virtual solutions to eliminate driver's distraction and lower the risk of road accidents. The objective of Track 3 in AICT Challenge 2023 is to recognize the distracted actions by the driver in a given video. In the following chapter, I will provide an overview of the method and present our findings. We start with an input video, which is fed into temporal chiplet algorithm to obtain clips with enriched temporal information. Then two action recognition models, Expand 3D and a multi-scale vision transformer, are adapted to extra features. Subsequently, two-level feature fusion is developed to fuse clips features. And finally, we use a famous action detector named Action Former to localize distracted actions. So about temporal chiplet algorithm, in action recognition, existing methods feed a video input into clips, and a clip is created by a number of frames with sampling rate. So the primitive speed procedure above has some drawbacks. Firstly, a single frame of a clip contains only spatial information. Secondly, the temporal information of a clip is lower density when the sampling rate increases. And lastly, it does not utilize the channel dimension of each frame in the clip when the video is grayscale. So to overcome these issues, we propose a temporal chiplet algorithm to retrieve temporal information of single frames, then enhances the temporal information density of the clip. For example, at each frame I1, this technique stacks the current frame I1 and the next two consecutive equidistant frames I2 and I3 to obtain a new frame I new with 3 channels. So here is an example of applying temporal chiplet algorithm, observing the figure. I noticed that there is a difference in orange rectangles of 2 images. Intuitively, this difference is a pattern with temporal information where an action happens. Moreover, to verify the effectiveness of temporal chiplet algorithm, we conduct an experiment in action recognition task with a Expand 3D model. The results are measured by the accuracy observing the table. Results are significantly improved in our own force and our own views when we apply the temporal chiplet algorithm. Therefore, we use a dataset of clips with applying temporal chiplet algorithm for picture extraction in both Expand 3D and multi-scale vision transformer. Pay attention to two-level feature fusion. Observing the dataset, we find out that some categories are difficult to identify in the dashboard view, but seem to be easy in other views. So the first of 3 views is taken into account in order to further improve the accuracy of prediction. So we adopt a two-level feature fusion, including multi-view fusion for fusing 3-view features and a multi-model fusion for fusing features from 2 networks, Expand 3D and a multi-scale vision transformer. So here is an illustration of two-level feature fusion. So now let's shift our focus to the results. we evaluate our proposed method on the Track 3 Naturalistic Driving Action Recognition of AICT Challenge 2023. Look at the table. We achieved a competitive result with a 58.81% on the leaderboard. So in conclusion, I hope that the findings and insights presented in this study offer valuable contribution to the field of naturalistic driving action recognition. Lastly, I would like to express my gratitude to your kind attention and your time. Thank you all very much indeed.
Hello, everyone. Welcome to our presentation on Track 3, which is the anomaly detection in naturalistic driving video. The title of our work is Deep Segmenter, which is a temporal action localization for detecting anomalies in untrimmed naturalistic driving videos. And the work was done by Armstrong Aboa, Yilas Baxi, Rashid Musa, Nima Jessica, and Yawedu Jenfi. And we are from Northwestern University and University of Missouri, Columbia. It was a collaboration work. Okay, to begin with, driving is a complex activity that necessitates a high level of concentration and coordination. Even with the best intention, drivers may engage in behaviors that can result in accidents, such as distracted driving, aggressive driving, or driving while impaired. Our ability to identify and characterize these behaviors is essential for enhancing road safety and preventing traffic accidents. To do the aforementioned, a comprehensive data set detailing different anomalous driving behaviors and differentiating them from safe driving action is required. The naturalistic driving data set is one of such data that has been extensively used to study unsafe driving behaviors, as shown in the image. The goal of AICT Challenge is therefore to help competitors to be able to identify 15 unsafe driving behaviors in a naturalistic driving video. And the task is to be able to first identify the start time of the anomaly, the end time of the anomaly, and the correct class of the identified anomaly. We would like to look at past approaches and limitations to those approaches that are being used in driver anomaly detection and classification. The anomaly detection and classification for naturalistic driving video could be classified into 3 major steps. First is identifying and extracting visual features from video frames. Second is identifying or defining the state of the driving behavior and observational period based on instances related to the extracted features. Third is classifying the type of driving behavior observed in the localized time sequence where the action is occurred. The past approaches have used 2 main approaches or 2 main steps or 2 main ways of doing it. One is using a rule-based approach to do the anomaly detection. And second is using deep learning approaches to do the anomaly detection. Now, with all these 2 approaches, the first approach, which is the rule-based, is good at doing step 1 and step 2, but does poorly in step 3. The deep learning approaches is also good in doing step 1 and step 3, but does poorly in step 2. As a result, the goal of this study is to introduce a hybrid approach to continuous video activity recognition by capitalizing on advantages of the 2 aforementioned approach that's based both the rule-based and the deep learning approach. We therefore introduce what we call deep segmenter in this work. We'd like to look at the methodology of the deep segmenter. The deep segmenter is made up of 4 modules. 1 is a data module, 2, the activity segmentation module, 3, the activity classification module, and 4, the post-processing module. The data module is responsible for pre-processing the data into a form that could be processed in the various steps. The processed data or the processed video is passed through the activity segmentation model, which has what we call the deep segmenter. And the algorithm for the deep segmenter is there. So the deep segmenter is made up of 2 parts. It has the key point detection and the event segmentation. So the input video goes through the key point detection, where the facial key point of the participant is being identified. And this is passed through the event segmentation, which use heuristics to be able to classify the event into the extracted frames as event or non-event. Event means anomalous and non-event means normal driving. Based on the rules, this event is being passed through the classification module, which is a 3D network proposed by Facebook to classify the event into one of 15 of the event. The final results is being processed into the summation format of the AICT. Our approach got 8th place on the leaderboard as shown below. We want to conclude that the approach used is fast and could be improved further.
Hello everyone, my name is Erkut. In this video, I'm going to present our paper Transformer-Based Fusion of 2D pose and spatiotemporal embeddings for distracted driver action recognition. Let's start with the introduction. In this problem, our aim is to both localize and classify distracted driving actions. We conduct our study on the Track3 dataset, including 3 cameras that are mounted in vehicle and 16 different distracted activities. This problem and dataset are challenging due to several factors. For starters, we have a demanding need of temporal localization accuracy. Also, we have 35 drivers who have different appearance blocks, such as sunglasses or hat. Lastly, some of the distracted behavior classes share a similar visual appearance. Now, let's discuss our methodology. Here you are seeing a depiction of our methodology consisting of 3 subparts. In a preprocessing step, we resize each video and feed our model to extract different features. In the middle part, extracted features are fed into the transformer-based fusion architecture. In the final step, class probabilities obtained after the MLP head per camera view are analyzed for finding the frame level significant peaks related to each class in a video. Firstly, without loss of generality, we use the slow-fast network to extract spatiotemporal features from overlapping video clips. As a next step, to take advantage of 2D pose information, we adopt a 2D top-down pose estimator HRNet network to generate the whole body joint coordinates. We select a subset of critical key points from body parts that correspond highly to distracted driving activities. However, the joint coordinates alone cannot explicitly convey motion information between body parts to the proposed architecture. To address this, we focus on highly active body parts and incorporate additional features into the pose feature embeddings, such as the pose of the head, the relative positions of the left and right hands to the face, and the relative position of the upper lip to the lower lip. Here, another problem is how to combine 2D pose and spatiotemporal information in a smart way instead of traditional concatenation. To this end, we propose transformer-based fusion solution. Proposed solution is generic and independent of the camera numbers and positions. 2D pose embedding is considered as the position embedding of the encoder, while the spatiotemporal embedding is the main input of the encoder. The architecture includes one LSTM layer before the position embedding. The proposed method uses a temporal sliding window approach during the training phase. For all classes K within a given video segment X, we compute a target probability score using the generalized softmax function. We train our network with the cross entropy loss. And P frame Y is the output frame level class probabilities within an associated video segment, while P segment frame Y is the segment level class probabilities for that selected frame under consideration. And here, C denotes the total number of cameras within the multi-camera setup, which is 3 in this problem. Now, let's see some results. Our method achieves a 0.5079 overlap score in the track 3. Additionally, we look for F1, precision, and recall evaluation metrics. Our experiments have proved that the proposed solution has achieved better results compared to the standard concatenation techniques. We also conduct ablation experiments to understand the importance of each component in the architecture. You are very welcome to come our poster session to discuss about experiments and details of the proposed architecture. Let's now conclude this presentation. In summary, our method is generic and independent of the camera numbers and positions while yielding the competitive results. We conjecture that the transformer-based fusion of embeddings will be helpful in similar problems. Thank you for your time and attention. Have a nice day.
Thank you very much for all the authors of track 3. Now we can open the space for the authors. Is there any author here? Oh, feel free to come up. Okay. Is there any questions from the audience on track 3?
I have 2 questions.
Yeah, go ahead.
Yes. Should I
yeah, please.
Yeah. So I have 2 questions for the first paper. Let's start with the first one. In slide 6, and you were mentioning about the human designed weights. So what is the exact meaning of that? Human designed weights in that slide 6.
Okay. Is there any author from the first paper, which from May 12? Can you answer the questions?
I'm here. Can you hear me?
Yes, we can hear you.
Can you show the slides on the screen?
Just a second. Let me open it.
Okay. Yes. Example to address the localization.
Let me know which is this. Okay.
Okay. Since we have 3 different camera views about the driver, so we try 3 different type models, and after training the models, we want to ensemble the prediction of different models. And from the slides, we can see different views have different capacity of different distracted behaviors. So it's easy to do the ensemble of different views with different weights on specific classes. To do this, we try 2 ways. The first way is to use convex optimization to learn three group of weights of different models for different classes. But the results tend to overfit easily. So we select the weights and evaluate our validation datasets to print the weights manually.
Not sure if that answers your question, but can.
Yeah, more or less. Yeah, it's also not easy to hear. And the second one is also related to this one. can you also explain a bit in detail about the post-processing step, like the technical detail? Because I also checked the paper, and it was not clear me exactly what are you doing in that part. Yep. Is the author from Meituan? Yep.
Okay. The post-processing is to the tag is to localization the distracted behavior. But our network is to the output of our network is the classes probability of different distracted behaviors. So to get the interview of different distracted behaviors, we need to merge the distracted classes probabilities to get entire interval.
Answer your question?
So that part, we also do the post-processing, but I'm exactly asking the details, like in the smoothing part or the what?
Okay.
Yeah, like what did you run, like an algorithm, or do you have like ranking model or something like that, or?
Okay, if some algorithms with some experience and some hypermeters training. If you are interested in the details, you can check our code or discuss with me with an email.
Okay. Yeah, we can continue the discussion maybe through email and other methods. I also have a question. Maybe we have the author from TUE here. So we have the videos inside the camera for the drivers, but this is a good application, you know, for autonomous driving. We also have the views from the dash camera and other sensors. So do you think these two can be combined together for more like a traffic safety? Is there some way that you can think of to merge these two modules? Maybe start with the authors from TUE here.
Yeah, I think that will be possible. So because the more data you have, the chance is getting higher to improve the safety. So of course the dashcam data will be helpful as well. But the only thing that we need to really align these two problems together and combine it in a smart way, let's say, because this is directly focusing on the driver, but dashcam is more focusing on the other surroundings or pedestrians or other traffic participants. So that's why it's always nice to have more data, and I think it should be really helpful to improve the public safety. But we should consider that one and see the data set as well, like then combine all of them together for the autonomous driving. Yeah.
Yep. Thank you. Let's see. Oh, go ahead. Any other author want to answer this question?
But I have different opinion about this track. This track, the task of this track is localization. But the aim of this tag is to protect the safety of the driver or the passenger. We all know the accident happened accidentally. When the accidentally happened, we cannot get the entire video and localization, the distracted behavior and warning him. I think the task is designed to be a predicted task prediction
mode will be most suitable for our motivation.
Yep. So you mean through our observation of the driver, we want to do more prediction instead of like with dash camera, it's too late when we find out there's an accident.
Yes.
Yep, I get the point. Is there any other authors also want to answer? If not, so right now it is 12 at noon. So thank you all. Let's applause for all the authors for track 3 again. Thank you all. So now that concludes all our session for the morning part. So now let's have a lunch break. So our lunch break is until 12:50 p.m. So let's come back at 12:50 p.m. We'll present all the papers for track 4, track 5, and 4 independent papers. And then we'll have the panel discussion and award ceremony. Thank you all. Hi all. So this is 12:52 p.m. Let's wait until 12:56. So 3 more minutes, and then we will officially get started with the presentations from track 4. Okay.
Good afternoon, everyone. We present the
Hello, everyone. Let us know if there's any issue with the audio and visual, things like that. Now we will continue to play the presentation for track 4, which is on the automatic checkout system. And in this track, we have 6 papers. After the track, we'll have 10 minutes for Q&A.
paper, Improving Deep Learning-Based Automatic Checkout System Using Image Enhancement Techniques. This is our team solution to the AICT Challenge Track 4. Automatic checkout system enables customers to scan and pay for their purchase without the assistance of a cashier. Recently, vision-based checkout systems have been a new approach that incorporates computer vision and deep learning technology. Using a camera, the system can classify and count products when they are placed over a shopping tray. However, there are several issues that need to be considered. Firstly, we have to handle motion blur from fast scanning action. Secondly, noisy and unrealistic synthetic training data that doesn't match with real-world products. Thirdly, hand interference that can fail the detection and tracking process. Finally, in some cases, the camera is misaligned with the region of interest, which is the white tray in the image. Our approach system consists of three main components: enhancement, detection, and tracking. Enhancement techniques are performed on both training data and testing video. For the detection task, we use the state-of-the-art YOLO-VA models, and for tracking, we use the SORT algorithm with a modified track management process. Here is the visualization of the pipeline of our proposed checkout system. We first improve the input image quality by deblurring and denoising using a deep learning-based enhancement model called NavNet. Then, we use the llama inpainting methods to remove the hand region in the image. Finally, the standard detect and track pipeline is performed on the hand-free image to obtain the counting result. We simply use YOLO-VA and SORT algorithm to accomplish this task. We will go through each process in detail. First, let's look at the enhancement process. NavNet is the state-of-the-art method for deblurring and denoising. The NavNet includes several novel modules like the simple gate and the simplified channel attention that have improved the enhancement quality and reduced complexity. In this work, we simply use some retrained NavNet model for both deblurring and denoising tasks. The enhancement process is performed on both the training image and the testing video. Here, we use the NavNet to improve the quality of the synthetic image patch during the data generation. This data generation pipeline is a copy and paste paradigm where product image paths are placed randomly over the background image. The background images are taken directly from the testing video. In addition, we also perform a simple blood field algorithm to localize the area of the white tray, which is the region of interest. All the generated bounding boxes are used to train the YOLO-V8 models later. We also noticed that most of the provided synthetic images are too bright, so we dim the generate image a little to make it more natural. Next, we remove the hand region in the image. The llama inpainting method is a powerful deep learning-based model that can remove unwanted objects from image. The llama model introduced the use of the fast Fourier convolution and the perceptual loss, together with an aggressive training mass generation strategy, leads to a model that produces truly impressive inpainting results. It is fast and supports arbitrary image size without compromising the quality of the result. To perform the inpainting task, we need the human mask. In order to generate a human mask for the inpainting, we simply turn to YOLO-V8. YOLO-V8 is the latest state-of-the-art method proposed by Ultralistic. It is a versatile model that can perform both object detection and segmentation. We simply use pre-trained YOLO-V8 segmentation models to generate a human mask for the inpainting process. For the detection task, we train two YOLO-V8 models, one for detecting the product and the other for detecting the white tray. The final step is the tracking and counting of the product. For tracking, we simply use the simple online real-time tracking algorithm, or SORT, with a customized track management scheme. The track management scheme is implemented to track and count the product at the same time. This scheme handles all scanning scenarios presented in the testing videos. First, we define a mean entering distance to ensure that the object is only counted when it is fully inside the region of interest. After the object passes this threshold distance, each state changed to confirm, and only confirmed objects are considered for counting later. We define a counting range around the center of the ROI, when the object is inside the counting range for at least 3 consecutive frames and satisfy the IOU threshold, we mark the object as counted, and we simply print out the frame index of the counting object. Here is the summary of the quantitative evaluation for the first round of the ICT Challenge Track 4. Our method is in the first place with an F1 score of 97.92%, which is quite impressive. Here, we demo some complex cases that we encountered during the evaluation. In the first case, the object is moved in and moved out of the ROI. In the second case, a part of the object is outside the ROI. In the third case, multiple objects are scanned together. And in the fourth case, the camera moved, making the ROI off-center. However, in all cases, the track management scheme worked quite well and delivered outstanding results. In conclusion, we developed an automatic checkout system that combines enhancement techniques and using state-of-the-art detection models that can help improve the performance of the whole system. We also devised a track management algorithm using prior knowledge from the testing video to scope with the complex scanning actions. We have included subcode in our GitHub page. Please check them out. Thank you for watching.
Hello everyone, this is Delong Liu, and today I will introduce an adaptive target region-based commodity detector system and developed for Task 4 in AICT Challenge. This project was a collaborative effort by Zeliang Ma, Delong Liu, Zhe Cui, and Yanning Zhao. We are from Beijing University of Posts and Telecommunications. I will introduce our work in the following 4 sections: challenges, methods, results, and conclusions. The first one is challenges. In this competition, we primarily face 2 significant challenges. One of the challenges, as depicted in the diagram, is the dramatic positioning of the tree in the video. This rotation necessitates allocating the results to accurately location the detection area. The second challenge was faced was generating sufficiently training data for the detectors and classifiers. To overcome this, we explored different data augmentation methods and target data synthesis approaches. It's necessary because there are substantial differences between the training dataset and the testing dataset. To enhance the counting and recognition accuracies, we have designed our frameworks with 4 modules, as depicted in the figure. The first is the processing module, which serves as a bridge between the training and the testing data. In the section, we focus on ensuring precise counting results. To achieve this, we utilize the open source module directors to extract the trace position information and then update the target region accordingly. During trend detection, we utilize an open source module to detect the trace region and calculate the intersection over the union between the last detection trend region and the correct target region. The IOU values helps determine whether the tree have moved. Additionally, the tree region detector in the previous frame is used to assess its need for an update, and appropriate processing is carried out accordingly. To optimize the computational efficiency, trend detection is performed every 15 frames, and the IOU storage is used to determine whether the tree undergone any movement. The tree information is updated based on its moving or stationary state. To address those issues of the overly bright or dark image in the train set, we employed the traditional MSRCR and the deep learning method RetinaXNet. Those technique helps enhance the virtual quality and balance the brightness level of the images. We ensure the appropriate coverage of the products and avoid interfering with the detector's training. We randomly pitch the products into the train area and cover them with human skin. This ensured and desired coverage ratio with maintaining the integrity of the training process. Simultaneously, we record the related position information of the product and generate foreground segmentation labels. Those recordings provide us with the necessary training data for the detectors. Based on the recording bounding box, we cropped the foreground images to acquire the required training data for training the classifier. The second module of our system is the detection module. The purpose of those modules is to accurately locate and identify the products that appear in the video. It aims to produce more precise target detection results for subsequent classification. In order to mitigate false detections of the background, we utilize the results of two detectors and fuse them together. The third module of our system is the classification module. In this module, we utilize the four CNN-based classification modules to efficient night to retinite night. Those modules are combined to perform the feature extraction and classification tasks, while the detection module focuses on distinguishing between the foreground and the background. Accurately and reliable classifying the product within the fold image become crucial in this module. To achieve this, we have developed the multi-layer precision form fusion module as depicted in figure. MPFM facilitates and integration of the features extracted from the classification modules. In order to optimize the fusion process, the features from each classification modules are collected or further processed by the FPFM. The FPFM functions as a multi-layer procedure. This allows the effectively feature fusion and enhance the classification performance of our system. And the module of our system is the tracking module. This module receives the features extracted from the FPFM and performs the tracking using a deep sort. The deep sort-based tracking enabled our system to accurately track and identify the products across the consecutive frames. Furthermore, the tracking results are subject to additional processing through the multi-target confidence refinement module. This module helps address the potential errors in detection and classification. This ultimately leads to more precise and reliable final results. With the effectiveness for our proposed method, additional analyses are conducted to examine the performance improvements brought by the data arguments and system methods. The adaptive adjustment detection region algorithm for the video frame data reprocessing. The double detectors fusing algorithm and the FPFM. Table 2 is about data arguments. Table 3 is about data synthesis methods. Table 5 is about target directors fusion algorithm. Table 6 is about MPFI. It is worth mentioning that our algorithm performs well on the official test A, with only almost negligible difference of 0.0005 compared to the best FE score, while leading to more than 0.15 compared with the other contestants. Finally, we have presently an adaptive object detection system, delivering outstanding performance in the 2023 AI City Challenge Task 4 competition. Our system successfully reduced the false detections and missing detections. However, it is important to note that our correct implementation does not meet real-time requirements. Moving forward, we acknowledge the need to make a balance between the accuracy and efficiency in our method. In the future, our efforts will be directed towards optimizing the system to enhance its real-time capabilities. We will also prioritize the ensuring and meaningfulness. We will also prioritize the ensuring the meaningfulness and effectiveness of the proposed approach. Thank you for your listening.
Hello everyone. Today we present our paper on DeckNet, a deep automated checkout system submitted in the AI City Challenge 2023 Track 4. I'm Yishun Kai.
And I'm Aaron Jiang. In this paper, we developed a robust system for automated retail checkout. DeckNet is a deep learning algorithm that addresses existing challenges with its unique solutions.
For instance, data augmentation helps with synthetic training data, selective deblurring will counter motion blur, and retrospective rectification algorithm corrects missed or wrong classifications.
Framing the challenge as a detect, track, count problem, many previous works have addressed the areas of object detection, tracking, hand segmentation, and video deblurring. Models such as YOLO and StrongSort have produced more robust results than classical computer vision algorithms. Our research aims to bridge the gap between theoretical models and their practical applications for this challenge. Our proposed model, DeckNet, contains 3 modules: pre-processing, training, and post-processing. This image shows the software architecture of DeckNet. Each part will be discussed in detail in the following sections. In data augmentation, we randomly adjust the brightness, reflectivity, size, and orientation of the training images and fit multiple product images with minimal overlaps onto the cropped background, resembling the checkout counter. Then we split the data into training and validation sets. For training the YOLO VA model, we tune the learning rate, batch size, and dropouts with Atom Optimizer. Models are trained for enough epochs until validation loss converges and training loss plateaus. The randomness in data augmentation produces different models for ensemble learning.
Prior to neural network processing, we perform video pre-processing. Initially, we masked the hands using our optimized hand segmentation class based on Eagle HOS, detecting and masking them with the background color. We also conduct region of interest detection for the white tray area in this challenge. Starting with the preset ROI as a failsafe, we apply grayscale and Gaussian blur to mitigate color and shade effects. Then, the Canny tool and shard derivatives identify edges. Finally, the flood fill tool from OpenCV determines the ROI with carefully selected seeds. To address motion blur, we utilize NavNet, a highly efficient CNN for image restoration. Pre-trained weights were sourced from the REDS dataset. Despite its efficiency, deblurring remains complex and time-consuming. To ensure faster inference, we selectively applied deblurring to frames when new items enter the scene. The classification result from the deblurred frame carries greater weight in the final item result calculation. Here you can see the deblurred frame on the right. Our system's backbone comprises 2 key components: YOLO V8, a powerful classifier with advanced techniques like anchor-free detections, and StrongSort, an enhanced deep sort algorithm that improves accuracy by approximately 8.5%. The backbone generates a dictionary shown in the 3rd point here, where each unique index assigned by StrongSort serves as a key. The corresponding value is a tuple containing the timestamp and an inner dictionary, which tracks the count of each class detected by YOLO V8. With the generated dictionary, we use retrospective rectification to reduce instability in classification results. We retrospectively check previous detections within a certain range and timestamp. If they have the same classification, we treat them as one entry and aggregate the frame counts. In the forward recording step, we generate the checkout result. A valid detection threshold is calculated based on the average speed of items in the video. Only consistent classification results appearing in more frames than the threshold are recorded in the final output. Now I'll briefly summarize our experimental results. The setup we used was a i9-9980XE plus two RTX 3090 GPUs. We've achieved a third place finish on the test set A with an F1 score of 0.8254. Collecting and training on more accurate datasets from a real-life deployed platform can improve the performance furthermore. Also, an extension to the project could involve integrating barcode scanning to handle diverse packaging and a wide range of products in retail stores. To conclude, our paper presents a robust pipeline for automated checkout using YOLO V8 and strong sort algorithms. It addresses three challenges that are common in automated retail checkout. I hope our inspiring experience could encourage more young researchers to push the boundaries of innovation. Thank you.
Hi everyone, my name is Arpita Vats. I am a PhD student at Santa Clara University. Today I will be presenting my paper on enhancing retail checkout through deep sort object tracking and YOLO V8 detection. We all know that AI and computer vision technologies are revolutionizing the way we shop and check out in the retail store. Today, I will discuss how AI and computer vision are gaining popularity in the retail industry, the increasing prevalence of self-service option, and specific focus of Track 4 in the 7th AICD Challenge on Automated and Accurate Checkout System. Track 4 AICD Challenge specify the focuses of the computer vision development in the area of retail checkout. In this work, we introduce an innovative framework named Retail Counter, one that incorporates a video in painting alongside detection, tracking, and selection module for accurately reporting the count of unique item observed in the video. Teams were furnished with a training data set comprising both genuine and synthetic images totaling 116K500 item scan along with associated segmentation mask. The testing data set includes numerous video clips with clips featuring one or more complete scanning action performed by customer in the natural manner. Multiple customers participated, each with slightly varied scanning pattern, thereby adding to the complexity of the experiment. A shopping tray was provided for the placement of scanned items in the test scenario, while the camera was positioned overhead and aimed straight down at the checkout counter. Automated checkout system faces various challenges in a real-world scenario that can make the process difficult. Factors such as object occlusion, motion, and item similarity can pose challenge for accurate item recognition and detection. Object occlusion refers to instances where items are partially hidden or obstructed, making it harder for the computer vision system to identify and differentiate them. Motion can introduce an additional complexity as item may move or be repositioned during the checkout process, requiring a robust tracking and detection algorithm. Another challenge is item similarity, where products within a similar appearance or packaging can be challenging to distinguish accurately. The real-world factor requires advanced computer vision techniques to overcome the challenge they present. The introduction of new seasonal product adds another layer of complexity to automated checkout system. Our object detection model was developed using synthetic image generated from a 3D scan object models and their corresponding segmentation masks. Owing to the limitation on external dataset uses, we produced a background that resembled the tray color in the test video and incorporated Gaussian noise. To enrich the training dataset, each image featured up to 3 objects from distinct classes. We successfully employed the photorealistic single image superresolution using a generative adversarial network SR-GAN model to obtain a high-resolution images, resulting in superior training image quality. In total, we generated 130K training images and 20K of validation images. To train our model, we fine-tuned the pre-trained weights of YOLO V8, which is currently acknowledged as the state-of-the-art model for object detection. This is an example of how our dataset looks like. This depicts our framework, which we will be discussing in the next section. As we can see from this diagram, that initially we take the test video, which we extract 60 frames per second, which is followed by a video in painting technique, which helps us remove the outliers, and then we further go for ROI detection, probably, which means like the area of reason that we are interested in, and then we pass it to our detection model, that's YOLO V8, followed by a deep sort tracker and the merge algorithm to get the final output, which includes video ID, class ID, and the frame position that object came into the frame. During training, these products were isolated in the frame and placed in a free space without any other object in close proximity. However, during inference, the model sometimes detected the worker's hand or body as a false positives, even when no products was present in the scene. To tackle this issue, we employed a computer vision technique to first detect human body parts, particularly hands, in the given frame and generate a mask to represent their location. This involved using key point detection method to estimate the position of hands, semantic key points, or identify the hands as object respectively. Subsequently, we applied a flow-guided video in painting technique, which utilizes three trainable modules: flow completion, feature propagation, and content hallucination, to jointly optimize the in-painting process. Our proposed method yielded superior results both qualitatively and quantitatively, outperforming the state-of-art technique and demonstrating promising effectiveness. Since the primary goal of the challenge was to identify objects solely above the white tray, we decided to dynamically identify the bounding box of the tray as our ROI and limit the detection and tracking within that region. To extract the region of interest, we used an OpenCV MOG2 library to extract the background and foreground of the image. In the given frame, the background image was converted to grayscale, and SCAR operator, which is an enhanced version of the Sowell operator, was employed for edge detection. The SCAR operator was executed in both X and Y direction and then combined. The largest rectangle in the frame was used as a region of interest, named as white tray, as depicted in the figure here. The proposed method is a multi-step approach in our proposed system. Frames extracted from the test set A are utilized as an input. The frames undergo pre-processing in the first step, which result in cropped and masked frames. The second steps involve passing the proposed frames into the detection network, which generates location bounding boxes. The frames that have location information are then fed into deep sort and the classification network, producing the tracks with a category score. The final step involves using a merge algorithm to fine-tune the object tracks and select the item output frame for each track. Our primary objective was to assess the effectiveness of each approach, identify the best performing combination. We evaluated the outcome based on the specific metrics such as accuracy, precision, recall, and F1 score. After a thorough evaluation, we found that YOLO V8 detector model paired with a deep sort tracking method yields the best result in our study. This combination achieved an impressive F1 score of 0.817, indicating a high-level accuracy and performance. Our model's performance in the competition is a testament to the rigor of our experimentation process and robustness of our object detection pipeline. To obtain this positive performance, we conducted extensive experimentation using different object detection methods and tracking algorithms. Using this proposed method, we were able to achieve fourth position on the public leaderboard with competitive result, which utilizes YOLO V8 detection and a deep sort tracking algorithm. Thank you.
Hi there, this is Ziqiang Shi from Fujitsu R&D Center, Beijing. Today I will introduce our paper called Check Sort, refined synthetic data combination and optimized sort for automatic retail checkout. This is a joint work with Zongning Liu, Niu Niu, Rujie Niu, Takuma Yamamoto, Xiaoyu Mi, Taisuke Uchida. In this paper, we propose a method called check sort for automatic retail checkout, We demonstrate the check sort on a multi-class product counting and recognition task in track 4 of AICT Challenge 2023. This task aimed to count and identify products as they move along a retail checkout wide tray, which is challenging due to occlusion, similar appearance, or below. And based on the constraints and the training data provided by our organizer, we propose 2 new ideas to solve this task. The first idea is to design controllable synthetic training data generation to bridge the gap between training data and real testing videos as much as possible. The second innovation is to improve the efficiency of the existing sort tracking algorithm by proposing decomposed current feature and dynamic tracklist feature sequence. We design a controllable synthetic data optimization scheme in which 3 hyperparameters need to be adjusted, namely the number of products on the background, the occlusion degree between 2 products, and the scaling of product size. Here, the occlusion degree is represented by IOU, and the scaling size is also within 0 to 1. These 3 parameters affect each other. If you put too many products on the background at one time and keep the original size of the products, the occlusion between the products will inevitably increase. The user can specify the range of these parameters, such as 1 to 6 products, the occlusion degree is less than 0.3, and the zoom size is within 0.15 to generate different training data. We adjust the different hyperparameters, conducted the ablation study, and found that with regard to occlusion, it is best to either have a bound of 0.5 or not have occlusion, and the scale size would be set around 0.5 as much as possible. At this time, the system will achieve better performance. Based on the detection and classification.
Hi everyone, good afternoon. My name is Anudeep and I'm part of Team Scientific. We participated in AICT Challenge on track 4, and today we'll be talking about our paper which is on adaptive ROI with pre-trained models. So our goal in this track is to build a system to automatically recognize products which are present in the ROI during retail checkout. So primarily our methodology consists of 4 major steps. First is the region of interest identification. Then we had a custom training module for object detection, then objects tracking and tracks post-processing. I'll talk about each of these details in the next slides. So this is a high-level detail of our inference pipeline. So as you can see, there are 4 major steps. First, the video frame is passed to ROI identification modules. Here we used pre-trained models like YOLO, V5 and MediaPipe to detect person and hands. And next, this frame is passed to an object detector model. This is basically used to identify the products that are there in the frame. The detections are further passed into a tracking module where object tracking happens for multi-class products using sort tracker. Finally, we have a post-processing module wherein we remove static tracklets and compute the frame number of the product in the ROI, which is the goal of the competition. So what is an ROI? So if you see the image on the right, a person is holding a product in his hands over the tray. So the white tray is the region of interest that we want to identify, and looking at the test videos, we had 2 major observations. One is majority of the times when the person is holding the product with both the hands, so identifying both the hands can serve as an approximation that the product is over the ROI. Second thing is person's bounding box is approximately equal to the width of the ROI. So based on these 2 observations, we built around a heuristic where it uses MediaPipe and YOLO V5 pre-trained models to identify the ROI. So our ROI identification heuristic worked as shown in this slide. We use 2 pre-trained models, so one to identify the person and the other to identify if both hands are present in the frame using MediaPipe model. So if both these criteria are satisfied, we capture three major information points. One is center of the bounding box of the person and width of the bounding box of the person. This is accumulated in a queue of size 30, where we hold only recent 30 frames information. And using that information, we use the formula below to calculate the ROI. Those white lines that you see in the figure are is the ROI that keeps changing for every frame. So for custom training for object detection, we were given product images and masks, but what we did is we created a synthetic object detection data set. So for that we needed some background images. We randomly picked up 3 images from the test set, as you can see below. And so in order to create the detection data set, we randomly selected up to 5 products from this segmentation data set, and we tried to paste them randomly at different positions in the background frames, so that way our synthetic data set looked more general. And that's how we repeated this process till we exhausted all the product images and the masks, and we generated our training data set. You can see some samples on the right. So we have trained a YOLO VFM medium model for 70 epochs using the synthetically generated images that we have created. You can see an image of the small inference on an image shown below. So this is the last part of the module where we have object tracking and some post-processing. For tracking, we've used simple online and real-time tracking with the parameters shown on the slide. And for post-processing, we have two major things. One is to identify static tracklets, and the other is computing the frame number of the product when it is in the ROI. This is essentially the goal of the competition. So for static tracklets identification, we've used the detections across various frames of a tracklet, and we formulated an approach where we compute the difference between each detection center and the mean across the frames. If the delta in both directions is less than or equal to 10, we consider that it's a static tracklet. And for frame number computation, we actually captured the first frame number when the product is in the ROI and the last frame number, and we compute the mean of both and report that as a frame ID for that specific product. Thank you.
What is the next overview? You have 5. Okay, let's jump to
for the Q&A.
Oh, okay, yeah, yeah. So, any questions for the participant team?
Any participants here? I know from Scientific is here. Any other authors of track 4 is here?
Yes, I'm here on the Zoom meeting.
Great. Yep. You have any? We have any question from the audience? Do you have any questions?
Maybe I got questions. So, I think in current settings, there are many variations. The current, they are not using the well-known demand adaptation method. Maybe it's might be like possible levels, something like this one. So, any idea of the using possible levels are the common adaptation method, like maybe the style transfer. So, yeah, any teams has a
okay. So the question is, does any team use any domain adaptation methods to improve their algorithm? Or how do you overcome the domain gap in the data set? If any author is here, you can answer it.
For our team solutions, so I may answer that question. So in our approach, we try to tackle this problem by trying to modify the synthetic data. So our solution is simply that we didn't try to use the deep learning based method directly, but we try to look at the whole data set and then compare it with the starting set. So as we stated in our presentation and the paper, we noticed some some key ideas. That first, if we look at the synthetic data, it actually quite dim. I mean that sum up most of the images are quite dim and a bit darker than the one in the testing set, and only a few cases that is completely bright and we cannot see clearly the detail on the product. So given that, we just simply separate all of those images into two groups. One is really dark and one is really bright, and then we just kind of find like try to balance the brightness inside in each image pass before we try to generate the training data for the object detection. Where in our experiment, we also try to use some denoising and then deblurring and some simple OpenCV method to sharpen the edge of the object, so can make it more clear and try to bring out the detail on the product to be more sharp, so that we can train a better detector model.
Okay, thank you. How about the team from Scientific? Okay. We know that the team from U Toronto is also here. Just want to hear how you address the domain gap in your method.
Yeah, can you hear me?
Yeah, we can hear you.
Yeah, so we kind of used similar fashion to address the domain gap between the synthetic data and the real models and the real data. Basically, we noticed the variance in things like reflectivity, the darkness, the shape, and the placement of the products. So we also kind of saved a bit of training by like putting multiple products randomly on the same like region of the checkout counter, so that the synthetic data kind of resembles the real data more and better in a sense. And also we did like data augmentation on the synthetic data, like the raw synthetic data themselves as well. So like by changing the reflectivity, the size, the orientation, to make the data set more robust and closer to the real world domain.
Yeah, sounds a lot of methods on domain detection.
Yep, thank you. Any other questions from the audience? Yeah. Oh, go ahead. Would you like to come up here so we can use the microphone and people on Zoom can hear you? Yeah.
Thanks. I'm not sure if they were given like a synthetic data by the challenge or they use their own synthetic data. So if they use their own synthetic data, what kinds of techniques they use to generate those synthetic data, or what kinds of tools they use to generate those synthetic data?
Thank you.
That is my question.
Thanks. Okay, so I think the question is for you.
Yeah.
Like, how do you generate the synthetic data?
Yeah, so actually, I think in this year I have released my interface for the auto retail checkout. So it's the synthetic data of the auto retail checkout. I have the and by doing this way, we can generate a variety of the synthetic data. So with generate data set with a good diversity. So yeah.
Thanks. Yeah, so the ANU team, they spend a lot of time generating the synthetic data, and they also have the engine available for teams to, if you are interested, you can feel free to use their GitHub repo. And many teams have found that very useful. Thank you. Any other question? Nope. Okay, then let's go ahead to the presentations of track 5. We have 6 papers for track 5. And then we will have a Q&A for 10 minutes as well.
Hello, everyone. I am very glad to present our work, named an effective motorcycle helmet object detection framework for intelligent traffic safety, which is the track 5 of CVPR Workshop AI City Challenge 2023. I briefly divide the presentation into 4 sections. First of all, I will briefly go through the background and dataset, and then I will introduce our method, including ensemble model, passenger recall module, and category refine module. Moreover, we will show some experiments results. Finally, we will make a conclusion for our method. Detecting violations of motorcycle helmet rules is an important computer vision task that can greatly protect the lives of motorcycle drivers and passengers in traffic accidents. This abnormal event detection problem can be viewed as an image object detection task, which aims to detect the location of the motorcycle driver and passenger in the image and whether they are wearing helmets. The training dataset contains 100 videos and ground truth bounding boxes of motorcycle and motorcycle riders with or without helmets. Each video is 20 seconds duration, recorded at 10 fps. The video resolution is 1920 by 1080. The testing dataset also contains 100 videos. However, the study of such a task poses several challenges. Firstly, it is difficult to accurately detect helmet use under different lighting conditions and camera angles. In traffic monitoring systems, cameras are often located at high altitudes, resulting in low-resolution video. As shown in the table, we count the number of boxes in each category in the given training dataset. The category imbalance problem is very serious, especially the lack of passenger 2 data. Analyzing the dataset, we see that passenger 2 only appears in 2 videos. We visualize the sample. It is observed that the passenger 2 in left is a small child in front of the motorcycle, and the model struggles to classify this instance. On the other hand, the person identified as passenger 2 in right is at the rear of the motorcycle, and this situation is more consistent with our perception. We propose the motorcycle helmet object detection framework to detect motorcycle helmets. The framework includes ensemble model, passenger recall module PRM, category refine module CRM. The object detection approach used in this paper is based on the recent DITAR algorithm. DITAR shows a simpler alternative training mechanism of detection transformer compared to recent detection transformer methods. This alternative enjoys a significant advantage in training efficiency, especially with a short training schedule. We fetch the bounding box of the detected object in each video frame and the corresponding confidence using the detection model. We fine-tune 2 DITAR models with different initialization processes on AI City Challenge dataset. Then, we perform non-max suppression to filter detection boxes that overlap the same objects. The ensemble model can improve the accuracy and robustness of detection model. Passenger recall module is designed via tracking refinement, which greatly improves passenger category recall. We employ the open-source framework Detectron 2 pre-trained on the COCO dataset to obtain the collection of person bounding boxes PI. We obtain the collection of motorcycle bounding boxes MI from data. Calculate IOU between MI and PI. The matched person box is recorded if the same motorcycle box matches to a person box greater or equal to 3. Moreover, we use sort to predict the track of the person box and record the motion direction of the person. We compute the motion direction of each bounding box based on the correlation between consecutive frames. Then, we determine the position of passenger 2 according to the track direction. Passenger 2 is the last person box in the track direction. We further train a binary classification network ResNet on the training set to determine whether a pedestrian is wearing a helmet. We pass the box corresponding to passenger 2 obtained previously to the classification network to determine whether a helmet is present. In the video, we found that as the motor vehicle drives out of the camera, the label predicted by the model will change as the target gradually becomes smaller. Inspired by the idea of tracking, the corresponding box of a track ID should not switch categories during movement. Sort is one of the most typical methods of tracking by detection category. We apply sort to associate the detected objects of different frames in test videos and get the trajectories of motorcycle and person. The trackers use information matrices of the bounding box to assign corresponding tracklets with person and motorcycle detection. Finally, the tracker generates a set tracklets. We compute the frequency of detected classes across all frames. When the frequency of a certain class C is greater than 50% of the total number of detections for the given tracking ID, We consider it to be of class C and refine the class label across all frames accordingly. In the table, we investigate how several components contribute to the final results. We observe that adopting data with ensemble model method outperforms baseline data model by 17.14%. It also appears that the PRM can noticeably improve the performance. Furthermore, our track refinement approach indeed assists with CRM. The results show that post-processing resulting tracks using prior knowledge further enhances the results. We perform tracking visualization on the training set 090 video, and it can be seen that the object prediction category with it 4.2 at frame 12 of figure is still met. But at frame 24 figure B, it is predicted to be P1 no-homid, which is modified to delmet using the proposed CRM strategy. The proposed system is submitted to the Track 5 of AI City Challenge 2023 for evaluation. As shown in table, our method surpasses these methods by a large margin with score 0.8340 and ranks first place among more than 30 teams from all over the world. In this paper, we propose the motorcycle helmet object detection (MHOD) framework to detect motorcycle helmets. The framework employs an object detection network to predict the location and class of all targets in the video. We introduce the passenger recall module, PRM, for tracking refinement to improve passenger category recall, and the category refinement module, CRM, to correct the object categories. The PRM is an extensible module that mainly implements recall for passenger 2 in this paper. We can improve the effectiveness of this framework by developing strategies appropriate for passenger 1 in future work. Thanks for your watching. If you have any questions, please contact us.
Transport system. As you know, motorcycles enjoy widespread use as a favored mode of transportation. However, compared to the cars and other standard vehicles, they provide less protection to riders, making them more vulnerable to accidents. Recognizing this safety challenge, traffic laws mandate that all motorcycle drivers have helmets. This requires not only reduce the risk of injury in case of accidents, but also plays a pivotal role in ensuring the safety of riders on the road. Another critical measure to enforce this mandatory helmet rule is through automated detection of motorcyclists not wearing helmets. Each object within this data is classified using class IDs or labels. This classification allows us to better understand and distinguish between various frames and elements. The pipeline of the framework includes 2 mainstays and 2 processes. Initially, we employ the detector to identify the location of motorbikes along with the drivers and passengers. We then crop the bounding boxes and forward them to the identifier to further information instructions. Obtain information involved detecting motorbike and individually on them, either wearing helmets or not. The framework assigns confidence scores to the information gathered from the detector and identifier stage, allow us to filter out the incorrect objects and retain the correct one for the final outcome. We employ the YOLO VI algorithm in both detector and identifier. Specifically, its largest version at the time we tried the framework, YOLO VI X is the best one. This state-of-the-art object detection model has proven to be highly effective in identifying various objects, including motorbikes within complex environments. To optimize task efficiently, we decided to train our model at a resolution of 1280 using the largest version of YOLO VI. Another reason to choose this resolution is the considerable size of the training dataset, which has been expanded due to augmentation process. This is the diagram of data conversion for training both the detector and identifier. The input of the ground truth of the given dataset with 7 classes and 9020 by 1080 resolutions. We convert them into 2 new datasets, includes 1 class with 9020 by 1080 image size and 7 classes with the cropped image. By carefully modifying the original dataset to produce D2, we examine the impact of image size on both the detector and identifier processes. We change and test the detector model at resolution of 1280, 1536, and 1920. As indicated in Table 1, the results are nearly identical across these resolutions. Consequently, we choose 1280 resolution to enhance the speech performance and reduce the training time. In the case of identifier, we experiment with various image size following a simple model, including 256, 320, 384, 448, 512, and 576. Additionally, to boost the identifier accuracy, we explore the use of example models. As depicted in Table 2, we implemented example models by selecting combinations of different image sizes. We have tested several thresholds for final rank as shown in Figure 5. The visualizations of results with 35 different scenes of 100 videos of the testset. Various scenes has different outside environments, includes overcast, clear sky, haze, and nighttime. The table presents the final rank results for the test sequence, with our results emphasized in the post-test. Thank you for your attention.
Hello everyone, my name is Hui-Chen from VNPT Group. Today I will present our paper Helmet Rule Violation Detection for Motorcyclists using a custom tracking framework and advanced object detection techniques for AICT challenge. As you can see, nowadays motorcycles is the most popular mode of transport and they also cause a lot of problems. The track file of AICT challenge therefore comes to encourage researchers to develop innovative solutions that can effectively detect motorcyclist helmet violation. After experiment on the track file data, we come to a final proposed system which consists of 3 main components: the object detection, the object association, and the port processing for tracking. Regarding the object detection module, there are 2 sub-modules: the helmet detection for motorcyclists to detect all the required classes. The head detection module, on the other hand, detects motorcyclist heads, which will be used as additional information to improve results from the helmet detection module. Both models are based on efficient data, and we use detection techniques to enhance these models' performance, such as test time argumentation, ensemble, pseudo labeling, and weighted books fusion, which allow to combine bounding boxes from different models to achieve the best results. The next module is the object association module. Works as a link which identifies pair of human motor and human head by calculating overlap areas and relative position of the bounding boxes and attach them together. Last but not least, we customize the shop checking module with our 3 additional algorithms: the direction detection, P1, P2 checking, and the attachment algorithm to reassign classes from of motorcyclists using information from past frames. The direction detection algorithm is done by check the coordinate of the motorbike between the current and previous frame to determine its direction is in direction or the out directions. Meanwhile, the P1, P2 checking algorithm decides if P1, P2 presents on the motor simply by counting the human head associated with the motor. As you can see from the figure here, there are 3 heads detected corresponding to the motorbike. So the P2 is present on the motorbike. Finally, the attainment algorithm is illustrated by the pseudocode and the table on the slide. Simply, the algorithm will update human objects class after decided the current scenario whether the P1 or P2 is on the motorbike. From the figure, you could see that there are 3 humans on the motorbike, which is indicated by 3 heads, but there are only human detected by the model, so we apply the transformation in the green box to accurately update the human class from P1 no helmet to P2 no helmet. From the comparison results, it is evident that the post-processing for tracking achieved the highest improvement, about 24% compared to assemble and pseudo-labeling methods. Finally, the combination of the 3 methods, including ensemble, pseudo-labeling, and post-processing for checking, produced the highest accuracies at 69 and 97. In conclusion, our method ranked 3rd place on the public broad of the Checkify AICT Challenge. To know more about us and our products, please visit icenter.ai. Thank you for listening.
Hello everyone, my name is Junming Cai. I'm come from Department of Computer Science, University of Taipei, Taiwan. My topic is video analysis for detecting motorcyclist helmet rule violation. Problem definition. Objective: identify motorcycle and their ride with or without helmet in the 100 testing video. Team will need to identify 7 class. Example of person and motorcycle detection using the Eurovici EOE picture model. Here is a floodlight light and a very bright headlight make a challenge to see the motorcycle and driver clearly. Eurovici EOE picture model detect 4 positive person on the right side of the image. It failed to detect the motorcycle and driver. Our method extract each frame from the 100 training video, convert the ground truth label to the YOLO format, training our models. Extract each frame from the 100 testing video using the 7 class detector to detect the 7 class in the 100 testing video. Obtain the detection result for the 7 class. This figure shows the architecture of Eurovici EOE model. CVPR include a channel attention module, special attention module. Channel attention module focuses on what is meaningful, give an input image. Special attention module focuses on where the informative part of the image is located. This figure shows the architecture of Eurovici EOE and CVPR. We add 3 CVPR here. CVPR separate estimate 1D channel attention and 2D special attention and combine them rather than directly generate the true 3D way. The 2-step process in CVPR is computationally expensive. A simple attention module to address this limitation. It is a simple and parameter-free attention module. It can efficiently produce true 3D way. This figure shows the architecture of Eurovici EOE and simple attention module. We add 3 simple attention modules here. Evaluation result: we achieve MAP scores of 0.6112 0.6389 and 0.422 for the baseline Eurovici EDOE, Eurovici CBAM, and Eurovici Simple AM. This score ranked as 6th for 5th for 4th on the popular leaderboard. Visual result Eurovici EDOE. A motorcycle has been detected as a motorbike, and a driver has not been detected by using Eurovici EDOE. A motorcycle has been detected as a motorbike, and a driver has also been correctly identified as driver helmet by using Eurovici CVPR. A motorcycle was not detected, and a driver has been correctly identified as a driver helmet by using Eurovici Simple Attention Module. Thank you for your attention.
Hello, everyone. Welcome to our presentation on track 5. And track 5 was on helmet violation detection. The title of our work is Real-Time Multi-Class Helmet Violation Detection using Few-Shot Data Sampling Technique and Yellow V8s. This work was done by Armstrong Abua, Ben Wang, Yaredu Jemfi, Elas Baxi from Northwestern University and University of Missouri, Columbia. To begin with, traffic safety is a major concern worldwide, with helmets usage being a key factor in preventing head injuries and fatalities caused by motorcycle accidents. However, helmet usage violation continue to be a significant problem in many countries. In order to detect such violations, various automatic helmet detection systems have been proposed and implemented. The problem with these systems is that they lack the real-time usage, and as such makes it impractical for the purpose that it has to serve. As a matter of fact, the goal of this work is to develop a real-time helmet violation detection system that is robust to varying weather conditions and time of day. To begin with, the data for this competition was provided by the AI City Challenge, which consisted of 100 videos for training and 100 videos for testing. Each video was made up of 20 seconds in length and 10 frames per second, which means that for the training data set, we have over 20,000 frames, right? The data set came with initial annotations, and comparing the initial annotations with the image, we found out that there were some missing annotations which will lead to poor performance of the model if it's not correctly corrected or taken care of. Secondly, there were challenges with time of day and weather conditions. Some videos were foggy, we had 9 videos, and we're not really balancing the data set. And as such, in order to effectively build a very robust model, these things have to be taken into consideration. Based on the challenges in the data sets and the purpose of real-time detection, the study followed two-step process in this methodology. So first, we propose a unique data processing strategy in order to get the best representative data sets that we could train the model on. Second is that we have to use a fast object detection framework to attain the real-time object detection. Now, to the unique data sampling strategy, processing strategy. So the first part of it is a few-shot framework, few-shot frame sampling. Now, this was very essential because the fact that there were some missing frames and all that, and we could not annotate all the frames in order to use. We have to find a strategy that will help us to select the most or the best representative frames of all the 20,000 frames for re-annotation before we train a model. In order to do so, we developed the few-shot frame sampling technique, which follows this step. First, we saw the videos, and the video sorting, it's first getting the background images and using the histogram So we first estimate the background of each video, and we get a histogram for that background. And based on the histogram, we're able to determine whether it is night or day. Then for the day was mixed with the foggy. So in order to be able to determine which one is foggy and day, we use the skewness to be able to estimate what day of foggy it is, whether it's day or foggy. Then we have an algorithm that selects the frame rate to sample from these videos. Next was to make sure that the frames that we are trying to annotate do not have so much similarities. So we have to do semantic scan, which help us to be able to identify frames that are similar semantically, so that we'll have to take the best representative frame for annotation to reduce our tax in re-annotating on the data set to that, which was very helpful for us. The second part of our data processing strategy was data augmentation, and we use 6 key data augmentation strategies: image flipping, rotation, scaling, cropping, blurring, color manipulation. And these are examples of some of the augmentation strategies that we use. So flip and blur have been shown in the slide. Next is our fast object detection model. In this study, we used the YOLO detection as you only look once model, but we consider 5 different YOLO model architectures. We consider the YOLO v5, YOLO v7, and YOLO v8. So these are the various hyperparameters that were tuned. These hyperparameters were gotten using genetic algorithm, and these were the final hyperparameters that were used to train these various models. The model results on our validation data set, when we split our data into training and validation, we realized that the YOLO v8 was outperforming all other models when we added test time augmentation. So YOLO v8 data test augmentation outperformed both YOLO v7 and YOLO v5. But when we added test time augmentation to both YOLO v7 and YOLO v5 and YOLO v8, we saw some great improvement in the results. Likewise, we did the same for the test data sets that were provided by the competition, and realized that using YOLO v8 and test time augmentation gave us the best result. We also compared the frames per second for the various models. So even though YOLO v8 was given as the best MAP, that's a mean average precision, which was a metrics that was used to evaluate the model, the FPS was around 95, right? FPS, and it's also comparable to the other models, right? So we settled on this since we're getting the best MAP and also having a fast model. So these are some of the detections from our model. And on the leaderboard, we are 7th on the leaderboard. Thank you very much.
Hi everyone, I'm Bo-Xun Wang. I'm glad to introduce our work on Track 5 in AICD Challenge, PRB FPM Plus Video Analytics for Enforcing Motorcycle Helmet Law. The Track 5 Challenge tries to detect the motorcycle driver and passenger whether wearing a helmet or not. Motorcycles are one of the most common transportation in developing countries. It provides less protection to a driver when compared to other vehicles. Wearing the helmet is the minimum protection and is also mandated by the traffic rules. Benefit from the detection model. These tags can automatically be detected without heavy labor. However, there are still some problems by directly applied to this task. One of the problems we try to improve is the classification alignment problem. Due to the detection model detecting the video frame by frame independently, the same object may get different classified results in different frames. To solve this problem, we propose the two-stage method. This is our workflow. It contains 2 steps. The first step uses the detection model to find the object, and the second step, based on the object found by the detection model, uses the tracking model to match the object across the frame to align the classification result. For the detection model, we compare to the other famous model in recent years, and we choose to improve PRB-FPN as PRB-FPN Plus as our model. A simple quality comparison is shown below. The YOLO V7X6E gets the wrong classified result on a small and unclear object. However, our PRB-FPN Plus can correctly detect and classify the object with a tighter bounding box. As the figure shows, the YOLO V7E6E detects the motorcycle as the car, and PRB-FPN Plus correctly detects the motorcycle. The quantity result will show later. We also find out that our model can detect the object and that is excluded in the bounding box rule. This might confuse the model when detecting and classifying the object. So we use the pseudo-label technique to reduce this problem. The pseudo-label is created by combining ground truth and detection results from our model. By doing so, the model will not confuse to the object that is not included in the label. Next, we use similarity learning-based tracker as our tracking model. The smell track is composed of two modules. The first module, similarity learning module, calculates the similarity score of the object across frames. It gives score to decide whether the two objects in different frames is the same thing. The other module similarity match cascade match the object by the similarity score. By doing so, we align the classification result across different frames. Next, we will show some results. The table shows the comparison between our detection model and other works. Our PRB-FPN Plus gives the competitive results with other models. The effect of the pseudo-label shows in the table. Although the pseudo-labels gets higher result in the training set, but it gets worse result on the testing set. The last one shows the leaderboard. Our methods gets the rank 8 on the leaderboard. Thanks for listening.
Okay, so that concludes all the talk for the track 5. I know many of the authors are here. Let's see if Pranamesh or Sanjita is there. Do you want to host the Q&A section?
Yeah. Hello, Thomas. I'm here, and I think Sanjita is also here. Yeah. Yeah.
Yeah. Let the authors know if you have any question or the audience have any question. I will leave it to you. Thank you.
Yeah. Maybe just from my side, I will start off with the any teams. We have seen that the teams have used an ensemble of approaches for getting a better detection. So if any team can highlight on how does it impact the real-time processing, because since this will be applied for real-time CCTV location, so real-time processing speeds may be helpful.
Yep. So the question is like, what method for detection can it be applied for real-time processing? So what's the performance of your detection algorithm? Any author would like to come up here? We have authors from VMPT, from Yangming, Xiaotong, and Yu Taipei. Sorry? Yeah. Please come up. Please come up. You can enter through the microphone. Yeah, please come up here. Yeah, please use the microphone. Okay, so we are team 55, and our PRBF PM Plus can detect the model in real time. Yeah, and also we only use the weight for detection model and add the tracking method. So the whole system, the workflow can inference in real time. Yeah. Okay. Pranamish, I think that's the other answering the question. Do you have any other questions?
Maybe, yeah, I will also ask another question. So if the teams have seen the data set, so there were different camera angles, something like from the front, from the back, and as quite a few teams have also focused on passenger 2 or passenger 1 detection based on occlusions or so. So if some teams can highlight on what were the thoughts on different camera angles, how does that help or maybe doesn't help a particular angle in having a better detection or decrease in detection because of some camera angles. If the teams have looked into those and if they can highlight it, they have some thoughts.
So you means the different camera angles detection rate?
Yeah, something like that, or if some visual results, if it has shown like if some angles have been better in detection rather than some other angles, maybe that can be also taken up by the smart city officials, like which camera angle they should put to have a better detection of the helmet violation.
Okay, so that's why we use the shooter label to enhance our detection rate, because when we if there's a new environment or different angles image, we will use the shooter label method to increase our detection rate, so that we can successfully to detect the unseen environment videos. So that's why we propose this shooter label to enhance our detectors.
Okay, yeah.
Yes.
Thank you very much. Yeah. So Thomas, any other questions if there is from audience or so we can take up?
Yeah, if you have any question, you can feel free to use the chat, or you can feel free to unmute and let people know if you have any question. Or we have audience have any question.
Sorry, we thought the evaluation system is wrong and unfair, because you can find more positive and the score will be high. So we thought maybe TP and the TP true positive and the false positive may be wrong place. Yeah. So I think the rank maybe should be, yeah. We found that the evaluation system may be not correct. Yeah.
Yeah. Thank you. Yeah, Prathamesh, do you want to take that, or Sanjita?
If I understand correctly, so it was regarding the evaluation thing, and we have rectified the evaluation script and to highlight the correct MAP score, and I think so. Currently, the evaluation leaderboard is also showing based on the corrected ones. So all the submissions that were done have been basically re-evaluated using the corrected script. We do understand that maybe if the teams had the prior information, they could have further improved on their accuracies based on that, and we actually apologize for that. But I think the current one that we have, the leaderboard is based on the correct script.
Yeah, thank you, Prathamesh. So the idea is that we have already re-evaluated. So we have updated the evaluation script.
For the case more positive than the score with I think it's unfair. Yeah.
Oh, yep. The question is that they feel when there is more false positive, the score get higher, which is an issue of the previous evaluation script. We have already corrected the error, and we
Really correct.
yeah we have updated the leaderboard, and so for the awards assignment, we will make sure that we use the correct script and based on the corrected score. Yeah. Yeah, thank you for raising the issue, and so in the afternoon we will show the corrected leaderboard during the award ceremony, and if you have any questions or you want to verify anything, just let us know. We are happy to address that. Ming-Ching, do you want to add? Yeah.
So hi, this is Ming-Ching. Yeah, so I'm just because I talked to many people and I'm also collaborating with these teams, right? So what I first found out is that there's a strange things that for some case that they know, they are more detected true positives. It seems like the evaluation code has problem bug that makes up the true positive and false positive, right? So and then I think we have an organization, but I'm not part of the evaluation part, but the evaluation team has fixed the evaluation code, right? And then I think one important thing is because the team is looking at the submitted results and then they go back to tune their internal parameters, right? So what they believe to be better could produce the worst scores, right? So it would be fair that when we evaluate all the things, we evaluate all the submitted results, because maybe the result that looks bad in the beginning could be better in the end, right? Because the script is wrong, so they tune the parameter in a different way, maybe in the wrong way, right? So that's why I think we want that's the team's feedback on this challenge.
Right. Cool. Yeah. So Pranamesh, maybe or David, just to confirm that all the successful submissions of track 5 are re-evaluated, not just the latest result or not just the highest score.
So we have re-evaluated all the submissions of all the teams that they have submitted throughout the challenge. And based on that, whichever score came out to be the top for each of the teams, that we have taken as a final score. So it's not the final submission that was made by the team or the final one that came out at the end of the old evaluation. So it's based on all the evaluations, all the submissions of all the teams. And the best of each team has been taken as their MEP, final MEP.
Okay, did that answer your question, Ming-Ching and Professor? Okay, yeah, if you have any question or anything, we can discuss after offline. Yep.
Yeah.
Okay, thank you. Let's clap again for all the participants of track 5. Yeah, this is a new track this year, and we thank you for your participation and for your support. Finally, we have
Hello, everyone. My name is Mukhtar Al-Qacha.
So finally, we have the presentations of 4 independent researchers. So some of them proposed new data sets. Some of them, they used like a vehicle reality data set from previous years. And then they have newly proposed methods. So let's hear the final 4 presentations. And then we have a Q&A for them as well. So Ming-Ching, will be able to host this Q&A? Yeah, both of us can. Okay, now let's get started.
I'm an assistant professor at United Arab Emirates University. Today, I'm gonna present our fisheye 8K dataset for 2D road object detection task. Why fisheye camera? Because of its 2 major benefits. Wider and more comprehensive view of the surrounding environment. We can see that single fisheye camera can cover the whole intersections on these pictures. The second benefit is to remove the dewarping steps for the object detection task. In this table, we see road object detection datasets. Only 2 of them are fisheye camera based, One of them is our fisheye 8K, the other is Foodscape. But Woodscape is for self-driving car. Our fisheye 8K dataset consists of 22 videos from 18 cameras, and it has 8,000 images with resolution of 1080 by 1080, and 5 classes: pedestrian, bike, car, truck, and bus, and it has 157K bounding boxes. It has 3 scales: small, medium, large, and we benchmarked on the latest YOLO variations. From this picture, we see how the images are split into training set and the test set. To reduce the bias, all the images of the particular camera into one of the sets. For example, camera 3 videos are only belong to training set. Also, we try to keep 70-30 ratio for each class's bounding boxes. In terms of bounding boxes size, most of the bounding boxes belong to the small category because of the fisheye camera spherical view. In this table, we show our benchmarking results. YOLO variations are trained on DGX1 supercomputer for 250 epochs. For the 640, YOLO V8 performed the best in terms of MAP 0.5, but it performed the worst in terms of inference time. On the contrary, for the input size 1280, YOLO R P6 performed the best on the MAP 0.5 and also for the inference time. Here we see that two best models for input size 640 and 1280. For 640, car and pedestrian classes perform the best and the worst, and for 1280, input size, bus and pedestrian perform the worst and the best. On the right hand side, we can see the normalized confusion matrices for each models, and we can clearly see both models have very high false positives and high false negatives for the bike class. In this slide, we show some hard cases, false negatives and false positives. Here we see some scooters are not detected on the sideways, and here we see two partially visible cars are not detected. And road participants such as truck, standing pedestrian, and the bus, they are not detected at all. On the bottom side, we see some examples of false positives where the signs and this pillar misclassified as pedestrian, and this yellow building behind that car is classified as bus. Horizontal sign is misclassified as bike. On the right hand side, we see the examples of misclassifications between the classes. As these two pedestrians walk away from the camera, they are misclassified as bikes instead of pedestrian. We present our demo here. Both models are COCO pre-trained models. The left-hand side is fine-tuned on fisheye 8K. Thank you for your time. I'm ready for the Q&A.
I'm honored to present this paper titled Nordic Vehicle Dataset (NVD), Performance of Vehicle Detectors Using Newly Captured NVD from UAV in Different Snowy Weather Conditions, which is accepted in CVPR 2023 AI City Challenge Workshop. This work is a joint effort between the Machine Learning Group at Luleå University of Technology and a company called SmartPlace. This company is the main provider of the drone that is being used to capture this data. The work is inspired by a problem generated from the region that we are living in, north of Sweden, where we are experiencing harsh weather for almost the whole year. We ask ourselves how the state-of-the-art detectors, like YOLO and others, can detect and track vehicles in such a kind of weather. To address this concern, we first conduct a literature review to find all the UAV datasets that being used in the current ongoing research work. As an example of these datasets, VIS drone, UAV project, UAV vehicle detection dataset, MIMOS drone dataset, UAV videos for traffic, and many others. 4 criteria were set to conduct this systematic literature review and find the relevant dataset. The criteria are: the data should be captured from UAV, it should contain of vehicles, the location should be generic, and it should provide varying weather conditions. None of the data that we search for achieving all of these 4 criteria except the MVD data that we proposed. The main steps to produce the MVD dataset can be summarized as data capturing, data preparation, and data description. For the data capturing, real drones, which is produced by SmartPlane, was used to capture the data. The main specification of this drone are as follows. The wingspan is 120 centimeters. Takeoff weight 1.2 kg. The cruise speed is 13 meters per second. The sensor is called Eximor RS CMOS. The lens 7.9 millimeters. The video recording, it can record the videos with a very high resolutions reach to 1080 and 4K, and it can provide 25 frames per second. For the static images, it has static images with a resolution of 16 megapixels. For the data preparation, we have 3 main parts. In the data annotation, the open source tools called GVAD was used to annotate the data. While for the data augmentation, you can refer to the full descriptions in the shared code at GitHub. But both the augmentation library and the embedded augmentation features in YOLO model were tested and evaluated. As the height values are not provided for all the recorded videos, proposed height estimation methods was used to estimate the height of the flying drone. The main characteristic of the MVD data can be summarized by: we collect 22 videos of aerial footage captured in the north of Sweden during the winter time. It consists of 26,313 annotated cars. The flight altitudes range from 120 to 250 meters. The varying snow cover, and we have also varying cloud cover. The GSD, which is the ground sample distance or pixel size, range from 11.1 till 20.2 centimeter. The resolution of the videos varies from 1920 times 1080 till 3840 times 2160. These are some of the samples that we collect, and as we can see in the first image, we have an altitude of 250 and the snow cover from 5 to 10, and the cloud cover, it's clear, while in the last image, the altitude is around 150, the snow cover from 0 to 1 centimeter, and the cloud cover is overcast. The experimental results, we try to test the latest YOLO model, which is V5, V5S, and V8S, with and without the augmentations, and also the further RCNN is used for evaluations. Also, you can refer to the paper, and for the sake of the time, you can find more experimental results where we collect different UAV datasets and run them over different models, including the MVD data. As a conclusion, we can summarize it by this statement. There is a crucial need for current research conducted for vehicle detection to utilize and benchmark such challenging data collected in difficult situations. Thank you so much.
Present our work titled Robust and Scalable Vehicle Re-Identification via Self-Supervision. First, I would like to acknowledge the contributions of our sponsor. Our work tackles the problem of vehicle re-identification, so I would like to give you a little background on this task. Here, you're asked whether you have seen a particular vehicle image. And of course, this question is being asked in the context of the gallery that you have. Now, in order to respond to this question, you need to compute the similarity between this image and all the images in your gallery, and then rank your gallery accordingly. If you are doing this correctly, then the top result in the ranked gallery should share the same identity as this image. Therefore, the objective of vehicle re-ID is to identify all images of a particular vehicle identity in a large gallery set composed of images captured by a network of traffic cameras at different locations, different time, and of course different weather condition. If you think about this task can get quite challenging because there are different vehicle identities that are of same make, model, year, and even color. On the other hand, a given vehicle can appear quite different depending on the viewpoint and the orientation. Therefore, we need a vehicle reality model to learn to discriminate between similar looking vehicles. It also needs to learn minute details in order to associate different images that belong to the same vehicle identity. And of course, we need to make sure that this vehicle reality model does not rely on the ample fine vehicle annotations. Based on this, a self-supervised approach can be more desirable. Additionally, since the target of vehicle re-identification is for large-scale applications, for example, in a city scale, we need to make sure that our vehicle re-ID model is computationally efficient. For this goal, we propose our approach self-supervised and boosted vehicle re-identification, or in short SSPVER, which has two different heads during the training to not only satisfy standard re-ID objectives, but also establish local to global correspondence. The re-identification head has the standard classification and triplet loss functions. Different from contrastive loss, for self-supervision, we use knowledge distillation and self-training, where we generate global and local view sets and then ask a student model to match the predictions of a teacher network. This formulation results in a consistent performance improvements across different choices of backbone networks and re-ID benchmarks. In terms of city-scale multi-camera tracking accuracy, SSPVER improves performance compared to a baseline model which only uses the standard re-ID objectives by a considerable margin. And this performance improvement obtained by maintaining the same computational complexity. Further investigation shows that SSPVER results in feature compactness through establishing local to global correspondence. Comparison with state-of-the-art models revealed that SSPVER outperforms all alternatives except for the HRCN method for the re-ID metrics. However, studying efficiency measures show that HRCN requires significant computation budget to achieve the performance. Therefore, in the accuracy versus efficiency trade-off, SSPVER is the state-of-the-art approach.
Hello to everyone. My name is Carlos Gomez Gulamo, PhD student at the University of Alcalá in Spain in the Orbisave Research Group. I want to present to you this work titled Improving Multi-Agent Motion Prediction with Heuristic Goals and Motion Refinement, focused on the field of autonomous driving and artificial intelligence. Now let's go with some motivation. Efficient motion prediction is one of the key and most difficult challenges in reaching full self-driving autonomy. Most state-of-the-art methods do not focus on efficiency, but only on performance, like the final displacement error. In that sense, HTML rasterization and vectorization can be very expensive, but at the same time, only considering past trajectories is not representative enough to obtain optimal results. Moreover, predicting the agents without considering their nature, such as their type or preliminary intentions, may not be optimal. Finally, sheer understanding, considering lane geometry, semantic, and topological information can save tons of unnecessary computational resources, such as operations per seconds or parameters. Regarding some relevant state-of-the-art works, LaneGCM proposes a lane graph from raw map data to explicitly preserve the map structure as well as aftermap interactions. On the other hand, GraphPress proposes an only social method, specifically designed to effectively model interactions among agents without relying on map information. Finally, built upon the success of LaneGCM, GANNet models goal areas rather than the exact goal coordinates as preconditions for trajectory prediction. In this work, we present an open source method on a well-established Argover 2 motion forecasting benchmark, which makes use of potential mechanisms, graph neural networks, heuristic proposals as preliminary map information, and a motion refinement module to further improve temporal consistency. In that sense, we use fewer operations and parameters than other state-of-the-art models. This is our pipeline. First, we compute some heuristic proposals as preliminary map information that will be concatenated to the agent's displacement with the corresponding metadata, such as the agent and length type, and the topological information of the boundaries. This information will be processed by a transformer encoder. On the other hand, bits map information is processed by a LaneGCM module. Then, an agent map fusion cycle is going to merge the physical and social features, where we replace the agent attention block originally proposed by LaneGCM with a crystal graph convolutional network to enhance agents' interactions with these operations. Moreover, in a similar way to GANNet, we estimate tip calls and extract semantically features around them, being these tip contexts aggregated to the agents, interacting again to each other with another crystal GCM. Finally, a residual decoder calculates some preliminary multimodal predictions, and a motion refinement module, taking into account the past observations, preliminary prediction, and deep context before the decoded stage, calculates the final trajectories. Here we may observe some examples of input data and heuristic proposals for the target autonomous driving agent and the refinement module, where the goal is to further reduce the offset between the ground truth and predicted trajectory. In this evaluation study using the validation set, we may observe the huge influence of the physical context in terms of accuracy and inference time. We replace the originally proposed ActorNet with an efficient transformer encoder that considers the past trajectories, heuristic proposals, and agents metadata, as well as replace the spatial attention blocks with several efficient crystal GCMs blocks. Our final proposal has a latent size of 128, achieving a state-of-the-art prediction performance, and reducing the number of parameters and inference time by 21 and 41% respectively. On the other hand, in this table we can appreciate how our best model generalizes well in unknown traffic scenarios of the test set, both in the unimodal and multimodal cases. Here we can observe some qualitative results in challenging traffic situations, where the target agent can be a vehicle or a pedestrian, as well as initially stationary or moving. We can appreciate how the multimodal predictions are correctly computed, taking into account different directions or velocity profiles. As conclusions, we propose an open source model that integrates attention mechanisms, GNNs, heuristic lane proposals, and motion refinement for efficient signal understanding, achieving state-of-the-art results in terms of accuracy with less computational resources. Regarding the future works, we are working on including a map-adaptive lane loss to improve the diversity in the future prediction, as well as exploring the concept of knowledge distillation as a preliminary stage before implementing the model in our autonomous electric vehicle. Finally, thank you for your attention and question and answering in the poster session.
Thank you very much for all the presentations of the independent researchers. Now we can open the ground for Q&A from everyone. You have a question? You want to come up?
I got a question for the UAV dataset. I read a lot of papers also from the remote sensoring, and they're very similar to the UAV dataset. So could you please tell the difference between these two datasets, the remote sensoring and the UAV?
Oh, you mean the NVD data?
From the satellite, remote sensoring?
Remote sensoring, yeah. Okay. Are the authors here that can answer this question? The author of the fish eye, right? Fish eye, right? Fish eye, we have the author here. You want to come up to the mic? I'm probably also, yes. So, this is collected from UAV, right? So from remote sensing, this
attitude is much higher, right? So from remote sensing, you cannot see the specific cars and people's face, right? So, but this one, you can, this is at a scale of, you can detect like the motorbikes, right? So I think even for people wearing a helmet, that kind of thing, you can still see it. So it's a big difference, I mean, the attitude and also viewing angle. But most importantly, this one, the challenge is the fisheye acquisition, right? So the problem is, do you rectify the fisheye to become planar, then you do all the things just as if you do the satellite, which is like almost perspective, right? But that's the research question. Do you do rectification explicitly or implicitly? So what we propose is sort of implicitly, right? So we try to learn the feature without rectifying in the fisheye, and we show that it's sort of, it might work better, right? Because after you rectify the fisheye, what will happen? You will have this very strange contraction of pixels, right? You lose information when you make the the constant common filter kind of thing works, right? But the good thing is that you have constant common filter to apply for the dynamic model to do a better prediction. But also you lose features. Yeah.
Okay, Ying, I also have a question. So the question is, how long does it take for you, and also for the MVD dataset? We have 2 dataset papers. So how long does it take for you to maybe annotate every frame, and how many manpower do you need for labeling this scale dataset? Do you use any method to accelerate the annotation?
It's so the main team who work on this is the Mongolian team. Right.
Hi.
Yeah, can you?
Hi.
Can you answer this question? I think they spent a lot of tremendous amount of time to
Yes. Thank you very much. Yeah, thank you very much for the question. And the manpower, like 2 people, but of course with the help of other people, they have spent almost a year and a half, because we went through 3 different 3 steps, because we first labeled and then found out some problems, and then again we did one more, then again found out another problem, and then finally we in the final round we made it the final version. And unfortunately we didn't use any labeling smart tools to make things accelerate. We did it all old school.
I see. Thank you. How about the second paper? Are the authors here or on Zoom? The MVD dataset. If not, I also have a couple questions for the two papers. One paper on vehicle reality and one paper for vehicle prediction. So yeah, because in the AICD challenge, we are interested in vehicle-based problems and people-based problems, and both problems are equally important. So we want to know, for this kind of reality method and the prediction of trajectory, is it possible to apply it to the human-based problems, and what kind of modification is needed for this kind of application? Oh, yeah, please. So one of the authors here can come to answer this.
So actually, do you mean about applying trajectory prediction to pedestrians?
Yeah, to pedestrians.
Yes, actually, the original methods for trajectory prediction based on deep learning were for pedestrian prediction. For example, social LSTM, social GAN, SOFI, they took into account the physical constraints and social constraints. And then the vehicle motion prediction models, they applied these social interactions. For example, social LSTM, they compute social attention with first with LSTM, they extract the motion features of the past trajectories, and then they apply spatial attention to model the interactions. So actually that's pretty important. I think the main difference between vehicle motion prediction and pedestrian motion prediction is maybe the constraints, because the constraints and maybe the pedestrians are more random because they can turn in 0.7 seconds.
Unconstrained.
Yeah, it's more unconstrained. For example, for vehicles, I think in terms of terms, it's not so difficult, but in terms of different velocity profiles, it's way more difficult because a pedestrian is going to have maybe a constant velocity or maybe a low acceleration, but a vehicle can have sudden brakes or accelerations, and this is very, very difficult, even if they are driving in highways.
I see. Thank you for your answer.
Thank you so much.
Okay. Yep. So that concludes all of the presentation. Let's clap again for all the presenters, all the authors, and also thanks to Professor Minqing Chang and Professor Liang Zheng for the tremendous effort to review the papers. And we have such a short period of time to review so many papers. We are having a record-breaking number of submissions this year, and we just very appreciate all your support and all your interest in our workshop. So right now it is 2:53 p.m. We will have a break for 15 minutes. So let's come back at 3:10 p.m. and then we will have a panel discussion on. We will have the first 30 minutes on ethical AI, and then the next 30 minutes will be talking about synthetic data generation. So the panel discussion, we will have Professor Minqing Chang, Professor Liang Zheng, me, and Shuo Wang, also from NVIDIA, and also Professor David Anastasiou. So 5 of us will be discussing on these topics. And after that, we will have an award ceremony, and we will have a poster session as well. So now let's take a break.
This is my first poster. So should I go to the building and then
You can set it up now, or you can set it up at 4:30 when we finish everything.
Okay, I think that's it because I mean, you need to have the poster stuck in the wall.
You can do it now. We can, because it's already after 1:30. We can only put up the poster after 1:30.
Okay.
Your poster is already there, or you will have
No, my poster is there.
We can go there together at 1:30. At 4:30 p.m. 4:30 p.m.
Okay.
And then we can put up the poster. We only have 1 hour poster session, so we can go there afterwards together. But you don't have to go now. Okay. Hi, everyone. Let me confirm, is David and Shaw online now?
I'm here.
Okay, David, good to hear. How about Shaw?
Hey, Thomas. Hey, David. Hopefully you can hear me.
Great. Yep, we have Professor Liang Zheng here with me, and let's wait for Mingqing to come into the room and we can get started. Okay, anyway, I think we should get started because, you know, we have a award ceremony, and after that, we want to have more time for the posters, for people to socialize and understand each other's work. So let's get started. So we have a panel discussion again. The presenters are me and Shaw from NVIDIA, and we also have Professor Mingqing Chang from the University of Albany, SUNY, and also Professor Liang Zheng from Australian National University. We also have Professor David Anastasiou from Santa Clara University. So it's an honor to have all of us here to discuss on this important topic. First topic, ethical AI. As you know, every year we start this AI City Challenge workshop. We have a lot of comments from the CVPR workshop committee about ethical AI. They want us to specifically discuss the ethical AI issue during the workshop because we address a lot of problem in terms of tracking, in terms of object detection, of human and also for vehicles, and those include a lot of privacy concerned data, for example, like human face and also like vehicle license plates. So I think the first question I have for all of us, you know, is that so how do we address this in terms of our data collection? And also, what do you think is the future direction that we want to pursue to preserve the privacy of all the users and participants? How about Shaw? And do you want to share some of your thoughts?
Yeah, I can start, like, for example, using track 4 as an example. So the smart retail track. So when we do the data collection, considering the ethical AI, first is we want so ethical AI is not only about the privacy, also we want the data to be like diverse. So during the track 4 data collection, like first, we are trying to mimic what's the actual retail look like. So we find a actual counter. We go to the like cafeteria, checkout area of NVIDIA, and we ask like 4 of our employees as actors. So each of us like perform with the script in mind that we are actually buying items from the cafeteria. And also considering the privacy. So initially we are like placing like more than one cameras with different camera angles. So in the actual data set of the challenge, you only see one camera angle, like looking from top down. Previously, we are thinking different like composition of the challenge. So we are placing more than one camera. We're placing also 2 cameras at a lower angle, looking upwards from which you can see the face of the customer doing the checkout. Also, maybe the person waiting next in line. So after considering, like, since we're training, we're asking the team to train detection models from various angles of 3D built objects. So we're thinking one camera angle probably could work. Thus, we are removing all other camera angles that can have your face exposed. As part of the effort, we're like kind of addressing the privacy. Also, from like the track one multi-camera tracking, we have been using this city scale dataset for a couple of years, and during those vehicle detection tasks, we also like scan through all the videos and make sure any like pedestrian being captured there, either we avoid those clips or we kind of need to mask their faces to protect the privacy. Thomas?
Yep, thank you. I think we can discuss track by track. Let's continue with the discussion of track 4. I think Professor Liang Zheng has also spent a lot of time helping on the data collection of track 4. They used a lot of synthetic data to address these kind of issues. So maybe Professor Liang Zheng can share some of his thoughts.
Thanks, Thomas. Yeah, I think ethical concerns are very important. So one of the things that we've been doing is to use synthetic data for training. So we've shown basically that using synthetic data for training, we also have, at CVPR, we have some workshops on synthetic data for vision. And the idea is that in some applications, synthetic data could very well replace real-world data. And we've shown that using our synthetic data in retail, in a retail track 4, basically the performance has been very, very competitive. So we've developed some optimization procedure. So how to generate those synthetic data in the middle, compare with the real test data on the middle bottom. So basically, we found that using synthetic data in those virtual platforms such as Unity or PyTorch 3D would give us a much higher freedom in curate the synthetic data such that the resulting training set is really good and gives us really competitive test performance. So also in previous years, AICP challenge, we also used the synthetic data for vehicle re-identification and vehicle tracking. So those trials proved quite effective and successful. So I guess using synthetic data is one of the ways to alleviate these privacy concerns. Also, the community has the privacy preserving AI models where people are studying how to not let those attackers access the gradients of during model training and reconstruct those images or videos. So these are also trials in the community to alleviate to the privacy ethical concerns. So I guess so for AICT workshop, we are endeavoring to resolve these concerns, and I think so far we are doing very well. And we also, but we also, at all times, we need feedback from our audience, from our organizers to further improve our practice. So this is what I want to share. Thomas, I finished. Yeah. Thanks.
Cool. Thank you, Professor Liang Zheng. Okay, and also we have Ming Qing. So maybe you could also share your thoughts, and especially because you are also a participant of track 5 of the detecting the violation of helmet rule. So maybe from your standpoint, what do you think the privacy concerns is addressed in this data set, and also from your own collected data set, how do you address the privacy concerns?
Okay, thanks everyone. When I try planning about my this panel discussion talk, I think about at a higher umbrella of what we should do, or the field should address. I'm looking at this many aspects of AI, right? So overall, it could be the trustworthiness of AI. I think that's the overall umbrella, which we consider different aspects of AI: the privacy, the security, the fairness, the robustness, etc. of AI, right? So I'm thinking that the privacy is just one of the the components we considered, right? For example, right? So if you are limited to access the private data, and also privacy itself has multiple definitions. I mean, for different problems, say for face identity, right? So what you want from privacy is that you want the samples to be some kind of human face, not Godzilla, right? Now you have to be a human face, but you don't want that face to be recognizable to be you or me, right? So that's the goal, right? But for privacy, or maybe say IP infringement for in the industry, right? For example, like industrial inspection, I'm giving you some parts that you want to protect the privacy, to say that this is not the next generation of Apple iPhone. That's a whole different kind of privacy, right? So maybe we should not call it privacy, right? Because it's not just not identifiable for the parts. It has to. You cannot make the thing like identifiable if it's Samsung or iPhone, right? So it's different than the face case, because we want to know the thing that's identifiable as a face. No, it's recognizable as a face, but not identifiable, right? So take an analogy, right? If you are doing this NIST, I want some figure to be recognizable as a number, but not this number, not this sample, right? So this particular image, right? So this different level of privacy definitions, right? So they are differential privacy, they are federated learning, right? So if you want to do cross-silo, cross-device federated learning, you can apply differential privacy, right? So you can do SMC, you can do an homomorphic encryption, right? You have a lot of approaches to protect the privacy. Depends on how much level we want to protect. Okay, so I mean, what I'm trying to say is like at a high level, right? I mean, if we want to, it also depends on the amount of required data to train a suitable model. I mean, look at data, right? So I think the consensus these days is if you have enough data, if you have enough computational power, then you can solve the problem, no problem, right? But the reality is we always do not have enough data or labeling. That's why we have transfer learning, right? So we have this pre-training, right? Foundation model pre-training, right? So we have this concept drift, right? So we have this kind of ideas that limit. We have this one few-shot learning, right? So all these concepts come in at a case that we do not want to apply a perfect supervised learning. We want to leverage something that you can pre-train, you can do a little bit of fine-tune or adaptation, then it has to work, right? So all this there's also continuous learning, right? So this kind of developments from IC, they are actually different aspects of the problem that is tangled together. The problem is the foundation of the machine learning assumption, right? So because the machine learning is the black box setting. I mean, so far the deep learning are set this way that you have to train your model, and at a test time you have to expand to your test sample, right? So what did I say? Fairness, that's another aspect, right? So fairness concerns about, right? So is your model fair to say recognize the human face of different genders, races, or etc. Right? So from our perspective, I think it's the similar things, right? So this comes in the case of a non-IID data distribution, right? So you might have very few cases. One, so for example, in medical imaging, right? So you might have very few specific cancer cases, but you have a lot of normal people, right? So how do you do data augmentation, data hallucination? How do you do that kind of thing to ensure that you have enough model data to train your model? You also try to improve your model such that you can maybe naturally can handle this non-IID kind of distribution or training or testing, right? So what do I have? Fairness, security, right? So security, so it's also tightly tangled with this privacy issue, right? So membership attack, right? So that's one kind of adversarial attack and membership attacks are, I think, the two kinds of security concerns that are actually related to privacy, right? So security is more of that. I mean, sometimes security is more involved in, can I steal your model by a gradient inversion attack, right? So that's to steal your model. But on the other hand, if I'm trying to protect my data, then the membership inference attack or the sample hallucination kind of recovery kind of attack can get your data from your model, right? So this is like protection. So how do you do this? Differential privacy or some kind of mechanisms, encoding, decoding, and then you try to add your tricks such that you can somehow share some essence or some digest of your data instead of sharing the raw data itself, right? So you try to design this mechanism to make that happen, right? So the approach could be viewed as, again, right, the data side, the model design side, right? So from the data side, you can say synthetic data, hallucination of data can, if you use that, you can prove that that works, then that protects privacy, right? That's data side. Also from the model side, differential privacy, right? So I can ensure that you cannot invert the gradient to get my data samples out, then that protects the privacy, right? But it's still under big development. I think, for example, right, differential privacy, right? So I add this Laplacian noise to enough such that you cannot recover samples to be identifiable, but you might add too much noise, right? You can also do the thing called feature mixing, right? So I can mix up different features with different ratios, different kinds of algorithms does this as well, right? So such that you can mix do the feature mixing in the feature space to further make the thing not invertible, right? But what kind of theoretical assumption do you have? I mean, differential privacy comes with some mathematical guarantee, but that bound is usually not very applicable, right? But for the others, feature mixing, there's no mathematical, at least to my knowledge, I do not know any mathematical proof of this yet. Finally, you can do, say, homomorphic encryption, right? So I can just encrypt everything. I perform all the inputs on the encrypted part. So what's the problem? The computation is too slow, right? So you need maybe specific kind of hardware to do it, or maybe you need a specific design of the fully homomorphic encryption algorithm to do that, right? So these are all under an active development, to my point of view. Thanks.
Thank you, Professor Chang. That's a very, complete introduction of how we address these ethical concerns and how we take it very, very seriously. So Professor Liang Zheng has already talked about using synthetic data generation to help address the ethical concerns, and Shaw also explained that during our data collection, we pay a lot of attention in terms of privacy protection. Like for track 5, you see that all the human faces and license plate have been redacted properly. I also can add a little bit more on the how we use how we address this kind of ethical concerns, especially for track 1 and track 2. As you can see in track 1, we only have one real scenario. We have 6 synthetic scenario. We want to leverage synthetic data, and because in NVIDIA we have a very powerful synthetic data generation engine, and we want to use this kind of very high quality and high fidelity synthetic data, and that's very close. We want to closely to simulate the real people's movements, and use that to see if we can address the domain gap between real and synthetic data. That's kind of like what Professor Zheng shared about how we do this on track 4. We want to do the similar thing on track 1. But for track 1, it may be a little more challenging because we not only need to model the people, we also need to model the environment, and there are a lot of lighting change and all the kind of diversity that we need to address. So this is a very challenging problem. And also for the real environment here, you can see that for all the people in this scenario, we have 8 people, and they have all signed agreement with us to so their identity can be disclosed. So we take it very seriously on this.
Yeah, just real quick on the previous slide,
Mhm.
the training validation test set where they split between the different environments.
Yeah, so there is a question from one of the audience. He's asking like for the split of training, validation, and test set, do we separate these real and synthetic environments? So this is a good question because we actually only have synthetic data in the training set and validation set. The real data set only presents in the test set, and we didn't release the ground truth of that. So we want to encourage teams to explore methods that address the domain gap. They only train their methods on synthetic data set and see if that worked on real data set. But in reality, actually, I think most of the team, they didn't use the training set, and I think they only use the existing foundation model and run on the test set only. They have already achieved very good results. So in the future, we will also consider how to address that. Thank you for the question. Also for track 2, very quick, because I personally annotated this data set during my internship, which was 5 years ago when we just started the AICD challenge, like for 2 years. And we have this newly received data set called City Flow. In this data set, we actually also redacted all the human faces and license plates, but we didn't do it frame by frame because that takes a lot of time. So in NVIDIA, we have this very well-developed perception pipeline that can automatically detect all the human faces and license plates. So we run through the pipeline. So we do one round of redaction for all the human faces and license plates. And then we hired contractors to help us to redact those, to fix any error that we have using this automatic pipeline. So it saves a lot of time. And you also make sure that we have all the information properly redacted. And I think also we have David online. So David, maybe in the perspective of evaluation, you can also share how we have ethical AI bring into consideration.
Yeah, so I think everybody has mentioned a lot of good things. You know, we've had this challenge going for 7 years now, and this ethical AI has always been at the forefront of our thinking. With respect to evaluation, we've always tried to create evaluation metrics that are fair, that don't advantage one team versus another. We also created from the get-go this evaluation system that provides online results for teams as soon as they, for some tracks, as soon as they submit the results, they get to see the results, the scoring metric, and can see, you know, the top 3 of the leaderboard. So that's also one of the things we wanted to make sure that we're not disadvantaging people by releasing the leaderboard entirely from the beginning. We only show the top 3 leaderboard, and we show it anonymized during the challenge to basically give teams an aspiration, give them the idea that it's possible to improve their score. And we also give them lots of different evaluations throughout the challenge so that they have the option to improve their scoring and do better. Finally, you know, for teams that want to keep their codes private and not release their methodology, we added a few years ago a general leaderboard that allows teams to do that. Versus the public leaderboard requires teams to submit their code publicly and share it with the world. We prefer teams to submit to the public leaderboard, but we do understand that some teams need to keep their methods private, and then they can still compete, but submit to the general leaderboard. Not respective to evaluation itself, I wanted to add one more thing about our efforts along the front of privacy and just general AI ethics. So one important aspect of privacy is basically not, the ability to evaluate video, for example, without sharing that video to other humans. So doing so automatically. And especially, we've identified a long time ago the need to do so at the edge. So, even as far back as actually the first year of the challenge, we encourage teams to create models that will run on edge devices, low power devices. So at the time, I believe we had the Jetson NX2 boards, and we encourage teams to do detection on using those boards. And throughout the years, for different tracks of the challenge, we've encouraged teams to create algorithms that run efficiently in real time on these types of NVIDIA Jetson or other IoT devices, with the idea that the algorithms could run on the edge and provide only the important results to be further analyzed by a human, and thus maintain privacy. The algorithms or the pipeline can also include hiding faces and license plates during that whole process, and can still be done in real time on Jetson IoT devices.
Yep, thank you, David. Also adding to what you said, we also do have the rule that all the teams that they are willing to compete for awards, they need to release their source code publicly, so we can actually all the people that are interested in these problems, they can use their code to reproduce the results and even improve over the existing results. So it's good for the public benefits that we can in the future, if we have the same challenge track and if people have this kind of application in real world, they can use this algorithm.
I also have something I want to add. The following the comments from David and Thomas. So I think, like, in terms of the ethical AI, our ultimate goal is to build a practical model that can solve that have good generability and can solve practical problems. And I think to do that, there are so many challenges that I think Minqing have mentioned. One direction to solve is to create a universe data set. One way is to use synthetic data set, as mentioned by Professor Leong. But sometimes we need to admit that for our existing tracks, for example, some of the data set is kind of a limited. For example, track 3 and track 4, by the nature of the video data set, like those activities as sample is kind of a limited. So to address that, for those limited data set, it's kind of easy to be overfitting, right, on the public leaderboard data set. So I think leading by David, that our evaluation team have come up with the solution to overcome this overfitting issue by introducing another reserved test set B. So that's why for example, track 3 and 4, the final results, the final winner won't be based on this public data set A, since by nature the samples are kind of limited. To ensure not overfitting, we are using the evaluating the final winners based on the performance on the reserved data set B. And to do that, we from the organizing committee side, we need to spend quite a lot of cycle and efforts on evaluating. For example, different teams may train their models on different platforms. Some have powerful machines, some doesn't. And using last year as example, we need to retrain those models using a uniform platform on test set B. Then we test using the, for example, only the same GPU, one GPU, to ensure the fairness across all submitted codes from different teams. So this, we need to give credit to David and our evaluation team. Thomas.
Yep. Thank you. That's very good add-on. We can maybe for all the audience, we can have 1 to 2 more questions on ethical AI if you have. Maybe also audience on Zoom, do you have any questions on ethical AI? If not, I think we can, oh, please go ahead.
And very positive.
Okay, yeah. So the audience commented on what we said, that it's very important to balance the privacy and also the accuracy and performance of the algorithm, and also to benefit the runtime performance and also the accuracy. So in the future, we may want to give more weight to teams that explore this kind of cost-effective methods, and also for teams that really help address the problem of ethical AI. We can have many more of these kind of papers besides the challenge papers that can be presented at our workshop. Yep. So and also I think that also moves us to the next topic, which is on synthetic data generation. We already talked a lot about that, how we use synthetic data generation to help us to preserve like privacy, and also to for all kinds of application. So maybe we can share a little bit about the latest usage of synthetic data generation, and also is there any technique that we can use to accelerate this process, and what are the latest tools that we can use for this kind of application? I think Professor Liang and Professor Zheng, and yeah, maybe you can go first.
Thanks, Thomas. I just talked about the use of synthetic data in the AICT context. I'm probably just discuss a bit more context in synthetic data. So I think the use of synthetic data is not is primarily not only used in privacy sensitive contexts, but also used in contexts where data are really difficult to obtain. For example, I think in Prof. Huang's paper, where study the infant post-estimation problem. I think this is one scenario where it's hard to really get those ground truths, get those training samples where synthetic data can come into place. On the other hand, with diffusion models, I guess the recent work on diffusion models has sparked interest from the community using data from diffusion model to do pre-training, and it is found in a few areas that pre-training using diffusion model generated images have been very successful. For example, one of my colleagues in doing text to image matching area, where you could generate tons of images using text prompts, and those text image pairs are quite good. You just need some light cleaning process before you can use it for pre-training multi-modal language models. So I guess this is another thing. I think also research from Meta indicates that training with diffusion model generated images, because you've got some labels from the prompts of those images, so you can use those things to train the models, and those things gives really competitive results even on ImageNet test sets. So apparently data from diffusion model don't have much privacy issues unless they somehow recover the data from the training, but it's very unlikely. So basically, I think using synthetic data either from those data synthesis engines or diffusion models or other data synthesis sources could be a very important future way of getting data and training models. So I think in my group, we also have this kind of trials where we use not diffusion model, but we are using Unity to generate US work, using Unity to generate vehicles, persons, which are free of privacy concerns, and we've got very competitive results compared with using real world data. Also, in answer to the previous question from our audience, is that sometimes privacy preserving comes at the cost of accuracy, but sometimes if you are using the synthetic data in the right way, it improves the accuracy. So it's not really, you don't have compromise in accuracy. But admittedly, if you are considering fairness, if you're considering other type of things, the accuracy, as we normally understand, is compromised, but the accuracy in terms of fairness is increased. So, for example, the least representative groups, their farewell is improved. So the overall farewell is improved. I guess, so this is my thoughts about using synthetic data and some of the ethical problems facing the AI. Thank you.
Okay, Lin-Ching again. So my point of looking at this synthetic data usage can get back to like history, right? So when does this become an important tool, right? So you can think about when do we need synthetic data, right? So to me, right, suppose in the old days when you do your first machine learning homework, right, the linear regression, right, you have tons of samples. Your model is so simple, right, at night, right, 2 parameters. So in that case, you really don't need a synthetic data, right? Say support vector machine, right? So your support vector machine is learning these supporting vectors and discard all the non-support vectors. You don't need synthetic data, right? So these are the old days. Well, I mean, when we have a deep learning that we have over-parameterized model, that's the time we need synthetic data, right? So data augmentation is some kind of, to me, like early days of using non-realistic but synthetic, because you augment it, you change the perspective, you change color, right? You generate new data samples that help you to better regularize your sample, right? So throw out that kind of thing. It's a dynamic data augmentation, right? So I mean, these are sort of, I think, conceptually can be considered synthetic data generation. But when does this really come to the picture? I think it comes through the autoencoder, because at the decoder part, you can, that's the first, I think, data-driven generated model that can generate data, right? So from the autoencoder, you have UNet, right? So you have this more and more powerful model that you can pre-train. Then you can use that generated model to generate synthetic data. And then because the classification, the regression model you want to eventually train is over-parameterized again, right? So synthetic data help in that case of regularizing or improve your model performance, right? So let's look at the history, right? So UNet, right, CNN, what's the next? It's a transformer, right? So this attention models, right, is then after transformer, I think the bird, and then now the latest is the ChatGPT, right? So look at the trend, I think, and people call this foundation model is the next grade, right? So let's look at the foundation model, right? So ChatGPT has this 195 billion parameters, right? So people says that the number of sentences in the internet is roughly at that order, right? So what we do, I mean, so basically your model is so complex and huge that even a meaningful perturbation of your data, even through maybe just nearly neighbor search, it helps your model to be, again, regularized. I think that's my point of view of why synthetic data is so useful. I mean, for practical examples, say for example, right, if you want to train a reinforcement learning, kind of algorithm, you mostly train your model on a synthetic environment until it converges, sort of works, right? It's like a pre-training, or it's like a foundation model pre-training. after that, you fine tune on your realistic model, right? So that's also another case of why synthetic data is so important. That's my point of view, right? So the other point of view is close to what I just said about the scarcity and importance of data, right? So, I mean, for some case in machine learning, I think we have more abundant data that you have to discard data. So for example, that Google search engine, right? So this Google prompt. I mean, if you are an engineer of Google, you can access to everyone's input. So in that case, you have too many data. You have to throw out, right? You have to do data distilling, knowledge distilling, right? So you have to somehow find a representation that reduce and condense data, right? On the other hand, for other applications like medical imaging, right? So you want to generate synthetic data that can help you regularize your model, right? So these are two different perspectives. They share something in common. The thing is the generative model you want to train, right? So also, right, domain adaptation and continuous learning, right? So how do you forget this catastrophic forgetting and continuous lifelong learning? You need to have some kind of representation that can represent the data. You can forget. Then when you want to learn the new things, you take whatever internal representation you have. That is the generative model, right? That you can continue, you can carry on, you can adapt, right? So you can use that to detect, is there a concept drift? Is there a domain shift? Right. So to me, this generative model, I think very likely some kind of foundation model is something what you want. Because if you learn that, you solve the problem. You can generate things that you can use to train your dedicated model. That's my point of view of why synthetic data is so useful. We can do in discussion. Thanks.
Thank you, Ming-Ching. Yeah, it's very important foundation model. A lot of teams use foundation model for their methods in all the tracks, and we find that that's the trends that, and we also encourage many more teams to explore this direction to improve the current methods. Can I just one more thing here, because I work on this forensics, right? So I think we are at a stage that, thanks NVIDIA, right, we have such powerful hardware and software tools to generate very realistic samples, for example, deepfake, right? For example, these diffusion models that generate some picture that you cannot eyeball identify, is that a true, a real, or fake, right? Fake news. So how do you fight against fake news, right? So this kind of tools, while it generate a lot of society, concerns, we should not develop technology like this, because fake news it's a hard problem, right? It's an important problem, right? So how I think two things. One is, can we develop some tools that can help us or successfully identify something is synthetic? That will be important. In addition to just use that for machine learning, right? For example, right, given a sentence, can you develop a model to say, is this generated by ChatGPT or generated by Midjourney, right? So do you have this kind of forensic tools to do that, right? I think that's important, because, say, if you read a news article with an image, right? So the first question I'm asking myself is this the real picture or not, right? So what's the solution for this image forensic? Do you use watermarking? Do you use active forensic methods that add signature, that you can verify that signature? Do you do this kind of thing in computer security that they do in homomorphic equation, or what's that called, a zero knowledge proof, right? To ensure that you can have some kind of active mechanism to say that this is a real picture taken from this camera. It's not a synthetic one. I think this kind of research will have a growing impact, because I think most of the machine learning AI development is on the other side. It's on improving the synthetic data generation, but very little on the other side of verifying if that is true or violating the ethics of AI. Right? I think these are, the two fields that can actually help each other, the development. Thanks. Yes, thank you, Professor Chang. That's two very related fields. I think something good for our panel is that we have researchers. We also have people from the industry. So from my standpoint, I can share a little bit, like in terms of industry, like how we generate the synthetic data, like what kinds of tools that we use. I went through this a little bit, during our workshop summary, but we can talk more about this So you can, as you can see in track 1, in this data, this is a very challenging data set that we are creating because we want to simulate like real people as much as possible. And we find that because I used to do this kind of vehicle re-identification task using synthetic data, but I know using the Unity platform, there's just so little that you can control. But in this kind of more complex scenario, we need to model the lighting, we need to model the environment and the reflection on the ground plane and the human movement in a natural way. So this we need a platform that's more that have more controllable parameters that to help people to create real data. So we have this NVIDIA have this platform called Omniverse. It's actually a collaborative platform, so everyone can contribute and everyone can use it. And it's based on this USD format, which is the Universal Scene Description. So there can be USD of people, there can be USD of the environment, and we can combine them together. And we have a lot of tunable parameters to help people to diversify it for all kinds of environments. If you see the figure at the bottom right, this is the pipeline that we use to generate the synthetic data. So in Omniverse, we have this omni.anim.people module. So this module can be used to simulate the human appearance and also simulate the movement around the store. So we have a lot of anchor points around the store. So we make sure that all the objects, they follow a specific trajectory in the store. We also have some rules. For example, when people collide into each other, they know how to avoid each other in their movement. So we have all kinds of rules there. And we also have recently improved this tool that we not only we can not only generate the people moving around, they can also move in different speed. They can also run and do all kinds of action like pushing the cart, like selecting items from the shelf. And also we want to simulate more people in the future. You see in this environment, we only have about 6 cameras and 10 people. In the future, we can have 30 people, 40 people. This will be an even more challenging scenario. Besides Omni.anim.people, we also have another tool called the Omniverse Replicator. So this replicator is used to generate labels from the synthetic data. So as you can see, like if we want to generate labels of bounding boxes, and even the track IDs. This track ID can be consistent across cameras. So we can use that to generate multi-camera tracking data. We can also have other annotations like the posts, like the key points. That's also possible with the tool recently. And we, like a lot of you suggested, we can also add the automatic calibration based on a specific format. We can also add the 3D key points on the ground plane for this scenario. So this will potentially enable a more like enrich the research for this field a lot. And also we can generate the labels in all kinds of formats. So currently we generate the format in Kitty and we transform it into the MOT challenge format. But in the future, for whatever format based on your application, we can use the tool to generate. So this is something that I want to share with you. And if you have any feedback using our synthetic data, you want us, you feel, oh, we should add this, we should add that, just let us know. We can continue to improve this. We also have Shaw and David. Do you want to also share about synthetic data generation, your perspective?
Okay, maybe I can go first. So in terms of synthetic data, I view it as a one of the new era in data collection. So data collection is always a big part of like machine learning research or data related work. So I think read some article previously. On average, most of one of the machine learning related project, like 70% of the work is done collecting the data. Like synthetic data, I view it like theoretically no difference from adding a new tool of doing the data collection. For example, using traffic as example, previously you collect speed using like Bluetooth sensor. or radar, and then it can be evaluated using LiDAR to collect cloud points. And recently we're leaning towards using videos. So each of the new tool, after it introduced those data collection diagram, it's not ensure that your quality of the output model would be better than previously. You need to use the tool properly. For example, when using cameras, it's not a given that when you switch from a LiDAR to camera, then the detected vehicle speed will be improved or vehicle detection will be improved. I think similarly to synthetic data, but different from previously, for just adding a new tool, like synthetic data is a new diagram of collecting unseen data instead compared to previously we are just collecting seen data. But still, if we are not using synthetic data properly, then it has some potential drawbacks. For example, if we create a synthetic data from a generative model, then potentially using the synthetic data to retrain a new model, it can emphasize or enlarge the bias already existed in the previous model for generating those synthetic data. So one of my thoughts is like when we using synthetic data, how to design the tool to generate synthetic data would be a very important focus. But the potential of using synthetic data is tremendous, as explained by other members previously. It make the data collection much cheaper. More importantly, it transfers from only collecting seen data to a new domain of collecting unseen data, so that it can give you more opportunities to train a model on a so-called what-if condition.
Yeah, so there's also connect with what Ming-Qing said, that we can leverage a foundation model for more potential use. Also, David, do you also have any thoughts you want to share?
I think everybody else has brought together all the latest, has talked about all the latest tools out there for generating synthetic data. From an ethical perspective, I think these tools also give us the power to generate data ethically, to make sure that, for example, people of all races are represented within the data set that we create that contain people and things like that. I haven't been a part of generating synthetic data itself that much, but we've used it in a couple of the projects over the years, and have, so just from the other side of the table, I can say adding synthetic data does help in training more robust models that work better than just using the limited data that maybe is given to us as part of the challenge. It's clear that the majority of our algorithms are AI-based algorithms that just need a tremendous amount of data to train these massive networks. So the more data that we can include, which includes both real and synthetic data, the better. So for example, one of the things we've done is used 3D modeling to generate cars for one of the projects, and then we used GANs to transfer realism to those cars and make them blend in better with the different backgrounds that we placed those cars in, which were real backgrounds. And using that type of synthetic data generation really helped improve the performance of the detector and tracker that we used in that particular year. That's it.
Thank you, David. So that's from a user perspective. Okay, so we still have a little time. Is there any audience that also have questions on the synthetic data generation that we could answer? Or anyone on Zoom? If not, then we will go to the most exciting part of the challenge. So Sure, I'm thinking. So maybe I can share the screen from my side, and then when you need to change to the next page, just let me know, and then I will click for you. Do you
Yeah,
think
sure. That
because
sounds good.
I think the slide on my side is the latest confirmed with you.
Yeah,
Okay.
yeah, I believe so. Okay, so this could be, as mentioned by Thomas, one of the more exciting or relaxing session of this entire workshop. So let's go directly into track one. So for track one, this is already the 5th year of our MPMC type of track, but this year we are working on synthetic person instead of a vehicle previously. And thanks to Thomas for helping screen all the code submissions from the top teams. We are glad to see that all submissions are eligible in terms of being compliant to our challenge requirements. Thus, the top 2 teams shown here are validated and final. So if you go to next slides, you'll see the congratulations pages for team 6, friends from UW, Eric, and NDHC on winning track 1, and congratulate team 9 from Vietnam National University on being the runner-up. Going to track 2.
Let's clap for the winning teams first. Congratulations.
Congratulations. So going into track 2, so track 2 is also one of our old tracks. This is the 3rd year of this track. The top performance have improved significantly this year comparing to the 2 previous years. And thanks to Fred for helping validating the submitted codes. And the top 2 teams have met all the requirements, and the rankings are validated and final. So for track 2, the winner goes to team 9 again, the friends from Vietnam National University, and the runner-up is team 28, friends from Lenovo. Congratulations. Okay. And track 3. So track 3 is the 2nd time for this driving behavior recognition challenge. So this year we changed a new evaluation score. We use overlapping score over the F1 score used previously for a more robust evaluation. And as we mentioned previously, like due to the nature of this data set, the number of behaviors are kind of limited. So to prevent overfitting, we would need to introduce this test set B. So Thomas, if you can go to the next page. So this year, like we have mentioned, to overcome this, to ensure this ethic and fairness this year, due to the limited time frame, we are still working on this actual test B evaluation. And we are using those, working on those submitted code from the top 5 teams as shown in the table. So the winner and runner-up will be generated from 2 of those 5 teams. And we will contact those teams individually and publish the result on our page, just as the previous years. So for track 4, we have a similar situation with track 3. This is the 2nd time on track 4 as well. And to overcome overfitting, we also need to introduce this test set B. And also, like for this track, we have noticed from previous years, the last year, that the performance on test set B actually have a significant gap between the performance on test set A. So actually the evaluation, the importance of evaluating test set B is kind of proved that we need to finish the evaluation very carefully. So next slides, like same as track 3, we're still working on this, and we will be announcing on our web page soon after the workshop, as well as contacting the teams individually. Okay, and track 5. Yeah, and track 5. So this is the new track this year. And this track is to solve a very practical detection problems, and thanks to Dr. Pranamish Chakrabarty and his teams for creating this wonderful data set. But this year, previously, there is a small bug in our evaluation code that we are calculating the recall incorrectly. So previously, if I remember correctly, we're using the false positive instead of false negative in the denominator of the recall calculation, so that it rewarding a little bit more on the submissions with less detection results. But we, as explained by Prathamesh, we have correct this evaluation code and rerun on every and all the submission results, and we pick the top performance of the team. And our right-hand side is a screenshot of the updated leaderboard. So if I remember correctly, the top 2 teams, due to this new evaluation, they switch position, but the same 2 teams have won this track. So next slides, then we will announce like team 33 is the winner of track 5. Friends from SKKU, and team 58 is the runner-up. Friends from CTC, BUPT, and AUS. So the final page, congratulations. And yeah, and the final page show a very brief summary of all the teams winning the awards. So each track winner will receive an RTX 4070, one of the new NVIDIA's 40 series product, and each track runner-up will receive a Jetson Orin Nano dev kit from the latest NVIDIA's Jetson product family. And due to the chip supply shortages in general, it took us quite some time to receive all those items. No bad news here. Now all the items are in place and ready to be shipped out. We will contact award-winning teams separately after the workshop, and hopefully those devices can be a boost in our future research work. Congratulations again.
Congratulations.
All right, Thomas.
Okay, thank you. Congratulations to all again for track 3 and track 4. We really apologize of the limited time we have to conduct the evaluation on test set B, because we need to run through the inference pipeline and run on another data set to make sure to address the ethical AI concerns. So it will take us a little more time for these 2 tracks, but we will contact all the participants individually on the final results. Okay, so with that, that concludes our presentations and awards announcement. We will have a poster session now. If you have not set up your poster board yet, our poster boards are number 135 to 169. Let me repeat that. 135 to 169 in the West Exhibit Hall. So let us meet there, and then to set up your poster, we can have some time of socializing, and we can also have more discussion to understand each other's method. If you do, because the poster is optional, so if you don't have a poster, you can find an empty poster board, and then you can say I'm the team, for example, I'm the team from UW, or I'm the team from SKKU, and you can introduce your method in this way. Maybe also bring your laptop or iPad or anything. Okay, let's meet at the West Exhibit Hall. Oh, sure, of course. We can send this slide to you.
Okay, yeah, but friends from edgy need to have some thing to show them.应该可以站在这边吧。Good.
We're going to take a photo together again.
Yeah, 我们
先拍个照，不要在那里拍。对。
H. Bonjour. Yeah. I mean, These are our boss. Okay, so fire boss. 这个影响了这个，不能关，因为他们要这个拍照。对，郑老师代表我们。我们 can we not to block this part? Maybe we can divide it into group. Yeah, we can block. We can block. Right. Yeah, the other side. Okay. Thomas, is that okay to get everybody in? Yeah, I can get everybody in. Okay. Maybe for these two professors, your face is well. How about two wine? Yeah. Good. Okay. 3, 2, 1. 3, 2, 1. Here. Let me take this. 3, 2, 1. 3, 2, 1. Okay. Great. Thank you. Thank you. Paid off. Okay.